Welcome back everyone. Today is an exciting day because we are going to write our first Bash script. This lesson is all about putting what we've learned into practice and taking our first steps into the world of Bash program. I've prepared a comprehensive guide that will walk us through creating, understanding, and running a simple Bash script. And we'll start by discussing what a Bash script actually is, comparing it to a recipe to help visualize the concept. Then we'll dive into the practical part. Together we'll create a script that greets the user and provides some basic information. We'll go through this process step by step, from creating the file to making it executable and running it. We'll also explore some fundamental concepts along the way, like the shebang line and echo command and command substitution. Don't worry if these terms sound unfamiliar, we'll explain each one as we encounter it. After we've got our basic script working, we'll take it a step further by adding user input. This will give you a taste of how scripts can be interactive and responsive. Throughout the lesson, I encourage you to follow along on your own computer. Type out the commands, create the script, and run it yourself. Remember, in programming, doing is often the best way is learning. And by the end of this lesson, you'll have created your very own Bash script, something you can build upon and modify as you continue to learn. And as always, if you have any questions or run into any issues as we go through the lesson, please don't hesitate to ask. We're all here to learn together and no question is too small or silly. So, are you ready to write your first Bash script? Let's get started. Now, what is a Bash script? Before we start coding, let's talk about what a Bash script actually is. This is a think of a Bash script as a recipe. Just like a recipe tells you the ingredients you need and the steps to follow to create a delicious meal, a Bash script is a set of instructions that tells your computer what to do. In more technical terms, a Bash script is a plain text file containing a series of commands that the Bash shell can execute. It's like writing down all the commands you type in the terminal, one after another, and then telling your computer to run them all at once. So let's switch to creating your first script. We'll start with something simple, a script that greets the user and tells them the current date and time. Here is how we'll do it. In our terminal, we'll navigate to a directory where you want to create your script. You can use your home directory. To check it, just type pwd, and your home directory usually is located in home directory, /home directory, and then /your directory. Or you could create another directory, a new directory for all your project. To do this, just type mkdir and the name of the directory. For instance, scripts. Now, if we type ls, we can find scripts directory in our home directory, and we can change to this directory by typing cd scripts. Now, as you can see, our prompt is changed, and we've got scripts as our current working directory. Now, to create a script, we'll need a text editor. For these purposes, you could use any text editor installed on your system. For instance, if you've got Nano editor installed on your system, you could type nano and the name of the script. Or you could use Vim editor and type the name of the script. For instance, my _first _script.sh. So if I press enter, I'll start a new script in Vim editor. And to start typing in Vim, as you remember, we need to change to insert mode by pressing I. When we did it, in the bottom left corner, you can find insert word printed with all uppercase letters. Now we can start typing. And let's start typing the following into the file. Hash followed by exclamation point, followed by bin/bash. Next we'll press enter. We'll press enter one more time to have an empty line here and start typing the body of our script. And the first command we'll type is echo. We've used this command in previous demonstration lesson when we wanted to print out the contents of PS1 variable. So we'll use it once more. Echo. By the way, let me experiment with appearance. Let's try light theme, light appearance, and white appearance. Which one is better? Let's try black. I guess black is best. So echo and a string in double quotes. That is the line which will be output on our screen. So I'll type hello, comma, bash, programmer, exclamation point, and we close double quotes. Hit enter and type another line here. Actually, in Vim, we can exit insert mode and copy this line with pressing twice Y. So I'll press Y twice, and then I can press D, I'm sorry, not D, but P, to insert this line. Now, as you can see, we've copied the previous line and inserted it below it. Now we can place our cursor to the end of this current word by pressing E, that'll be end, E again, that'll be an end of the next word, just double quotes, and we can press A to append new text. As you can see, when we press A, Vim entered insert mode automatically, and we can write some text. But let me exit insert mode and go back to the beginning of this word. I'll press B, that will place the cursor to the beginning of the word, and we can delete the rest of this phrase until the end of this phrase. To do this in Vim, I'll press D followed by W, delete word. Again, we can delete another word. One more time, DW to delete the rest. Now as you can see, we've deleted extra character, which is closing double quotes. So to undo this change, we can press U. And we can press A to append again. Let's delete this exclamation point and start typing today is $character. That's how we refer to the variable, which will be keeping date command, the results of date command. That's the syntax we use. We place the command in parentheses. Again, let's exit insert mode by pressing escape. Copy this line by clicking Y twice and pressing P to insert a new line below it. Go to the end of echo word by pressing E again and press A to start appending. No, actually, let's delete the word by pressing DW once more, and press A to start appending double quotes and add some text. Your current directory is, actually, let's type working directory is colon. And again, we'll do the same as in previous line. We'll declare a variable which will hold the result of pwd command. Close double quotes, and that'll finish our first small script. So we'll exit insert mode by pressing escape, then we'll type colon WQ. Now if we ls, we'll find my first script shell. Let me clear the screen and type ll, remember LL is an ls for ls-la, and we can find that this script has these permissions. And by the way, before we talk about permissions, let's break down our first script really fast. So to view the script, I'll type cat my, then I'll press tab to autocomplete the script's name, hit enter, and here is our script. It starts with this line, hash, ! /bin/bash. This first line is called a shebang. It tells the system that the script should be executed by bash. The next line, the echo command, is used to print text to the script. And $date is a command substitution. It runs the date command and puts it out into our echo statement. And finally, $pwd in parentheses runs the pwd command to show the current directory. Now, that we've created our first script, we need to make it executable. This is like giving your computer permissions to run the script. And the permission, if we take a look at previous output, we miss letter X. The permission to run the script is letter X. So to add this permission, we use change mode command, and then we'll simply tell this command to add X permission, to add execution permission. So this plus X option adds executable permission to our script. And we need to specify the script's name, which is myfirstscript.sh, hit enter. Now, if we rerun the previous command ll, we'll find that the script's color has changed. Now it's green, and now we have several X's in permissions list. The first X here, the second X, and for everybody else, also X. Let's clear the screen. Now for the moment of truth, we'll run our script. There are two ways to do this. Using the bash command, so we can type bash myfirstscript, hit enter, and that will run our script. And another way to run our first script is such a syntax: dot, slash, and the name of the script, myfirstscript. Hit enter, again our script has run successfully. So this dot slash tells bash to look for the script in the current directory. This dot is referring a reference to our current directory. Now, as you can see, everything worked correctly, and we see a greeting, today's day, and our current directory printed on the screen. Exciting, right? You've just run your first bash script. Now some words about shebang. Let me clear the screen and get back to this cat myfirstscript.sh command. The shebang tells the system that interpreter to use to run the script. In this case, we are saying use bash to run the script. It's like putting a label on your script saying handle with bash. While hash ! /bin/bash is common, you might also see hash ! /usr/bin/env bash. This is more portable across different systems. Let's type this line. It looks like, let me copy this one and insert it here, and we'll go back one word by pressing Control left arrow, and we'll change bin to usr/bin/env, and then press space and type bash, and we'll describe it for portable use. Let's comment out this line by pressing Shift-Alt-# or 3 on your keyboard. You could also omit, let me paste this line, you could also omit hash ! /bin/sh. That's more for POSIX compliant shell. Also, let's command this line. I'll press Shift-Alt-3 not to run this line. But for our purposes, we'll use the shebang as in our first script, and it works perfectly fine. Now that we have a basic script working, let's add a bit more to it. We'll modify our script to ask for the user's name and then use it in the greeting. Let's reopen the script by finding the previous command. I'll press up arrow several times. Here it is, Vim my first script. And let's move to the start of this file by pressing G twice. Remember, to move to the end of the file, we press Shift-G, like this. And to move to the start of the file, we press G twice. Now we'll go down one line and hit I to insert, add an extra line, and type the following 2 lines. We'll type echo, what is your name, colon, close double quotes, and another line, read name. So we use name variable, and read command waits for user input and stores it in a variable name. And we use this name variable to refer to the values stored in the name variable. I'll save this script, WQ, and let's rerun the script with /myfirstscript.sh, and let's provide the name. I'll provide my name, and of course I forgot to specify that we need to use variable name in this line, hello bash programmer. So let's re-edit the first script, go to hello bash programmer line, and rewrite it. So I'll type WD to remove all these words, press A to append, and we'll type hello and comma after hello. Then we refer to the variable name. So to refer to a variable, we type $name and add some text here. Welcome to the world of bash scripting. Let's remove this extra space, hit escape, W, Q, clear the screen, and rerun this script. Now we'll provide our name, which is Vid, along with welcome to the world of bash scripting. Now our modified script works perfectly well as planned. Now to wrap up, and there you have it. You've written, modified, and run your very first bash script. And if we recap what we've learned that a bash script is a file containing a series of commands. We started our script with a shebang to specify the interpreter. We can use echo to print out to the screen. We can use command substitution. Its syntax is as follows: $ and parentheses, which allows us to use the output of commands in our script. We need to make script executable with change mod plus X before we can run them directly. And then we can use read to get input from the user. And this is just the beginning of your bash scripting journey. With these basics, you're well on your way to creating more complex and useful scripts. Remember, the key to getting better is practice. So try modifying the script further, or create new scripts to automate tasks you do regularly. In our next lesson, we'll dive deeper into bash syntax and start exploring more powerful scripting concepts. Until then, happy scripting. Welcome back, everyone. In this lesson, we are diving into bash syntax fundamentals. This is where we start to really get into the nuts and bolts of bash script. Don't worry if some of this feels a bit abstract at first. We'll use plenty of examples to make these concepts concrete. Now, I've prepared a comprehensive guide that will walk us through the fundamental elements of bash syntax. We'll start by exploring variables, what they are, how to create them, and how to use them. Think of variables as labeled boxes where we can store information for later use. Then we'll look at data types in bash. This might surprise some of you coming from other programming languages because bash handles data type a bit differently. We'll see how bash treats everything as strings but can still work with numbers and even arrays. We'll also dive deeper into command substitution. We've already met such examples, and we touched on briefly on our last lesson. This powerful feature allows us to use the output of commands as values in our scripts. Quoting rules are next on our agenda. Proper quoting can be tricky to master, but it's crucial for controlling how bash interprets our commands. We'll look at different types of quotes and how they behave. Finally, we'll explore some special variables that bash provides. This gives us useful information about our script and its environment, which can be incredibly handy for writing more advanced scripts. Throughout the lesson, I encourage you to try out these concepts in your own terminal. Type out the commands, create small scripts, and see what happens. Programming is very much a hands-on skill, and the more you practice, the more comfortable you'll become with this concept. Remember, if anything is unclear or if you have any questions, please don't hesitate to ask. We are all here to learn, and often your questions can help clarify things to others as well. So, are you ready to dive deeper into the world of bash scripting? Let's get started with variables. Now, in programming, a variable is like a labeled box where you can store information. In bash, we use variables all the time to store and manipulate data. To create a variable in bash, you simply give it a name and assign it a value. Let's take a look at the basic syntax. So we've got variable and value. That's a basic syntax for using variable. Notice there are no spaces around the equal signs. This is important in bash. So please remember that you don't use spaces after variable and before equal, and after equal and before the value. Let's try another example. I can type my name equal width. And of course we place variable value, which is width in this case, in double quotes. Hit enter, and now we can use echo, correctly type, and add some text, for example, hello. Then we use $ to refer to the variable, my name, and we close double quotes. Hit enter, and we'll get such a string, hello with. So if we run this, we'll see hello with. A few things to note. Variable names can contain letters, numbers, and underscores, but they must start with a letter or underscore. You cannot start a variable with numbers. Also remember that bash is case sensitive. So my name, my underscore name, and my underscore name with, let me type it like so. My uppercase underscore name uppercase is not the same as my underscore name. Bear this in mind. So these are different variables. And when we want to use the value of a variable, we put $ in front of it. Now, by default, variables in bash are global. This means they can be accessed from anywhere in your script. However, if you want a variable to be local to a specific function, you can use the local keyword. Let's take a look at the example of a function. For this, I'll create a function in Vim. By the way, let's change to scripts directory. Let's take a look at what we've got here. Let me rename my first script to contain number. That'll be our first script. My first script .shell, and we'll create a second script. We'll name it function example, for example, .sh. Oops, I forgot to add touch command, so I'll find the previous command, press home, and add touch to .function example.sh. Now I'll use Vim to open this file, and we'll create a first function example. To do this, we'll press I first of all, and then we'll use function keyword followed by the function name, for instance, greet. Then we open curly braces, hit enter, and add function body. For example, local keyword, the name of the variable, which is, for instance, Bob in double quotes. Then we need to output it to the screen with echo, and let's type some text here, hello, name, close double quotes. And now we'll refer to this function, which is greet, and also we'll try to refer to this function from outside. So I'll type echo outside the function, and of course outside, not outside the function, comma. Now we'll try to refer to the variable name inside of greet function. So name is, and the variable name, close double quotes, save the file. Let's change the permissions. We'll use change mode to function example. And let's run this script we've just created. And by the way, I forgot to add shebang. So let's take a look at what happens if we run such a script. Function line 6 syntax error unexpected end of file. So let me reopen this. Go to the start of the script by pressing G double times, hit insert, and add shebang. So we'll type hash exclamation point slash bin slash bash, add one line here, and save the file. Try to rerun it. Oops. I've reopened the file. To quit the file without saving, and if you haven't added it, we type just Q. Clear the screen and try to run this file once more. Now we get syntax error line 8, the same error. So for learning purposes, I've reopened this script, and let's take a look what could be wrong here. That's how you troubleshoot the script. Let's see. We've got function, its name greet, and we have opening curly braces. If we have opening curly brace, we need to have a closing curly brace. So this function definition is missing a closing curly brace, and the greet function call is inside the function definition, which is incorrect, because there is no closing brace for the function before we try to call it. And to correct this, we'll go to the end of this last line of the function body, which is echo hello name, press Shift 4 or $ to go to the end of the line, press append, press enter, and add closing curly brace. Now this function is correct, and as you can see, Vim output visually shows opening and closing braces. Let's exit insert mode by pressing escape and save the file and try to rerun this function. Now this function works correctly, and we get back to the local functions we've been talking about. So the first line shows that we can use local function inside local variable inside the function, which is name equaling Bob. But when we try to refer to this function outside, to refer to this variable outside the function, we cannot do this. And as you can see, we don't see variable name at the end of this line. Let me reopen this function and show you once more. So we use name variable inside of the greet function. and we can refer it inside of this function. But when we refer to this function outside, to this variable outside of the function, it won't work. Let me close this file by typing Q. Now, unlike many programming languages, Bash doesn't have explicit data types. Everything is essentially treated as a string. However, depending on the context, Bash will attempt to treat the values as a number when needed. Let's look at some common types of data you'll work with in Bash. Strings are sequences of characters, and you can define them with or without quotes. For example, name1 is Alice in double quotes, and name2 is Bob without quotes. Now let's try to echo name1 and name2. And as you can see, we can refer to both variables, Alice with double quotes and Bob without double quotes. But using quotes is generally a good practice, especially if your string contains spaces or special character. Now, although Bash treats everything as strings, it can perform arithmetic operation. Let's add some variables. For example, num1 is 5 and num2 is 4. Now we can perform arithmetic operations with these variables. We'll type sum equals, and to perform arithmetic operation we have a special syntax. We'll use $, double parentheses. Now we'll refer to num1 plus num2, close double parentheses, hit enter. Now we have a variable sum which contains this arithmetic operation, and we can refer to it with echo the sum is and sum variable. Hit enter, and that'll be an arithmetic operation calculating num1 plus num2, which is 5 plus 4. And we get an output, the sum is 9. Let's clear the screen and continue. And we continue with arrays. Bash also supports arrays, which are collections of items. So, for example, fruits variable, and now we'll add a collection of items in parentheses. So we'll open and add collection of items in double quotes now. For example, apples, bananas, and cherry. We'll close parentheses, hit enter, and let's output it to the screen with echo command, and we'll type the third fruit is, and now we can refer to the arrays, to the array fruits and its item. To do this, we'll type $ again, and we'll type a variable name, which is fruits. Now, to refer to the item, to some particular item of this array, first off, we should use curly braces before array name and after its name. So we place array in curly braces when we refer to it. And when we refer to the array's item, we place it in square brackets and specify the array's number, which is 2. Let's hit enter. Oops, I forgot the second double quotes to close this echo string. And as you can see, the result is the third fruit is cherry. By cherry, we refer to the second item of the array. That's because the array indices start at 0 in Bash. So if we take a look at this array, apples item will be number 0, bananas item will be number 1, and cherry item will be number 2. That's why we get this result, the third fruit is cherry. Now some words about command substitution. We briefly touched on this in our last lesson, but let's explore it a bit more. Command substitution allows us to use the output of a command as a value. There are two syntaxes for this. We can use backticks, like this, command and closing backtick. That's the first syntax. And we can use parentheses. We'll add dollar, parentheses, command, closing parentheses. That's the second syntax. So the parentheses method is generally preferred as it's more readable and can be nested. Let's take a look at some example. For instance, let's use current date variable, and that'll be with command substitution. And we'll use parentheses method. So for this we'll type dollar, parentheses, date command, and we need an output in the following command. In the following method, we need to output first year, then month, and place dash between year and month, and dash between month and day. And we'll close parentheses. Hit enter and echo the result of this current date with the following string. Today's date is dollar current date. We'll close double quotes, hit enter, and of course I'll get current date with hash because we don't use hashes before the variables. So we'll need dollar. And also we don't need these pluses before the day and month. Let's rerun the previous command, echo current date, and it'll output current date in this format, year, month, date. I'll clear the screen. And by the way, let's output now some words about voting rules. Voting can be a bit tricky in Bash, but it's important to understand. There are three types of votes and they behave different. The first type is no quotes. Variables and command substitution are expanded. Single quotes, everything is treated as a literal string. No expansion happens. And double quotes, variables and command substitutions are expanded, but spaces are preserved. Let's see an example. Let's add a variable name, and it's Alice in double quotes. Now, let's use three examples with echo command. Well, the first example is echo. The name is name variable. Hit enter, and we'll get the name is Alice. Now let's place it in single quotes, hit enter, and we'll get the name is name, dollar name as a string. It's not a variable now, and it's a string, because everything is treated as a literal string inside single quotes. No expansions happen here. And the third example will use double quotes for the name is string, and we'll get a variable value, Alice, again, because variables and command substitutions are expanded in double quotes, but spaces are preserved. And the last block about variables for this lesson, it's about special variables. Bash has several special variables that provide useful information. Let's create a simple Bash script. We'll name it special variables. So I'll type touch for.special_variables.sh. And let's open this script. We'll start by pressing I. We'll add a shebang bin bash. And then we'll add some example using special variable with echo command. And the first special variable is $0. It outputs the name of the script. So we could type script name is, and now we refer to the special variable, which is $0. Close double quotes, hit enter, and refer to the second special variable. I'll type echo, and special variable $1 and $2 and so on, $3, 4. That's the command line arguments passed to the script. So we could add first argument, colon, and refer to the special variable by typing $1, close this, Let me exit the insert mode, press Y double times, and press P to insert several lines here which we can edit. Let's go back to the line 3 of echo blocks. Go to first by pressing W. That will go one word further. And I'll press A to append, delete first and replace it with second. Second argument is $2. Now, the next special variable is $hash. It will output the number of command line arguments. So if we go to this line, we can change $hash to refer to the special variable and replace this text with number of arguments and go to the next special variable, which is $add character. It will output all the command line arguments. So again, I'll press escape to exit insert mode, copy this line and paste it under the current line. Go to the number, press A to append, delete these two words and type all argument and replace hash with add character. The next special variable is $? That will output the exit status of the last command. So let's remove one here and place question mark and replace this text with the exit status. Actually, let's type like this: last commands exit status. And the last special variable is $2. It will output the process ID of the current script. So I'll hit enter here, echo scripts process ID is, and will refer to the special variable which is $2 characters. Close double quotes, save the file. Let's give it execution permission with change mod plus X for special variables.sh. And now we can run this script and see the results. As you can see, let me clear the screen first and rerun it. As you can see, it output the script name is, that's special character $0. Then first argument, that's special character $1. Second argument, $2. Number of arguments, that will be special character $hash. Then all arguments, $add. Last commands exit status, that will be special character, special variable $question mark, and 0 means that script ran successful. If we get some other numbers here, that means that script ran or command ran with errors. And script's process ID, that's a special variable $. We've covered a lot of ground today. We've explored variables, data types, command add, substitution, voting rules, and special variables in Bash. These are fundamental concepts that you'll use in almost every Bash script you write. Now let's recap the key points. Variables in Bash are created with name equal sign value syntax. Everything in Bash is essentially a string, but it can perform arithmetic operation. Command substitution with $ parentheses and command inside of parentheses allows us to use command output as values. Voting rules are important for controlling how Bash interprets our commands. And also, Bash provides special variables that give us useful information about our script and its environment. For practice, try writing a script that uses these concepts. Maybe a script that takes a user's name as an argument, greets them, and tells them the current date and time. Remember, the best way to learn is by doing. In our next lesson, we'll dive into control structures like if statements and loops, which will allow us to make our scripts even more powerful and flexible. Until then, happy script! Welcome back, everyone. In this lesson, we are going to dive into working with files and directories. This is where bash scripting starts to get really practical and powerful. We're going to learn how to navigate and manipulate the file system using bash commands. I've prepared a comprehensive guide that will walk us through the fundamental commands for working with files and directories. We'll start by understanding how the file system is organized in Unix-like systems. Think of it as a big tree with branches and leaves, understanding the structure as a tree. So, if you get the structure, that'll help you navigate it more easily. Then we'll explore essential commands like pwd, ls, cd, mkdir, touch, cp, mv, and rm. Each of these commands is like a tool in your toolbox, and we'll learn how to use each one effectively from the scripting perspective. We'll also delve into the important topic of file permission. In Unix-like systems, every file and directory has associated permissions that determine who can read, write, or execute them. Understanding and managing these permissions is critical for system security and proper file management. Throughout the lesson, I encourage you to try out these commands in your own environment. Create some directories, move files around, change permissions. The best way to learn is by doing. At the end of this lesson, we'll put everything together in a practical exercise. We'll write a script that sets up a project directory structure, demonstrating how these individual commands can be combined to automate tasks. So let's get started. And before we start manipulating files and directories, let's take a moment to understand how the file system is organized in Unix-like operating systems, which is what bash is typically used on. As I've said, think of the file system as a big tree. At the very top, we have the root directory. So if I clear the screen here and type ls/, that is the definition of the root directory, hit enter, I'll get all the directories under this root directory. So please remember that / represents root directory. Everything else in the system is a branch or leaf of this tree. For example, your home directory, where your personal files are stored, is typically located at /home/ your username. You can type ls/home, hit tab to autocomplete, and that'll be your home directory, starting with root directory / and then some levels down, which is home and your home directory name. And if I cd to home directory and type tree, we can get an output in a tree view. And by the way, this dot is representing your current working directory, which in my case is home. So home is my current working directory, and then tree going down the levels. The name of the directory, my home directory, and then the name of the directory inside of my home directory. So understanding this structure is crucial as we start to navigate and manipulate files and directories. Now let's start with the essential commands for working with files and directories, and we'll go through each command, explain what it does, and provide example. The first command to use is the pwd command. Let's type it, pwd. This command tells you which directory you are currently in. It's like asking where I am in the file system. And in my case, I'm in a home directory, /home. The next, the most used command is ls command. We've used it several times before. This command lists the contents of a directory, and by default it lists the contents of the current directory. So if I clear the screen, type ls, that will list the contents of my current directory. But I can also provide the directory I want to list. For example, /home/ /my home directory. And that'll list the contents of my home directory. We can also go down this tree and list the contents of scripts directory. And as you can see, it'll reveal 4 scripts, and the third script doesn't have execution permission because it's not green. By the way, in your system, the output could be different because not every system reveals executable files as green one. The next, another most used command is cd command. It's used to navigate between directories, and it's like moving from one room to another in a house. So to move to my home directory, I'll type cd and the name of my home directory. Now I can type ls or pwd to reveal my current working directory. Now to move up one level to the parent directory, we can type cd 2 dots. That will move us up one level. And to move to your home directory from anywhere, you can type cd followed by tilde. This tilde represents your home directory. Now, if we type pwd, we'll find ourselves in our home directory. Let's change to the root directory, and we can also type just cd command without any parameters, and that'll bring us back to our home directory as well. If we type pwd, we'll find that we are back in the home directory. Let's clear the screen. And the next command is mkdir. This command creates a new directory. We've already encountered it, but let's use it one more time. We'll type mkdir my_new_directory. That's ls, and we'll find that there is another new directory in my home directory, which is my new directory. You can create multiple directories at once. For example, we could type mkdir and specify the directories you want to create. For instance, dir1, dir2, and dir3. Hit enter, ls, and you'll find that these 3 dirs have been successfully created simultaneously. The command to create a single file is touch command. This touch command is primarily used to create empty files, but it can also update the access and modification times of existing files. Let's create a new file. We'll type touch new_file.txt ls, and we'll find there is a new file.txt in our home directory. Now let's copy this new file with cp command. Cp command is used to copy files. Let's say we want to copy new file to dir1 with a new name, for example, this destination_file.txt. Enter. Let's ls dir1 directory, and we'll find that destination file.txt is copied from new file.txt to dir1 directory. We can also copy all files, all directories containing files to a new directory. For instance, let's copy dir1, and to copy all the files which this directory contains, we can use cp-r argument or parameter, and let's say we want to copy it to dir4. Hit enter, ls. Now there is a new directory dir4, and if we ls dir4, we'll find that it contains destination file.txt. Now we can also move files, and for this we use move command, mv command, which moves files or directories, and it also can be used to rename files. Let's say that we want to move new file to dir3. We'll type mv new file, and then we'll type dir3 destination directory, and that will move this file to dir3. Now as you can see, it's gone, and if we ls dir3, we'll find that this file, new file, is now inside this directory. Now let's say we want to rename this new file inside dir3 directory, so we'll type move dir3 new underscore file.txt, and we need to rename it to dir3 renamed underscore file.txt. And if we ls dir3 directory, we'll find that there is renamed underscore file inside of this. And of course, we can remove files with the rm command, which deletes files or directory. So be careful with this command, as deleted files cannot be easily recovered. And to remove renamed file, we'll just bring back this command, go to the beginning of this command, and type rm dir3 / renamed file.txt. And if we cd to dir3, type ls, we won't find this renamed file.txt because it has been removed successfully. We can also now remove an empty directory. Let's remove this dir3 directory by typing by cd to dots to go one level up, list the contents of our home directory, clear the screen, and type the following command, rm dir3. Now, if we type ls, we won't find dir3 here because we've just removed. And of course, we can remove a directory and all its contents with -r parameter. Be very careful with this because it removes everything inside the directory and the directory itself. So I guess we've got dir4 with some contents. Let's list it. ls dir4. Yes, we've got a destination file here. So now let's try to remove this directory with rmdir first. So we'll type rmdir dir4, hit enter, and we'll get an error, failed to remove dir4 because this directory is not empty. To remove everything inside of this directory and the directory itself, we'll type rm-r and then dir4 directory. Hit enter. Now if we ls, we won't find dir4 because it has been successfully removed with all the contents. So be very careful with this command. Now, when we've done the manipulations with files command, let's switch to file permission. In Unix-like systems, every file and directory has associated permissions that determine who can read, write, and execute them. Let's break this down. File permissions are represented by a string of characters like R, W, X, R. So let me clear the screen, create a new file with touch command. Let's name it file1.txt and list this file with the ls command, and I'll use LA parameters for this touch command for this file1 to reveal all the properties of this file. And this first block of the file is file permission. We can find R letter here, W letter, and so on. So the first set of this block represents the owner's permission. This first block is owner's permission. The second set of block represents the group's permission. So this second set, which is -r represents group's permission. It means that group has only read permission in this case, and owner has read and write permission. And the third block or set represents everyone else. In this particular case, everyone else can only read this file, and they cannot write to it, and they cannot execute this. So again, R stands for read permissions, W stands for write permissions, X stands for execute permissions, files, or access permissions for directory. And dash indicates that the permission is not granted. To view the permission, you use ls-l command, as I've done in this case. Now we can change permissions, as we've seen before, with chmod command. It's used to change file permissions, and there are two ways to use change mode. The first one is symbolic method. We've done it already. We can type change mode plus, let's say we want to add execution permission to user. In this case, we need to specify before plus user, and then we need to specify the permission, which is x, and the file name, which is file1.txt. Now, if we ls-la file1.txt, we'll find that user has execution permission. So they can read, write, and execute this file. Now, if we want to add, for example, write permission to the group, we can do the following. We can specify change mode, then G for the group, and W to specify a write permission to file 1. Let's do this and get back to ls command. Now we can find that the group can read and write to this file, but they cannot execute. Now, for instance, we want to give read permission to other, which we already have, but let's do it once more. We'll find the previous command and replace G, which was group, to O, which is other. And let's give them read permission. Hit enter, rerun ls command. Now others can read. We can also give them write permission. So we'll replace R with W and recheck ls again. Now others can write, as you can see. R for read, W for writing. And there is another method which is numeric method. Let me clear the screen. I'll press Ctrl L. So in this numeric method, each digit represents a set of permission. And 4 stands for read, 2 stands for write, and 1 stands for execute. You add these numbers to get the desired permission set. Now let's move on to our practical exercise. Let's put all of this together in a practical exercise, and we'll create a script that sets up a project directory structure. So let me change to scripts directory and create a new script with such command, and that will be 5.setup_project.sh listed, and we'll open this file with Vim, hit I to insert, add shebang, which is bin bash, add an extra line, empty line, and start typing our script. First, we need to create a good structure for our script, and it's best practice to use commands. So we'll start it with command and describe what we'll be doing. Create a project directory. How to do this? We'll use mkdir command and project name, for instance, my_project. Hit enter, and we'll cd to this project by typing cd my_project. The next block will be create subdirectory, and we'll use mkdir again, but this time we'll create several directories, for example, source, docs, and tests. The next block will be to create some empty files, and we'll use touch command and specify the file names. For example, we want to create main.py file in source directory, readme.md in doc directory, that's not doc, that's docs. And in tests, we want to create tests_main.py file. Now we want to set permissions, and we'll do this with the change mode command, and we'll set permissions with numeric methods. So we'll type 755, and we'll set it for src for source main.py file, and we'll set another permission which is 644, and we'll set it for docs readme.md file. And by the way, I've made a typo here. We'll need not readme but readme.md file. Now we'll list the directory structure. For this we'll use ls-uppercase-r. And the final block will show the file permission. For this we'll use ls-l command, and we need to specify the files. So let me exit this insert mode and copy this line with pressing Y twice, and I'll press P here and change touch to ls-l and the files we need to list. By the way, let me go back to command mode from insert mode and go to the end of this line by pressing Ctrl+4, not Ctrl+4 but 4 to go to the end of the line. And I'll delete this file. We don't need to look for this permission. Exit insert mode again, and we'll delete this last line, ls-l. To do this, I'll press D twice. Now let's save this file, give it execution permission with change mode +x, 5 setup project.shell, list it. Now let's copy this file with cp command. We'll copy file 5.setupproject.sh to home directory, my home, my username, and we'll create a tmp directory there. Enter. Yes, and we need to specify the file's name, which is 5.setup_project.sh. Enter. Okay, yes, cp command can't create new directories all the way. So we'll need to create the destination directory first with mkdir home, my username, tmp, and now copy the previous file. I'll clear the screen, cd to level up, ls, go to temp directory, list it, and here we'll run this script to create the directory structure inside of temporary directory we've just created. So I'll type // and the script name. So we've got one error here. Change mode cannot access source main.py. Let's clear the screen, check what has been created. As we can see, my project directory has been successfully created. If we list my project, we can find that docs, source, and test directory has been successfully created. Now let's open the script we've just modified, we've just run with Vim, and check it. Now, as you can see, I've made a typo here in mkdir source directory. So let's append and delete and rename it to src. Rename this one to src as well. Change mode is correct, src/main.py, and we'll also correct this src. Also, let's add echo command before this ls-r. I'll type echo project structure, save the file. Now let me remove the previous directory, which is my project, with rm-r, my project, ls again, and rerun the script. Now we can see that the script runs as expected. It reveals project structure, and it reveals the permissions, which is 755 permission. The first digit is 7, that's 4 + 2 + 1, meaning owner can read, write, and execute. Second digit is 5, which is 4 plus 0 plus 1, meaning that group can read and execute but not write. And third digit 5, that's 4 plus 0 plus 1, meaning that others can read and execute but not write. And the second permission, 644, the first digit is 6, which is 4 plus 2 plus 0, meaning that owner can read and write but not execute. And second digit in it is 4, which is 4 plus 0 plus 0, meaning that group can read but not write and execute. And third digit 4 plus 0 plus 0, meaning that others can read but not write and execute. So as for this script, the script successfully created the project structure, a main directory, which is our current directory, and that's dot, 3 subdirectories, dots, source, and tests. It created the files as requested, read in docs file, readme in docs file, main.py in source directory, and tests main.py in tests directory. Then ls-r command showed the recursive listing of the directory structure, and the permissions were set correctly. Read-write permission for the owner, and group and others can only read. And the second file, main.py, owner can read, write, and execute, and groups and others can read and execute but not write. Also, you may notice this dot after the permission string. Here it is. This dots is specific to certain Linux distributions, like mine. It's CentOS. Mine is RHEL 9 Linux distribution, and it indicates the presence of SE Linux security contacts. It doesn't affect the basic file permissions we've set. So overall, our script worked as intended. And wow, we've covered a lot of ground today. We've learned how to navigate the file system, create and manipulate files and directories, and manage file permission. These are fundamental skills that you'll use in almost every bash script you write. And remember, the key to mastering these commands is practice. Try creating your own scripts that work with files and directories. Experiment with different commands and options. And most importantly, don't be afraid to make mistakes. That's often how we learn the most. In our next lesson, we'll explore how to process and manipulate the contents of files, which will open up even more possibilities for your bash scripts. Until then, happy scripting. Welcome back, everyone. In this lesson, we're going to build on what we've learned so far and introduce some exciting new features of bash scripting. Now, I've prepared a guide that will walk us through creating an enhanced version of our file operations script. This new script incorporates several advanced concepts that will make our bash script more powerful and flexible. We'll start by looking at the complete script, and then we'll break it down piece by piece. We'll explore new concepts like special variables in bash, command substitution, getting user input, working with timestamps, setting file permissions, and modifying configuration files. Don't worry if some of this sounds complex. We'll go through each concept step by step, with plenty of examples and explanation. As always, I encourage you to follow along on your own computer. Type out the script, run it, and then see what happens. Don't be afraid to experiment. Try changing some of the commands and see how it affects the result. So, as far as you remember, we've learned about basic file and directory operations, and today we're going to take it up a notch and explore some more advanced bash concepts while building a more complex file operations script. So let's dive in. First, let's look at our enhanced script, and I'll change to scripts directory and create with touch command a script named 6.file operations, and bash concepts. .sh. I'll open it with BIM editor, enter insert mode, and add shebang bin bash. And first off, we'll add a command, display script name and current date / time. And to do this, we'll use echo command as usual, and we'll add the following string, running script, and now we'll use a special variable, which is $0 to output the script name. And we'll add one more echo command, echo current date and time, $, parentheses, and inside the parentheses we'll add date command. And we'll close double quote and continue to the next block. We'll add it with a command as usual, and it'll be asked for user input. And again, we'll use echo command and enter your name string. Let's add a space here and close this string. Followed by read command and user name variable. Now let's add another echo command. We'll add a string hello, comma, $, username, exclamation point, welcome to the file operations script. Let's add another block, starting with command, and we'll add create a new directory with timestamp. And let's add a timestamp variable containing the following data. We'll use command substitution here, and the structure for the command substitution, as you remember, $, parentheses, and the command inside the parentheses. And that'll be date plus %, year, %, month, day, underscore, hour, minute, and let's add second. That'll be the command inside the command substitution structure. Now let's add another variable, new underscore dir, containing my underscore file, and let's use $timestamp variable, and we'll close double quote. And now let's use mkdir command, and that'll be new underscore dir variable. We'll add in another block and a command to it, changing to the new dir. Let me hit enter several times to scroll it up. Now we'll use cd command and followed by new underscore dir variable. The next block will be to create several files in this directory. So let's add a command here, creating several files, and we'll do this with touch command. Let's create file 1.txt, file 2.txt, and file 3.txt. Now let's set permissions, and we'll do this with change mode command, and we'll set 644 to on file 1.txt, and we'll set 755 on file 2.txt. The next block will be to display file permissions, and we'll do this with ls-l command. And let's add some echo string here. We'll edit file permissions, and that'll be followed by ls-l command. The next block will be, let's say, to copy a file. We'll use cp command and we'll copy file 2.txt to alt underscore file 2.txt. The next block will be, let's say, to modify .bashrc file to always add the alias. and we'll use echo command again with the following line: alias list, that'll be the command for the list alias ls-la. Let's close the command and close the string, and we'll append it with two greater than characters, two tilde, that is our home directory, and dot bash rc file. And let's add another echo command, alias list. Actually, let's start it with the uppercase A. Alias list added to dot bash rc dot please run source, followed by tilde slash dot bash rc, we'll close single quotes, to apply changes. Close the string, echo string, and go to the next block, which is, let's say, display final directory structure. And again, we'll use echo to add some informational message like final directory structure, and we'll use ls-uppercase R followed by two dots. And now let's return to the original directory with ls command and followed by two dots. Sorry, not ls, but cd command. And the next block will be the final block, where we'll be displaying the script stats, statistics. And we'll have lots of echo commands here. So let me type echo, double quotes, and hit Y twice, and insert several echo blocks here. Now I'll go to the first echo command, go to this opening double quotes, and hit A to append. And we'll add some string, script, execution, summary, colon. The next one will be number of arguments passed, and we'll use $hash here. The next line will be all arguments passed, and we'll use $at character. The next line will be exit status of last command, and we'll use $question mark here. And finally, let's add an empty line here and add script completed. I guess that's it. Let's save this script, add execution permission with change mode command plus X and the script name, and try to run the script with dot slash and the script name. And as you can see, we get current date and time. Now we have to enter our name. Let me add my name, and then the script runs successfully. We get hello with welcome to the file operations script. Oops, I guess that's not successful. You cannot access file.txt, not such file at directory. Let me double check it. I'll reopen the file, script file with Vim editor, go up, scroll up, and as you can see, I've made a typo here with change mode command with 755 permission. I need to append here file2, not file. But again, save the changes, clear the screen, and rerun the script, enter my name. Now the script runs without any errors. It reveals file permissions. Now it prints out ls list added to bash rc file, runs source command to apply the changes, and it prints out final directory structure. And also it prints out script execution summary, number of arguments, all arguments passed, exit status of last command 0, and script completed. So what we've done here, we've used special variables, $0, which holds the name of the script, and some more like $question mark. This gives the exit status of the last command executed. These variables allow our scripts to be more flexible and informative. We've used command substitution here. The syntax is $, parentheses, and command inside of the parentheses. We've used lots of echo commands. We've used date and read command, the read command to get input from the user. We've used timestamps and file permissions, changing with change mode to set specific permissions to our files. We've used 644 permissions, meaning read and write for the owner, read only for everyone else. And 755 adds execution permission for the owner. We've modified .bashrc file, and we've used to greater than character, that's the operator to append to the text file to the end of the file. So this script demonstrates how we can combine various bash features to create a more powerful and flexible tool. We've introduced concepts like special variables, command substitution, user input, timestamps, file permissions, and even basic configuration file manipulation. In our next lesson, we'll start exploring control structures like if-else statements and loops, which will allow us to create even more sophisticated scripts. I'll see you there. Welcome back. Today we are diving into Lesson 7, Conditional Statements in Bash. This is an exciting lesson because it's where our scripts start to get smart. They can now make decisions based on different conditions. In this lesson, we'll walk through the concept of conditional statements, focusing on if statements in Bash. We'll start with the basics and gradually move to more complex examples. We'll cover the basic structure of an if statement, how to add else clause to handle alternative cases, different types of conditions we can check in Bash, how to use elif to manipulate conditions, and combining conditions using and or operator. Throughout the lesson, we'll look at practical examples that demonstrate these concepts. We'll write scripts that check for the existence of files, compare numbers, and even create a simple age checker. As always, I encourage you to follow along on your own computer. Type out the scripts, run them, and see what happens. Don't be afraid to experiment. Try changing the conditions or the messages printed, and see how it affects the script's behavior. Remember, conditional statements are all about making decisions, and after this lesson, your scripts will be able to adapt and respond to different situations, making them much more powerful and flexible. So let's start with one of the most fundamental concepts in programming, conditional statement. In Bash, this primarily means working with if statement. These powerful tools allow your scripts to make decisions and behave differently based on various conditions. Now, what are conditional statements? Imagine you're giving instructions to a friend about what to wear. You might say something like, if it's raining, bring an umbrella. That's a conditional statement in everyday life. In programming, conditional statements work the same way. They allow a program to execute different code based on whether a condition is true or false. In Bash, the primary tool for this is the if statement. Let's take a look at the basic structure of if statement in Bash. Let me list my current directory and create a new file that will be 7, name it if statement script1.sh. And I've made a typo here, let's replace D with S. So the basic structure of if statement is as follows. If followed by, let's make a space here, followed by condition, then, and here we'll need code to execute if the condition is true. And we close the statement with fi. So here the statement starts with if, then the condition is enclosed in square brackets, then indicates the beginning of the code to execute if the condition is true. And fi which is if spelled backwards, marks the end of the if statement. Let's close this file and create a new one. Name it 8 if statement script2.sh, and we'll start with shebang bin bash. Now we'll start with if space square brackets. Let's make a space here, -f parameter, and we'll add a file name which is example.txt. Now we'll hit enter, then hit enter again, and add echo line here. The file example.txt exists, and we'll close it with fi state. Save the file, change mod +x, f8 if statement script2, and let's run the script with / and the script name, and we get an error, line 3, missing on line 3. Let's reopen this file, go to the line 3, and if we go to the end of the line, we can notice that there is no space after example.txt and before closing square bracket. Let's add it. I'll hit A to append and add a space here. Now let's save the file and rerun it. Now the script runs successful, without errors. Let me reopen this file once more to demonstrate you the importance of these spaces. So this line starts with if statement, and it checks if example.txt is a regular file. Now in bash, opening square bracket is actually a command. It's a synonym for the test command. And closing square bracket is its final argument. The space is necessary to separate the command and its arguments. So remember to put spaces after the opening square bracket and closing square bracket. Let me close the script, clear the screen, and we move on. So in previous example with -f example.txt, with this condition, we've checked if example.txt is a regular file. And if the file exists, the script will print the file example.txt exists. Let me type cat command and demonstrate the script. So if this file exists, bash will print out the file example.txt exists. And if file doesn't exist, the script will do nothing. So that's why if we run this script, we see nothing. Now let's add an else clause to our script. Often we want to do something if the condition is false. That's where the else clause comes in. So let me copy this script 8 to the script 9. We'll replace 2 to 3 and 8 to 9. And open script 9 to modify it a bit. So we'll need to add else clause after this then clause. I'll hit I to enter insert mode, and we'll add another condition here, else. Let me go ahead and copy this line, enter insert mode again. Now we'll need to insert the line first. Now we'll enter insert mode and perform this action. Echo the file example.txt does not exist. And we close it with fi command, right q. Let's run this command with /9 if statement script 3, enter, and we get the result. The file example.txt does not exist. Now, bash provides many ways to test conditions. Let's take a look at some of common ones. Let me create 10.conditions in bash file, open it with vim, and we'll note some of the conditions. First, there are file tests, -f, and the file that's true if the file exists and is a regular file. Then we can test -d file. Let me copy previous line and insert it here, and I'll remove this part. So true if the file exists. Oops, I've made a typo here. Let's add space. And I'll exit insert mode and press WD to delete the file. And is a directory. Let's insert another line here. The third is -r file. It's true if the file exists and it's readable. Now we can check strings. So I'll add a command here, string test -z or z followed by string true if string is empty. Let's copy this line, insert another one, and that'll be -n followed by string true if string is not empty. Now, another test is string equals string. That's true if the strings are equal. And we'll copy this line, insert it below, and if we add exclamation mark here, and by the way, we'll need spaces after string and before the next string, and here we'll add spaces as well. So string exclamation point equals string true if the strings and strings are not equal. And finally, numeric comparisons. Here we get num1 eq, meaning equaling, and we'll need a dash before eq, then space num2. That'll be true if the numbers are equal. We'll copy this line, and if we replace eq to ne, not equal, that's true if the numbers are not equal. Then let's insert two more lines, and the third line will be num1, and we'll replace eq to lt less than now num2. And it will be true if the num1 is less than num2. Let's remove this line with dd command, copy this line, insert it, and the third condition is num1, and we'll replace lt to gt greater than num2. True if num1 is greater than num2. So that's how we compare and test different data types like files, strings, and numeric comparisons. Let's save this file and create a new file. We'll name it conditions in bash.shell, and let's replace temp to 11, hit enter, and create some simple file with conditions. As usual, we'll start it with bin bash shebang, and the first line will be echo, enter a number, then we'll add read command, followed by number variable, and we'll add if statement, open square bracket, add space, use the number variable, then compare it. For example, greater than 0. Add a space here and close square bracket. Hit enter and add then keyword. Hit enter again. So what we'll do? We'll print out with echo number variable is positive. Place a dot here and close double quotes. And we'll add a if statement. So if that's not true, we'll add another condition. Number less than 0 space close square bracket, and again, then hit enter, echo number is negative. Don't forget about dots. And finally, else, what if it's 0? Echo number is 0. and close the structure with F5. Let's save this file, change mod +X file 11, conditions in bash, and run this file with /file11. So let's enter -1, for instance, and we get an error when we enter a negative number. This problem occurs because of how bash handles variables that might be empty or contain special character. So when we enter -1, the number variable contains a negative number. And in the if statement, where we get number less than 0, if number variable is not quoted and starts with a minus sign, bash interprets it as an option to the opening square bracket command, not as a number to compare. And this causes the error message, and the script continues to the else block, incorrectly reporting that -1 is 0. So let's reopen the file and take a look what we can correct in this script. Now let's try to place number variable here into double quotes, and we'll place number, by the way, I've made a typo here, in elif statement in double quotes as well. And I've made a typo here. So this key change, quoting the number variable, and it tells bash to treat the entire contents of number as a single item, even if it starts with a minus sign or contains space. Let's save this change and try to rerun this script 11 and try to enter -1 again. Now we get -1 is negative. If we rerun it again and type in number 3, that is positive. And if we rerun it again and type 0, 0 is 0. Now the script behaves as planned. So this script asks the user to enter a number, checks if the number is greater than 0. If it is, it prints the number is positive. It's less, it prints the number is negative. And if it's neither greater than nor less than 0, it must be 0, so it prints that information. Also, please notice that we reopen this file, this elif statement, keyword. This is short for else if and allows us to check multiple conditions in sequence, like in this case. First, we check if the number is greater than 0, condition 1, elif, else if the number is less than 0, condition 2. Let's close this file, clear the screen, and create one more script, the final script for this lesson, where we'll be combining conditions. So let me find this command and name it 12 and add combining conditions in bash. Open it with vim, add shebang bin bash, and this time let's check the age of a user. So we'll start with echo, enter your age string. Then again we'll use read command and we'll be reading age variable. Now if we'll add square brackets, so if variable age greater than 18, don't forget about space before closing square bracket. Now we'll add one more space and we'll add such a construction, means add end. And now we'll check for age again. We'll add age variable again and compare it to less than, for instance, 65. Add space here. Then enter echo, for example, you are in working age. Better to say you are of working age. Else echo, you are either too young or of retirement age. And we finish it with F5 keyword. So in this script, we need to check multiple conditions at once. And we can do this with and, this double ampersand character That's for AND. Both conditions must be true. And we can also use OR. At least one condition must be true. That's double vertical line. Let's save this script and change mod plus X, and we'll run this script and enter the age. For instance, 12. You're either too young or of retirement age. Let's rerun it and enter 66. You're either too young or retirement age. And we'll rerun it the third time and enter 21. You're of working age. Now to wrap up, conditional statements are a powerful tool in Bash script. They allow your script to make decisions and respond dynamically to different situations. If statement allows us to execute code based on whether a condition is true or false. We can use else to specify what to do when the condition is false. Elif allows us to check multiple conditions in sequence. And Bash also provides many ways to test conditions, including file tests, string tests, and numeric comparison. And we can also combine conditions using AND, which is double ampersand, and OR, which is double vertical lines character. Now, to practice, write some scripts that use different types of conditions and experiment with combining them in various ways. In our next lesson, we'll explore loops, which allow us to repeat actions in our scripts. Until then, happy script! Welcome back, everyone. In this lesson, we'll be focusing on loops in Bash. This is an exciting topic because loops allow our scripts to perform repetitive tasks efficiently, saving us time and making our scripts much more powerful. We'll cover three main types of loops: for loops, while loops, and until loops. We'll start with the basics and gradually move to more complex examples. Here is what we'll cover: the basic structure and usage of for loops, how to use while loops for condition-based repetition, the less common but useful until loop. We'll cover loop control with break and continue, nested loops for more complex operations, and we'll take a look at practical example of using loops for process in files. Throughout the lesson, we'll look at practical examples that demonstrate these concepts. We'll write scripts that count, process lists, and even handle files. As always, I encourage you to follow along on your own computer. Type out the scripts, run them, and see what happens. Now, remember, loops are all about repeating action. And after this lesson, your scripts will be able to perform tasks repeatedly without you having to write the same code over and over again. And this is a big step towards writing more efficient and powerful scripts. So let's get started. What are loops? Imagine you're at a party and you need to give a party hat to each of your 20 friends. You could write out, give a party hat to a friend 1, give a party hat to friend 2, and so on, 20 times. Or you could just say, for each friend, give them a party hat. That's essentially what a loop does in programming. It allows you to perform a set of actions repeatedly without having to write out the same code over and over again. In Bash, we have three main types of loops: for loops, while loops, and until loops. Let's explore each of these in turn. The for loop. The for loop is used when you want to perform an action a specific number of times, or for each item in a list. Let's take a look at the basic structure of for loop. I'll cd to scripts. Oops, I'm not connected to my testing VM, so let me connect to it. And cd to scripts folder. Let's list its contents, and we can create script 13 loops underscore for loop structure. So the structure of for loop is as follows. We've got for keyword, followed by, for instance, some variable in list. Then we have do keyword, and in this block we'll have commands to be executed, and we close it with done keyword. So that's the basic structure of for loop. Now let's take a look at a simple example. I'll create file 14, and that'll be for loop example1, and let's rename it to 14, add shebang bin bash, and start our script. For color in red, let's say blue, yellow, green, do, not go, but do, and we'll echo my favorite color is color variable, and we'll close double quotes, and finish this structure with done command, keyword. Okay, let's save this file, give it execution permission, and run it with dot and script 14. As you can see, it has printed out the phrase my favorite color is 4 times, 1 time for each color, with the variable color taken on each value in turn. We can use for loops with number range. Let's create another example, example 2, starting with bin bash, and we'll start with for keyword, let's say number in, and use curly braces here, let's say from 1 to 5, do, and we need to specify what to do. Again, echo number, and we'll use number variable, and that's it. Such a simple example. Finished with done. Save the file, and by the way, we need to name it example 15, not 14, so let's move this example 14 to, again, 14 example 2, but we'll need to rename it 15. Now let's change mod plus x to example 15, ls, here it is, and run this example with previous command. This one, that'll be example 2, and rename it to 15. The output is number printed 5 times, from 1 to 5. So, in this example, we've counted from 1 to 5, and we've used curly braces to specify the range. Now, the while loop continues to execute as long as a given condition is true. Let's create a file for while loop structure. I'll type vim 16.loops while loops loop structure. And the structure is as follows. We have while keyword, then in square brackets, opening square bracket followed by space, then follows condition, space, closing square bracket. Then again, we've got do keyword, and again, commands to be executed, and done keyword. That's the basic structure of while loop. Let's save this file and create an example that will be example 17, and we'll rename it while loop example 1. Hit I to insert mode, add bin bash shebang, and start with while keyword. Actually, let's add a variable first. For instance, count equals 1. While we open square bracket, add space, add variable count, less than 5. Again, we'll add a space here and close square bracket. Then new line, do, and what we need to do is echo, let's say count is, and we'll use count variable, close double quote, and we'll add one more variable count, dollar, braces, parentheses, and one more, and inside of this parenthesis, count plus 1, and we'll add a space plus 1 before 1. That's it. We'll finish it with done keyword and save. again change mode plus X 17 and run the example number 17. As you can see, the script worked fine and it counted from 1 till 5. So the loop continues as long as count is less than or equal to 5. Another type of loop is until loop. The until loop is similar to the while loop, but it continues to execute as long as a given condition is false. Let's take a look at its structure. And again, I'll create a file for until loop. So let's rename it to example 18 loops, and we'll replace while with until loop, and we'll replace example with structure. Okay, and the structure is as follows. Until, followed by square brackets, and we'll add space here. Here comes some condition, a space again. Again, we'll use do keyword, and here commands to be executed, and done keyword. That's the basic structure of until loop. I'll save the file, clear the screen, and for the example, we could copy the previous example, which was example 17. So let me copy 17 example 1 to, I'll use the same name and rename it. So that will be example 1, but the example purpose is until loop, and that will be, the number will be 19. Let's open it with Vim, example 19, until loop, example 1. And we'll change here less or equal to greater or equal 5. Not equal, but then, greater than 5. Let's save this example and take a look what happens when we run it. Example 19. Let's double check it. Everything is correct. And let me reopen this file once more. And of course, what I've forgotten to change in the previous example is this while keyword. So let me append here and remove while and replace it with until. So that's how you troubleshoot. Please remember that every keyword and every symbol is correct in your script in case it doesn't perform as expected. So let's save it and rerun it, and that'll count till 5 again. What the script does, it does the same thing as while loop example, previous example, but the condition is reversed. The loop continues until count is greater than 5. Now let's switch to loop control, break and continue keywords, because sometimes you might want to exit a loop early or skip the rest of the current iteration. That's where break and continue come in. Break immediately exits and continue skips the rest of the current iteration and moves to the next one. Let's take a look at an example using both. So again, I'll create script 20, loops, loop control, example 1, .sh. By the way, you don't need to specify this .sh ending or extension. That's only for your convenience. If you want to see that it's a shell script and when you list the files, you can specify .sh. So let's go ahead and create this file, add shebang, and we'll start it with 4 number in, let's say, we'll use curly braces here from 1 to 10, do, and we'll do the following. If starting the square brackets, add space, number equal to 3, again we'll add a space here, then continue, and that'll skip the rest of iteration, not iteration, sorry, but iteration, and we'll need 1 arc. And now we'll need to close this block with fi keyword and start the second block. Let's add a space here, blank space, and start with if again. Again, we'll add square brackets, add a space, number equal 8, and what we'll do then, break, and that will exit the loop entirely. Again, we'll close it with fi keyword, and finally we'll echo number is number, and finish this for loop with done keyword. Let's save it, and we'll change mod +x on this and run it with /. And as you can see, we've got something missing here on line 10. Let's reopen the previous file. First off, I'll add M letter here. Number is number. And again, I forgot to add a space here after 8, so don't forget about this space. Right Q, clear the screen and rerun the previous command. Now it's performing as expected. So the script is printing numbers from 1 to 7, skipping 3. Now, you can also put loops inside other loops. These are called nested loops. Let's take a look at an simple example of nested loops. So let me create a file for it. That will be example 25, loops, loop, nested, example 1. As usual, I'll start it with shebang, bin bash, not that one, but bash. And let's start it with 4. Let's say I in from 1 to 3, do. And now the nested loop in it for j in, let's say, from 1 to 3, do. Echo I is I variable and j is j variable. And we'll need to add 2 more dones, done again. So that's how we use nested loops. Let's save this file and add some execution permissions to it with change mod +x and run it with /. Now, as you can see, this prints out all combinations of I and j from 1 to 3. And sometimes that could be very convenient and save you much time and effort if you do this manually. And finally, let's take a look at some simple practical example with processing files. Let's put our loop knowledge to use with a practical example, and here is a script that processes all .txt files in a directory. I'll clear the screen and list the contents of this directory, and that will be example 22, loops, practical example 1.sh. Again, we'll add bin bash, and let's start it with for loop. Let's say file in all .txt files, do, and we'll add if condition, if, and it is followed by square brackets. Again, we'll add a space here. We'll check if it's file, and we'll use file variable, add a space here, then echo processing file. And here you could add commands to actually process the file. Now, but we'll finish this script with fi. Let's delete this space, and done. I'll save the file, change the permission, misspelled change mode, correct it, and run the script. It doesn't find any txt files here. Let's create with touch command file1.txt and file2.txt. Rerun the script. Now it found 2 files, file 1 and file 2. And if we want to go further, we could do some actions really with these files, add some commands to really process these files. For example, rename them or archive them or move to some other directory and so on. So to wrap up, loops are a powerful tool in your bash scripting toolkit. They allow you to automate repetitive tasks, process lists of items, and create more complex and efficient scripts. The for loops are great for iterating over lists or ranges. While loops continue as long as a condition is true. Until loops continue as long as a condition is false. And you can use break and continue, which give you more control within your loops. And you can also nest loops for more complex operations. Now, try writing some scripts that use different types of loops and experiment with combining them with the conditional statements we learned in the previous lesson. In our next lesson, we'll explore bash functions, which allow us to create reusable blocks of code in our script. In this video, we are going to dive into a hands-on lab where we'll create a Linux system administration interactive menu script. This is an exciting opportunity to apply our bash scripting skills on real-world system administration tasks. So we'll go step by step in creating a script with a menu-driven interface. For various tasks, we'll start with a basic menu and gradually enhance it, adding more features and complexity. Here is what we'll cover. We'll first set up the basic structure of our script, then create a menu loop to keep our menu running, implement different actions for each menu option, and add user interface and making decisions based on that input. Then we'll enhance our script with additional features like a screen clear option and a simple game. Throughout the lab, I encourage you to follow along on your own computer. You can also type out the code, run it, and see what happens. Don't be afraid to experiment. Try adding your own menu options or modifying the existing one. Remember that this is hands-on lab, so it's okay if things don't work perfectly the first time. Debugging and problem solving are important skills for any programmer. If you run into issues, try to figure out what's going wrong. And of course, if you need help, don't hesitate to ask. So by the end of this lab, you'll have created a fully functional interactive menu script. This is something that you could potentially use as a starting point for your own projects or scripts in the future. Now let's start with step 1, setting up the script. I'll log into my testing server and cd to scripts directory, list it, and we'll create script number 23 and name it menu_script.sh. We'll add shib1 with bin bash and an extra empty line. And let's type some welcoming message. For example, welcome to the interactive menu script. And by the way, let's experiment with appearance once more. Now let's type some more lines and then experiment with appearance. So we'll hit enter here and add a command. You know how to add a command. We started with hash. And for example, we'll add, and I've missed, we will add our menu code here. Now let's continue with step 2 and create the main loop. We want our menu to keep appearing until the user chooses to exit. For this, we'll use a while loop. So let's add the following code to our script. While true, do echo please choose an option. Now let's experiment with appearance a bit more and take a look what's better to read from the screen. Let's try dark. That's a bit hard to read. Light and white. I'm not sure. If I had your feedback, what's better to read? Let's try light once more. I guess light is good, but it doesn't select these keywords. And black selects the keywords with yellow. So I guess the best choice is black. And we'll continue with black, I guess. Okay, let's add another echo command. and we'll add option 1. Please better say hello. That will be option 1. We'll add another echo, and let's copy this line and insert some more echoes. So option 2 will be, and we don't need the space, let's check the date. Option 3 will be list files, and option 4 will be exit. We don't need this one, so we'll delete it with pressing D twice. Now we'll use read command with -p parameter and enter your choice from 1 to 4. Close the string followed by choice variable. Okay, let's write to this file to save the changes. Now let's add some actions for each menu option using a case statement. And we'll start it with case keyword, and we'll use choice variable in the following cases. 1. Echo. Let me hit enter several times to scroll up. So echo, hello, there, nice to meet. That'll be case 1. And we finish case 1 with double semicolons and switch to case 2. So case 2 will be echo, and we need to output the screen. Today's date is, and we'll use date command to get today's date. We'll finish it again and start case 3. Again, echo, and now we need to find out the files in the current directory. So the files in the current directory are, close the screen and end the case. And finally case 4, echo, and thank you for using interactive menu. Let it be the name. So we'll change interactive with uppercase, menu with upper script, and we don't need this W. Again, we'll end it with double semicolon. And by the way, what I've forgotten in case 3 is to add a command, and that'll be ls-l command. Now let's save script with W command, and we need to close the case with case keyword, but spelled reversely. That is ESAC. And let's add one more command, echo, and actually we'll use just echo. This just prints a blank line for better readability. Okay, let's save and quit the script, change its mode, change mode command +X, and run it and see what happens. Yes, we don't need this space here. Welcome to the interactive menu script. Menu is spelled incorrectly, and we need to correct it. So let's move menu script to 23 and we'll spell it correctly. Okay. Now let's refer to this error, line 50, syntax error, unexpected end of file. Okay. Let's add some string to this end of file. And to go to the end of file, we press Shift G. So that'll be uppercase G. Now let's add some text to echo. I'll hit A to append, double quotes, and space. Right Q. Rerun this script, but menu correctly spelled. Again, syntax error, unexpected end of file. Let's reopen it. And of course, if we take a look at our script, what we forgot to add here is done closing statement. So let's place it here and save the script and rerun it. Now our menu is working fine, and we can read welcome to the interactive menu script. By the way, we need to correct menu again. Please choose an option let's choose option 3, for example, and it lists the files, and we can choose option 4, but for now it doesn't exit the script. So let me press Ctrl+C to break it and reopen the script and continue working on it. First we'll check all menu words, so I've spelled it incorrectly. Let's search for menu. For this I'll press / and type MA. As you can see, for now it has found 2 words with MA. So let's correct this one, menu, and this one. And we continue working on our script. So I've scrolled down. Let's enhance our script. We'll add a clear screen option and implement a guess the number game. So let me go up here, check the date, and we'll insert, actually let's insert it here, echo 4.clear the screen, and that'll be 6, echo 5.play, guess the number, and 6 will be to exit the script. Now we'll need to modify this enter your choice from 1 to 6. Let's save the file and add 2 more blocks, 4 and 5, for clearing the screen and the guess the number game. So for this we'll go down here, change 4 to 6, enter several times, add choice 4, echo green cleared, and we'll need to add a command before echo, so we'll type clear, and also we'll put it 1 level down, and we'll add double semicolon to finish this case. We'll start case 5, actually we don't need this line, so case 5, hit enter, and we'll add secret number variable, that'll be dollar, parentheses, 1 more parenthesis, and let's use random. Seems like Vim is not working correctly. I can see that some words are missing. Let me save the changes and reopen it, and if it doesn't fix the problem, I'll try to fix it with restart, I guess, this one. So we continue with, yes, it doesn't fix. Let me change the appearance. Dark is okay. Now we can continue random, and we'll need a space here, and we need a space before random, then %10 plus 1, and again we'll add a space here, and add an echo line here. Echo, I am thinking, we don't need this O, over a number between 1 and 10. Now let's add a while loop here. So we'll add while, and by the way it should be on the same level as echo, while true, do, read, -p, your guess, and question mark, close double quotes, and followed by guess variable. Enter. Now if, and we start the construction with square brackets, and we'll add a space here. Now in double quotes, guess variable equals to what? To a secret number variable, or secret number variable, and we'll add a space here again. Finish this line with semicolon, and then keyword. And that'll be echo congratulations, exclamation point. You guessed it. Close the screen and break keyword. Otherwise, not otherwise, but well, let's add another condition with elif statement. Actually, let me copy this one and insert it here. So I'll hit A to append and elif guess variable, and we'll use less than comparison secret number, then enter echo too low. try again, and let's add a dot here. And finally, else, again, echo to hide. Try again. Let's add exclamation point here as well. And we'll finish the statement with fi keyword and done. Then what else we need to add? We need to add double semicolon. That was choice 5, this guess the number game, and choice 6 was to exit the script. Echo, thank you for using interactive menu, and we'll need to add a command here, which is exit 0 to exit, right? Also, let's finish this case construction with ESA case reversed, and we'll finish the cases here with asterisk and closing parentheses. Then let's place case on another level like this and echo on this level as well. And we'll also add an echo statement here as well with invalid option. So all other cases, that is asterisk, will be invalid option. Please choose a number between 1 and 6. Close double quotes. And what else we need? We'll need this double semicolon. Now the blank line is still here and done keyword is still here. Okay, that's it. Let's try to run this code. I'll exit it, clear the screen, and try to run it. Now we've got several errors, line 42 and line 79. Let's reopen it. Let's find line 32. Yes, I've exited. No, it was line 42 and 79. Clear the screen. 42, 79. So let's find 40. Elif statement. Let's check it. Yes, we've got single quote here instead of double quote. And let's find 79. That's just the blank line. So let's delete all these lines and save the script, clear the screen, and rerun it. Now I've reviewed this script, and by the way, I've made a copy of the script with menu_script added. And let's take a look. It's now working. Let me first exit it and reopen this script. So I've corrected the indentation for better readability and add several typos here. So let's take a look at the final version of the script. We started with shebang, then echo here. And by the way, let me change it to black. While true, do echo and all the choices. Then we read this choice variable, read from the user's input, and then we start case block with choice variable in it. The first part of the block is just to greet the user, then to output the date, the files in the directory, clear the screen, and here comes the guess number game. Again, let's change the appearance to be white. We are using random function here, and then while loop, here it is. While true, do read what's your guess. Then if statement, if it's equal to secret number, congratulations, you guessed it, and break this while loop. Another option, if it's less than, echo to low. Then else, echo to high. Close while loop with fi, close if statement with fi, and close while loop with done. And the sixth option is to exit from the script. And the last option is invalid option. Please choose a number between 1 and 6. We finish the case and print. Let's get back to black because it's output incorrectly. And then we finish the whole script with done. Now let's run the script. I'll write Q and clear the screen and run it. Now as we can see, it's working fine. We can choose option 5, for example, and select 3, too high, select 2, too high, select 1. Congratulations, you guessed it. Now, let's check the date. It's working fine. Clear the screen, and finally exit. We'll select 6 to exit. Now, to wrap up, first off, congratulations, you've created an interactive menu script that presents a list of options to the user, performs different actions based on user input, includes a simple game, and continues running until the user chooses to exit. This script demonstrates several important Bash concepts: while loops for continuous execution, case statements for menu options, reading user input, conditional statements, command substitution, and arithmetic operations in the number guessing game. You can further enhance this script, and here are some ideas for you. For example, you could add error checking for user inputs. You could implement more complex actions for each menu option. And you could add color to your menu using ANSI escape codes. Next up, we'll be writing similar script with hands-on lab, but that'll be more Linux administration related interactive menu script. Welcome back, everyone. Today we're diving into a hands-on lab where we'll create a Linux system administration interactive menu script, and this is an exciting opportunity to apply our Bash scripting skills to real-world system administration tasks. That'll be a script with a menu-driven interface for various system administration tasks. And of course, you can extend it for your needs. And we'll start with basic system checks and gradually add more complex operations. Here is what we'll cover. First, we'll set up the basic structure of our script. Then we'll create a menu loop to keep our menu running. Then we'll implement different system administration tasks for each menu option and add user input and performing tasks based on that input. And finally, we'll enhance our script with additional features like checking system load and searching for large files. Throughout the lab, I encourage you to follow along on your own Linux system. Type out the code, run it, and see what happens. Also remember, this is a hands-on lab, so it's okay if things don't work perfectly the first time. Debugging and problem solving are crucial skills for both programmers and system administrators. And we start. So the objective is to create a script that presents a menu of common system administration tasks and performs these tasks based on the user's choice, and continues to run until the user chooses to exit. This script could be a handy tool for any system Linux administrator. So we'll start by creating a new file called, let's say, sysadmin_menu. Let me check the files in this directory, and we'll create file 24 and name it sysadmin_menu.sh. We'll add shebang as usual, which is bin bash, and we'll add welcoming message with echo command. Welcome to the Linux system administration menu. And let's add an exclamation point, hit enter several times. Now we want our menu to keep appearing until the user chooses to exit. We'll use a while loop for this and add the following code to our script. We'll add while true, do, echo, and we'll add several echo lines. So I'll copy it with $Y and insert several lines. Go back to the first one, hit A to append, and the first line will be please choose an option. The second line will be option 1, and we'll check for, let's delete 4, check system uptime. Then option 2, view disk usage. Option 3 will be list top CPU dash consuming processes. Option 4 will be check available memory. Option 5, view system logs. And finally, let me insert one more line here. Finally, option 6, exit. So that's the first block. And we also need to add read command -p, enter your choice from 1 to 6. Add a space here, close double quotes, and we'll use choice variable as we've done in previous example. And we need to spell choice correctly. Okay, now let's add some actions for each menu option using a case statement, right? Like in previous example. So we'll add case followed by choice and option 1, echo system uptime is, and we'll add uptime command and close this case with double semicolon and add case 2, again echo. By the way, please note the indentation here. So we hit enter after the number of keys and Vim automatically indent as needed. So case 2 will be echo disk usage, and the command for this is df-h, human readable format. Again, we'll close this case and start a new one. Now we'll echo top CPU dash usage processes colon, and the command for it is ps aux. Now let's sort them, and we'll sort by %CPU, and we'll need to add dash here and pipe it to add dash n, let's say 6. And again we'll close this case and start case 4, echo available memory, and we'll run free command -h, human readable format, close the case 5, and finally echo, and we'll read last, let's say 10 lines of system log, and for this we'll use sudo with tail command, and we'll be reading var log this log file. Again, let's end this case, start case 6, and let's add several more options. We'll change the first menu as well. So echo system load average, and we'll output with cat -proc -load avg. Again, we'll close this case, start case 7, echo. Actually, we won't start it with echo. Let's start with read -p, enter the directory with search. Again, let's copy this read -p, insert several times. Actually, we'll need only one time. We'll delete this one, and we'll delete this 3 words. Enter the minimum file size, and now we'll insert echo command, echo searching for the files larger than. Let's add a variable here, for example min_size. Let me make the font size smaller, min size, and we'll be using megabytes for it in, and we'll add another variable and name it search_dir, and let's add 3 dots before closing the string. Okay, that will be first echo message, followed by the command itself, sudo, and we'll use find command, in double quotes, the variable search_dir. Then we'll be looking for the type, file and size plus, and again in double quotes, variable in curly braces, min underscore size. We'll close double quotes and use megabytes, and then execute the following command: ls -lh followed by curly braces, empty curly braces, and that will finish this command and start searching from root directory. And let's pipe it to sort-e5 and rh. Again, I'll make it font size a bit smaller. Let's check it. So searching for the larger files larger than minimum size, and we'll need curly braces here, and megabytes in storage dir. We'll need curly braces here as well. You do find storage dir, type F, size, minimum size, in curly braces. Okay, let's continue. Actually, we'll add one more case. That will be case 8. And by the way, what I've forgotten here is to close the previous case. Okay, now we'll add case 8, and actually not 8, but for all other. So we'll use asterisk here, and we'll type echo. Oh, actually, we need a case to exit from this script. So that will be case 8, and that will be echo, and thank you for using enhanced Linux system administration menu. Goodbye. And we'll add a command, exit 0, and also close this case. Now we'll add all other cases, choices, and we'll use echo invalid option. Please choose a number between 1 and 8. And by the way, I've skipped 8 here, so let me rename it. That will be case 8. And we'll add a dot here and close the case. And add ESAC, closing keyword. Add echo, and for a blank line, and one more echo. Actually, let's skip this echo and add read command with -p option. Please press enter to continue. And let's add 3 dots here, readability, and finally add done keyword. Okay, I hope this script doesn't contain any typos or errors. Let's save it and change mod plus x will be 24, right? Sysadmin underscore menu sh, and run this script 24. And as you can see, it works fine, just fine. Check system uptime. Okay, let's start with option 1. Invalid option between a number 1 and 8. Okay, number 1 doesn't work. Let's exit, clear the screen, and rerun it, and try number 2. Invalid option. Please choose a number between 1 and 8. Okay, I guess our script doesn't work. Let's troubleshoot it. Open it once more and see what's happening here. Yes, I'm afraid I forgot to add some echo commands in the first block. So let's copy this echo command, and exit will be option 8. Let's replace it. I'll hit I to insert, delete, and add option 8. Now let me add one more echo command. Hit exit, copy this line, and insert some more. So option 5, view system logs. Yes, that's true. Option 6, system load average. So let's add option 6 here, insert 6, and we'll add check system load average. I will need P here, and option 7 is search for large files, and we don't need these lines. Let me delete them. Now we've got 8 options. Let's save the script and clear the screen and run it again. Let's check option 1, valid option. Okay, let's troubleshoot furthermore. First off, let's drag this one from 1 to 8, read-p, enter a choice variable, case, choice in. Okay, as you can see, I've forgotten to add $character to show the script that I'm using choice variable, not just a string. Let's save it, clear the screen, run it again, try option 1. Now it's working. As you can see, system uptime is 58 minutes, 1 user, load average, and so on. Let's press enter to continue. Let's view disk usage. I'll hit option 2, and we get an output with disk usage. Let's press enter to continue and select option 3, and we get 3, not 3, but top CPU consuming process. Press enter, select option 4, and we'll get available memory. Again, press enter, select 5, and we need to provide the password for sudo, and cannot open var log syslog. Maybe this file doesn't exist. I don't want to troubleshoot this option right now because the main thing that our script is working. Okay, let's continue with enter and select option 6, load average, and we get this information. Press enter, select option 7, search for large files. Let's enter our home directory, enter the minimum file size. Let's enter 1 megabyte. Invalid argument. Okay, something wrong with arguments, but this option is working, and we need to troubleshoot this defined command and its arguments. By the way, it could be your home task with this script. Please troubleshoot this find command used in option 7, and also you can troubleshoot the system logs command used in option 5. And finally, let's check if we can exit. I'll select option 8, and now we've exited our script. Thank you for using Enhanced Linux System Administration menu. Goodbye. So the core script functionality is working just fine. We need also troubleshoot the commands we've used in this script. And of course, we can extend the script to make some configuration changes in our system, like host name, IP address, and so on. Whatever we'd like to automate with this script, we can do this. Now let me reopen this script, and we'll wrap up here. So first off, congratulations, you've created a powerful Linux system administration tool that presents a list of common system administration tasks. It also performs the tasks based on user input. It includes advanced features like searching for large files, and it continues running until the user chooses to exit. The script demonstrates several important Bash and Linux system administration concepts. We've been using here while loops for continuous execution. We've used case statements for menu options. So here it is, case statement. Also, we've been reading user input in this script with read command, executing system commands from a script, using sudo for privileged operations, and file searching and sorting. Now, you can feel free to further enhance the script. And here is some ideas. First off, troubleshoot the commands we've used in this script. Then you can add error checking for user input, implement logging for actions performed, and include some network diagnostics option. So I hope it was informative, and I'd like to thank you for viewing. Next up, we'll be talking about functions in Bash. Until then, happy script. Welcome back, everyone. Today we're diving into lesson 10, functions in Bash. This is an exciting topic because functions are like building blocks that will allow us to create more complex and powerful scripts. In this lesson, we'll cover what functions are and why they are useful, how to define and call function in Bash. We'll be working with parameters in functions, returning values from functions, and using local variables in functions. And we'll take a look at best practices for when and how to use functions. Throughout the lesson, we'll look at practical examples that demonstrate this concept. We'll run them and see what happens. Don't be afraid to experiment. We'll write functions that greet users, perform calculations, and even create a small number guessing game. And as always, I encourage you to follow along on your own computer. So let's start. What is a function? Imagine you're baking cookies. Instead of writing out all the steps for mixing the dough every time you want to make cookies, you might have a recipe card that lists all the steps. And when you're writing out your baking plan, you can just write mix cookie dough and refer to that recipe card. In programming, a function is like that recipe card. It's a set of instructions that you can refer to by name whenever you need to perform those instructions. So let's take a look at basic function syntax. We'll name our file, let me change directory to scripts directory and list it, and we'll name our file 25.function_structure. And of course we need to use Vim. So here is the basic structure of a function in Bash. Let's break this down. It starts with function name. It's the name you give your function to your function. Choose a descriptive name that indicates what the function does. And then parentheses. After each function, you need to add parentheses. The parentheses are required after the function name, even if they are empty. And curly braces. Enclose the commands that make up your function in curly braces. So let's close this file and open the next file. I've pre-created part of it. It's script 26. Actually, I've pre-created the whole file. And as you can see, it starts with shebang. And what it does, when you run the script, it will print hello world to your screen. And again, we have the function's name, empty parentheses, opening curly braces, and the command itself, the function's body. And you also need to refer to this function, to call this function, to run it. And now I can note the error here, and if you noted it, it's good. So I've forgotten to add closing curly braces. Let me go down here, hit I, and add closing curly braces. And as you can see, Vim automatically highlights the structure. It highlights the opening curly braces and closing curly braces. And we can add an empty line here. And we can add an empty line here for better readability. Now let's save this file, clear the screen, and run this file. That was file 26, I guess. Yes, function example 1. Let's run it. And as you can see, we've successfully run function hello world. Greeting function. Let's double check its name, by the way, at 26. Yes, its name was say hello. So that's how you refer to the function. First you create a function, and then you have to call this function by typing its name. Now, of course, we can use functions with parameters. Functions become even more powerful when you can pass information to them. These pieces of information are called parameters or arguments. And let's take a look at how we can use parameters in a function. Let me create a new file. I'll copy the previous one, and we'll name it example2 and replace 6 with 7 and run it with Vim. Vim 27, tab to autocomplete, and let's rename this function, so that will be function name, let's say greet, and function body will be echo hello, and instead of word we'll use $1. Then we've got this closing curly braces, and we can call this function by typing greet and refer to the variable $1 that will be used as parameter Alice. Let's copy this line, paste it here, and we'll have the second parameter Bob. Let's save it, clear the screen, and run this 27 function example 2. Now, as you can see, we've called function twice and used it with parameters. This $1 refers to the first parameter passed to the function. And when we, let me cat this function, when we call the function here, we're referring to its name, and then we pass the parameter Alice to this function. So when we call greet Alice, comma, $1, inside the function will be Alice, and the output will be hello Alice and hello Bob. You can use $2 and $3 and so on to refer to the second, third, and subsequent parameter. Now we can return values from function. In Bash, functions don't return values in the same way as in the other programming languages. Instead, they can either use the echo command to output a result, set a global variable, or use the return command to return a status code where 0 for success, non-zero for failure. Let's create a new file that will be file 28, function return values example. I'll add shebang, and let's add this function add underscore numbers followed by parentheses, and then we add a space and add an opening curly brace and a function's body. Local sum equals dollar parentheses and one more parenthesis, and inside of this second parenthesis we'll add a command. First we need to add a space as usual, and then $1 space plus $2, and again we'll need to add a space here after $2, and let's echo this local functions command. Result will echo some variable, and on the next line we'll close curly braces to end the function's body, and then add an empty line and use result variable that will contain the next information, again in parentheses. And now we are using just variable add, not variable but function add numbers, and we pass numbers to these variables, 5 let's say, and 4. And the next line will be to echo, and here by the way not result but result, sorry for that typo. So we will output this result with echo command as the sum is and result variable. So we return value from our function to the result variable. Okay, let's save this, add X to file 28 and run this file 28, and the sum is 9. So that's how we return values from function. Let me output this script once more with cat, and we'll take a look at this script once more. So first we define a function here, which is add numbers, that takes two parameters and add them together. So this function takes these two parameters and add these two parameters. Next we use the local to declare sum as a local variable. So this local keyword declares that this sum is a local variable, local to this function. Then we use echo to output the result. And when we call the function, we capture its output using command substitution. Remember, this structure is named command substitution. And then we store it in result variable. Here it is. Now let me tell you some words about these local variables in function. By default, variables in Bash are global, meaning they can be accessed from anywhere in the script. However, it's often better to use local variables inside functions to avoid accidentally modifying variables used elsewhere in your script. And as you remember, we can create a local variable using the local keyword. Let's create one more example of using local keyword. So I'll create a new file that will be file number 29. Let's name it function local variable. And we'll add example. Add a shebang bin bash. Let's name it simply my_function. Again, we add parentheses and opening curly brace. And now we'll use this local keyword to refer to the next variable as local to this function variable. Let's name it also simply my_variable, and that'll contain the following information. I am local, such as string, and we'll print out it with echo and refer to this variable, so we'll add $my_variable, but I've missed I here, and we'll close this function with curly brace, add some space here. Now let's call this function. We'll type its name, my_function, and what will it do? It'll print I'm local. Let's add that. It'll print I'm local. Now, if we want to call this variable outside of this function, let's try to echo, and we'll try to refer to this variable outside of the function, and the function name is my variable, and instead of this double quotes, we'll use $, so we are calling this variable outside of the function. What will it do? So let's comment it. It'll do nothing, because my variable is local to the function. Okay, let's save it and change mode, file 29, and try to run file 29. So the output is as expected. First, we get I'm local because we are calling the function which contains local variable containing this string I'm local. Let me cat file 29. And the second echo command doesn't produce any result because we are calling my variable which is local to the function and can be called outside of the function. Okay, I'll clear the screen. I hope it's clear. So when to use function? Functions are great for coding when you need to use multiple times in your script. We can also break down complex tasks into smaller, manageable pieces. We can organize our code into logical sections by using functions. And we can create libraries to use commands that you can source in multiple scripts. Now let's create a more complex example that brings together several concepts we've learned. So let me create a file that will be file number 30, I guess. I'll type vim 30 function example 3. And again, we'll add bin bash here. So let's create a function to check if a number is even or odd. So first we'll add a command here, function to check if a number is even or odd. And we'll name this function check underscore even underscore odd. Again, we'll add parentheses and start the function's body with opening curly brace. Hit tab here to make it readable for better reading. So let's add some if statement here. If, again, we'll use double parentheses and a space inside of double parentheses. We'll refer to variable 1, which will represent the first positional parameter passed to this function. Then we'll use modulus operator, which is percent character. It calculates the remainder of the division of 1 by 2. So we'll add 2 here, and then equals sign character. It will check if the result of the modulus operation is equal to 0. So we'll add 0 here. Again, don't forget about space here, and semicolon. Space then, and what we'll do then, we'll echo space, and the first positional parameter is even. Else, echo the first positional parameter is odd. And we'll close this if statement with fi keyword. And what we need to do next, we'll need to close this function with closing curly brace. Now let's create a new function, and let's add a command what it will do. Function to generate a random number between 1 and 10. Again, we need to name this function. Let's name it generate random number, parenthesis, opening curly brace, and the function's body we'll use local keyword here and a variable random underscore none, which will contain the following: dollar, double parenthesis, and space inside of double parenthesis. Again, we'll use random Linux function or bash function, modulus operator, which is percent and 10 plus 1 space, and we'll echo the result of this, so that will be percent, not percent dollar, that's a variable, random underscore number. We'll close this function with closing curly brace, and next what we do? We'll add main script. Let me hit enter several times. So let's remove this add word and leave just main script. First we'll echo the following information: welcome to the number checker. And we'll use for structure for I in, not in, but I in the range between 1 and 5 in curly braces. So that's how we put the range between 1 and 5. And then we'll close the statement with semicolon and use do keyword. What will we do? We'll first declare a number variable, which will contain the following: dollar, again in parentheses, generate underscore random underscore number. And we'll declare the second variable, result, which will contain the following: again, dollar in parentheses, and we'll use check underscore even underscore odd. Is that correct? Let's check. Yes, the function is named check even odd, and we'll use a variable, previous variable number. And finally we'll echo, first we'll add some string, random number, colon, $I, colon, space, result, close double quotes. And now we are done, and add some echo line here as well. at the bottom of the script. Let's say, thanks for using the number checker. So that's it. Let's try to run this script. I'll save the file. Again, use change mod +X. That's file 30. And run this file. See what happens. Welcome to the number checker. Random number 1, 2 is even. Random number 2, 10 is even. Random number 3, 5 is odd, 3 is odd, 4 is even. And finally, thanks for using the number checker. Let's clear the screen, cat file 30, and take a look at what we've done. So this script defines two functions. Function check even odd, which determines if a number is even or odd, and function generate random number. Here it is. It creates a random number between 1 and 10. The main part of the script then uses these two functions in a loop. Let's take a look at this loop. Here it is, to generate and check 5 random numbers. And as you can see, it has run just as expected. Now, to wrap up, functions are a powerful tool in your Bash scripting toolkit. They allow you to organize your code into reusable blocks, make your script more readable and maintainable, reduce repetition in your code, and create libraries of useful commands. As you continue your Bash scripting learning path, you'll find that functions become an essential part of writing efficient and effective scripts. So practice creating and using functions in your scripts, and you'll soon see how they can make your life as a scripter much easier. In our next lesson, we'll explore how to handle errors and debug our Bash scripts. Until then, happy script. Welcome back, everyone. In this lesson, we are going to dive into error handling and debugging in Bash. This is a crucial topic that will take your scripting skills to the next level. We'll walk through various techniques for making our scripts more robust and easier to debug. We'll start with basic error handling and gradually move to more advanced techniques. Here is what we'll cover. Why error handling is important. Basic error handling techniques like checking exit statuses and advanced error handling with custom functions and traps. We'll also cover debugging techniques including verbose output and using the Bash debugger. Throughout the lesson, we'll look at practical examples that demonstrate this concept. We'll write scripts that handle errors gracefully and explore how to find and fix problems when they occur. And as always, I encourage you to follow along on your own lab environment. So why error handling matters? Imagine you are building a house. You wouldn't just focus on making it look nice, but also want to ensure that it can withstand storms, earthquakes, and other unexpected events. The same principle applies to our scripts. We need to prepare them for things that might go wrong. Error handling allows your scripts to detect when something has gone wrong, respond appropriately to errors, and provide useful information to the user or log file, and prevent cascading failures, where one error leads to many more. Now let's start with basic error handling in Bash. And the first error handling technique is checking exit status. In Bash, every command returns an exit status when it finishes executing. A status of 0 typically means success, while any other non-zero status indicates an error. We can check the status using the $? Variable. We've used it in previous lessons, and now let's refresh using of this $? And we'll start with an example. Let's name this example 31.error handling underscore checking exit status underscore example. As usual, I'll start with shebang, which is bin bash, and we don't need this slash, extra slash. So we'll start with a command, try to create a directory. And we'll use mkdir for this. Let's name it underscore my directory. Now let's check if the mkdir command was a success. And we'll use if statement here. In square brackets, we'll need a space. And use this $question mark variable. We need $question mark. Then we'll compare it equal to 0. And add a space again, add semicolon, then keyword, and then we'll echo the following string. Directory created successfully. Else echo failed to create a directory. And we'll run a command exit1. Close the structure with fi, save the file, clear the screen, again change mode, +x, that was file 31, and we'll run this file 31, and as you can see, directory was created successfully. If we ls, we can find my directory right at the bottom. By the way, let's remove this file 1 and file 2 with rm file asterisk to remove all files starting with fil. Let's list again. So my directory was created successfully. Let's clear the screen. So in this script, we attempt to create a directory and then check if the operation was successful. If it wasn't, we print an error message and exit the script with a non-zero status to indicate failure. It's a very basic and simple example, but it can be quite handy. Now we can use OR logical operator, and the character for it is double vertical lines. So we can use it to exit if a command fails. By the way, let me create a template file. So I'll create it with touch command and name it template, open this file and add a shebang here that'll be bin bash. So now when you're used to creating shebang, I won't be spending our time to create a shebang in every new script. Let's save it. And now we'll use this. Let me go to my home directory, ls it with a, and open this .bashrc file, go to the end of the file with uppercase G, and add an ls. So we'll name this ls new script. Let's say new underscore script, or just new, and that will run the following command: copy current directory template file to, let's say, script1 file.sh. Let's save this file, clear the screen, and we'll reload .bashrc file. We need source command for that. Cd to scripts and try to run new command. Let's check it. Now we've got this script1 created, script1.sh, and if we add script1, we can find that it contains shebang. Now every time we will be copying this script1 command, or better to say, renaming this script1 file to the file we need, to the name we need. So back to our lesson. Let me clear the screen. Now I'll rename this script1 with move command, and that'll be file 32, I guess. Let's use file 31, error handling, and let's name it OR operator example. And of course, that'll be file32. And by the way, let's change mode. We need to also add change mode command to our new ls command. So let me get back to my home directory again, open .bashrc, go to the end of the line, and what we need to do is to append the next command, change mode plus x script 1.sh. Okay, let me save this file, source.bashrc, change to scripts directory, list it, and now let's run this new ls and list again. Now, as you can see, our script 1.sh has got execution permission, and we don't need to run change mode plus x on every file we create. So now when you get acquainted and got used to this procedure, I won't repeat it, because now you know how to handle it. Okay, back to our script. I've created file32. Let's change mode plus x with 32 tab, and we'll open this file with vim, hit I, and add some script here. First we'll add a command here, try to change the directory, exit if it fails, and let's add cd path to directory, and then we'll add this or exit 1, and we'll add one more command. The script continues here only if cd was successful, and we don't need this extra s, and the command echo changed directory successfully. Okay, let's save it, clear the screen, and run it with /file32. And as you can see, we've got an error because path to directory does not exist. And if we correct this directory, for example, we want to go to, let's say, not path, but /home directory. Let's add one more. Save the file, rerun it. Now we get this message that changed directory successful. So this technique is concise but should be used carefully, as it doesn't provide much information about what went wrong. So if we change the script back to path to dir, save it, rerun it, we don't get much information here. Actually, in this particular case, we get information that no such file or directory. But there are lots of examples when this technique doesn't provide much information. Another basic technique is to use the set-e option. We can make our entire script exit immediately if any command fails by using the set-e option at the beginning. So let's copy the previous script, which was script 32, to the new one, and we'll rename it error handling set-e option example, and of course that will be example 33, not this one, but this one, 32 to 33. Okay, let's open it, and we'll modify a bit this script. We'll add set-e option here after the shebang, and let's add some commands after this cd command. For example, we want to create a new file with touch, new underscore file .txt, and we want to change mode 644 new file .txt. And let's change this echo string, all operations completed successful. Let's save this file and run it, file 33. And as you can see, we get an error right at the beginning of running the script. Let me get the contents of the script. So right here, the script exits on set E option. While powerful, this set E should be used with caution, as it can sometimes lead to unexpected exits. Now let's switch to some advanced error handling techniques. And the first technique is to use custom error function. We can define a function to handle errors consistently throughout our script. So let me clear the screen, create a new script with new command. It's an ls I've created, and rename this script.1.sh to file 34. Actually, let's use 33 error handling and modify it a bit. So that will be file 34, error handling, advanced, and the first technique is custom error function. Okay, let's open this file, vim34, and add some text here, some script code. So let's create a new function and name it error underscore, oops, not this one, but error underscore exit, parentheses, will open curly brace and echo an error message. We'll type error and we'll use variable $1, parameter 1, close this string, and then redirect it to $2. So this greater than $2 redirects the output to the standard error string, or stdr. In Unix-like systems, there are three standard input-output screens: stdin, or standard input, and file descriptor for it is 0. stdout, it's a standard output, and file descriptor for it is 1. And stdr, standard error, and file descriptor for it is 2, as you can see. So by default, echo command outputs to stdout, to our display. It's a standard output. And this greater than $2 part changes this behavior by redirecting the output to standard error out. And we'll add a new line, exit 1. We'll close this function with curly brace and add some scripting code below. Let's add a command, usage. So let's add cd block, cd path to directory. Then we'll add or logical operator and a variable error exit, not variable but our function error exit, and some text, failed to change a directory. And one more command, we'll need to touch new file.txt, and again or logical operator error exit, failed to create new file. So this second part is for error handling of each command. And finally we'll add an echo command to inform us that all operations completed successfully. Okay, let's try to run this script, that is script 34. Now we got this error failed to change directory. So now the output is a bit more informative. No such file or directory, line 10, and then we get error failed to change directory. So what this script does, and this function does, it prints an error message to stdr and exits the script with a non-zero status. Another technique is to trap errors. We can use the trap command to catch errors and perform cleanup operation. Let's create a new script with new command, and we'll rename it to script1 to 35. That'll be error handling, and let's cut everything after this advanced keyword, I'll press Ctrl K and name it wrapping errors. Okay, open it with Vim, file 35. So let's use cleanup keyword, and it's also followed by parentheses. That will be our function named cleanup, and we'll add opening curly brace and the body of the function. Let's add echo, cleaning up, temporary files, 3 dots, and let's use rm command dot rf dash rf, maybe without r, just f, and we'll be cleaning temp directory my underscore temp underscore file, and we'll close this function. Now we'll use trap keyword, then cleanup function, and exit command. Now we'll add, let's comment it, script commands here, and we'll add some commands. For example, touch tmp my underscore temp underscore file. And we can also add more commands. And finally, echo script completed. Let's try to run this script, that is script 35. Script completed, cleaning up temporary files. So this script will always run the cleanup function when it exits, whether successfully or due to an error. Now let me cat the output, the contents of this file again. And here, when the script starts, the cleanup function is defined, and the trap cleanup exit command sets up the trap to call cleanup on script exit. And this trap cleanup exit setup ensures that the cleanup function is called, and the cleanup function prints the cleanup message and removes the temporary file. This trap command allows you to specify a function to run when the script exits. This is useful for cleanup operations, like this one, ensuring that resources are released and temporary files are deleted. And this exit signal is a special signal in Bash that is triggered when the script terminates. This includes both normal termination, successful completion, and abnormal termination or errors or interruptions in the script. And finally, some words about debugging techniques. When things go wrong, and they will, here are some techniques to help you find and fix the problem. The first debugging technique is using set-x for verbose output. Adding set-x to your script will cause Bash to print each command before executing it. Let's create a new script. Again, by the way, what number should we use? That's 36 already. So let's move script 1 to 35, not 25, but 35. And let's remove this part, hit tab. That'll be script 36, error handling, advanced, and we'll name it set, not sex, but set x option. Okay, and we'll open it with Vim, and we'll add this option right below our shebang. So we'll type set-x. Now we'll add some code, echo. This is a debug message. Now let's add a command, ls, path to file. It's a non-existent directory. And again, echo command. This message won't be reached if the directory doesn't exist. Let's check how it works. /. Now we get, this is a debug message, and we get a message that an error occurs on this line, ls, path to file. Then the output of the error cannot access no such file or directory. So as you can see, we here can analyze the output and the errors step by step. And this can be incredibly helpful for seeing exactly what your script is doing. Another technique is to add debug echo statement. Sometimes the simplest debugging techniques is to add echo statements to your script. Let's create a new script with new command, and we'll move script 1 to 36, error handling. Actually, that should be 37, error handling, debug, echo, statements. We'll open it with Vim 37, not 27, but 37. Let's add first echo statement, echo debug starting script. And the command for it, let's add variable containing hello, world string. And now we'll add the second echo statement. Again, debug variable is set to $var. Close it, and we'll need double quotes here. Now we can add more commands. Then add the final echo statement, echo debug ending script. Okay, let's save it and run file 37. So as you can see, now we get the steps output on our screen. And finally, we can use bash debugger, bash db. For more complex scripts, you might want to use a full-fledged debugger. And bash has its own debugger called bash db, which always allows you to step through your script line by line. So let's try to run bash db with our final script, not final, but last script that was, I guess, 37. Now we'll get command not found bash db because it's not installed on this system, but that'll open an interactive debugger where you can set breakpoints, examine variables, and more. Now let's put it all together. Let's create a script that incorporates several of these error handling and debugging techniques. We'll name it debug script example. So let me create a new file with new command, move it to script 1 to 38.debug script example. I will open it with Vim and start with a command, enable command printing for debugging. And we'll use set-x command. Now we'll add error function, error handling function. By the way, something wrong with Vim output. Let me change appearance again. I change it to dark mode. Let's add a function name, error underscore exit, parentheses, opening function body, echo, error, $1, and we'll output it to $2, which is standard error output, and then exit 1. Close function body and continue. Now we'll create a cleanup function. Let's name it cleanup and add echo statement, cleaning up, 3 dots, and then we'll add a command run-f, and let's say we want to clean up tmp temp file, temp. The next block will be, we'll need to close this function, and the next block will be set trap to call cleanup function on exit. So we'll use trap keyword followed by the function name, which is cleanup and exit. Now we'll start our script, so we'll inform the user echo starting script. Let me hit enter several times, scroll up. Now we'll create a temp directory. Let's say not directory, but file. We'll do this with touch command, and we'll create it in temporary file directory and temp file name. Or logical operator, we'll use function error exit with the following text: failed to create temporary directory. Not directory again, but file. Next, we'll try to write to the file, and we'll do this with echo, for instance, hello, world string. We want to redirect to temp directory and temp file. Again, we'll use OR logical operator and error exit function with the following informational message: failed to write to the temp file. And finally, we'll try to read from the file. So this will cause an error, probably cause an error, because we'll be reading from non-existent file. So let's add from non-existent file. And in parentheses, this will cause an error. And we'll use cat command to read from this file. We'll be reading from temp, non-existent file, and again OR logical operator and exit, not exit, but error underscore exit function with the following message: failed to read non-existent file. And finally, echo, this line won't be reached due to the previous error. Okay, let's save this file and run it. That's file 38. And what we've got here: first off, a typo, failed to read non-existent file, but the script runs as expected. Grep cleanup exit, echo start and script. Then we created a file, added hello world to this file, and then tried to read non-existent file, got an error, failed to read non-existent, and exited from this script. Let me correct the typo, find this line and this word, hit A to append, failed to read from non-existent. Okay, so in this script we use set-x for verbose output, then we define an error handling function, then we set up a cleanup function with a trap, use our error handling function to catch and report errors, and intentionally cause an error to demonstrate how it's handled. Let's wrap up. Error handling and debugging are essential skills for any bash scripter, and they help you create more reliable scripts and make it easier to find and fix problems when they occur. So remember, always consider that you could go wrong in your script. You can also use exit statuses to check the errors. Also remember to implement appropriate error handling techniques and use debugging tools when things aren't working as expected. And again, practice these techniques in your scripts, and you'll find that debugging becomes easier and your scripts become more robust over time. Welcome back, everyone. Now we are going to dive deep into the examples used for our advanced bash scripting techniques lesson, and we'll walk through several advanced concepts and techniques. We'll be building on everything we've learned so far, so don't worry if some of this seems challenging at first. We'll break each concept down and look at practical examples. Here is what we'll cover. We'll cover advanced variable manipulation, including parameter expansion and indirect reference. We'll be covering advanced array operations, including associative arrays, process substitution, brace expansion, advanced input-output redirection, subshells and command grouping, advanced use of traps and signals, and recursive function. We'll be covering parsing command line options as well. Throughout the lesson, we'll look at the code examples that demonstrate this concept. We'll also create a more complex script that combines several of these techniques. So let's get started. And first off, let me list the contents to get the number we start with. So the last was number 38. We'll create a new file with new command. It's an ls new. Now we'll ls and new file has been created. Its name is script1.sh. Let's move this script.sh and we'll name a new file 39. Let's name it Advanced. And the first script we'll take a look as an example will be on parameter expansion. And we'll add .sh extension to this, open it with vim, file 39. First off, let's add a command here. What this script will be doing, that will be about parameter expansion example. Now let's add a variable name containing an empty value. Now we'll use echo to use this variable, and let's add parameter 1, option 1, that will be default value, colon, and let's use command substitution here. The structure of it, as you remember, is dollar, parentheses, then we'll use name variable, dash, and that will be, for example, John Doe. And by the way, we don't need command substitution structure here. We'll use curly braces, and this line uses this $name John Doe to provide a default value if name variable is unset or null, and it also does not change the value of name. Next, let's add another line, echo line, and this time we'll be using this name line. Let me copy it and paste it here, and let's remove this extra line. So this time the variable name will not be unset. We'll set it to the following value, $, and we'll use curly braces here. Let me delete this double quotes, and in curly braces we'll type name again, dash, and this time we'll set it to Jane Doe. So that'll be a value of name variable. And now we'll add echo, option 2, that'll be assign default, and we'll output name variable. Now let's add the third option with echo, that'll be option 3, where will be alternating value of this variable, and again we'll refer with $, we'll use curly braces, we'll refer to name and alternate it with plus, and we'll use such a string hello, comma, and we'll refer to this name variable. Close double quotes, close curly brace, and close the echo string. Now let's take a look at the next example. Let's add a string that'll be a variable, and the string is hello world as usual. Now let's take a look at the following example. Echo, that'll be option 4 for this technique, and we'll refer to the substring of this string. Let's put a colon here. And how do we refer to it? Again, $, curly braces, string variable, followed by colon, let's say to the 7th position and 5th position. We'll close this echo string, and finally echo option 5, string length. Again, let's put colon here and refer to the string variable with $, curly braces, string variable, and we'll need to put hash before string variable and close this echo string. Let's save this file, clear the screen. By the way, what file was it? 39. So let's run this file, 39, and take a look at what's happening. Line 16 and line 17. Let me find these lines. By the way, to find line 16, you just press Shift : and start typing 16. As you can see, it has found line 16 very fast. But first let me exit from this file and take a look at the error message. So line 16, unexpected end of file while looking for matching, and it is looking for double quotes. And line 17, syntax error, unexpected end of file. So let's reopen this file. That was file 39. And if we take a look at the script itself and the code, and we'll start with the first line, as you can see, we don't have a closing double quotes at the end of this echo line. So let's add closing double quotes here, and let's take a look at the second line, second echo statement, and we actually need to assign Jane Doe to the name variable, so we'll use equal sign here and save this script. Now let's try to rerun the script, and now it's acting as expected. So let me clear the screen and get the contents of this script and review it once more. Now, the first echo statement line checks if the variable name is set and not null. If it is unset or null, it uses John Doe as the default value. This is useful for providing default values without changing the actual variable. The next line, similar to the previous example, this second echo statement actually assigns the default value to the variable if it's unset or null, and it's assigning Jane Doe value to this variable. The next echo statement prints hello name, and if name is set or not null, and if name is unset or null, it prints nothing. This is useful for conditional output based on whether a variable is set. Next up is this line, string hello world, and here we extract a substring from string, which is hello world, starting at index 7 and taking 5 characters. And please remember that indexing are starting with 0. So it's a concise way to extract parts of strings here. And finally, the last echo statement prints the length of string. This hash operator, when used with $ and curly braces, it counts the characters in the string. So let's clear the screen and rerun the script. So there are 13 characters in the string hello world. The substring extraction was the world bird, and here we've assigned Jane Doe and then used Jane Doe with hello string. And we continue with advanced bash scripting techniques, and the next technique is indirect references. So let me reopen this. Actually, reopen, and let's rename this script to advanced_techniques.sh. So I'll go to the start of this command and add move 39. Advanced parameter expansion will rename to advanced-techniques.sh. Now we'll open advanced-techniques.sh script, go to the end of it, and let's add a new command. I'll scroll up a bit, and we'll add hash indirect reference. Now let's take it as an example, a variable fruit, and for example it's an apple. And let's put an apple into double quotes, and now we'll use apple variable, and value of this variable will be red. Now let's try to print this out to our screen with echo command, and we'll use the following structure. Though double quotes will refer to the variable, in curly braces we'll use exclamation point, and will refer to fruit variable. Let's save it and try to run this. Yes, we'll need to run a new script. We've renamed it advancedtechniques.sh. So that will print out a red value. Let me clear the screen, reopen the script. So this is an example of indirect reference. This structure, dollar, curly braces, and exclamation point before the variable expands the value of the variable whose name is stored in the fruit. So it first expands fruit to apple, and then looks up the value of the variable named apple. Another useful technique is different advanced array operations. So let's add a command here as advanced array operations, and the first technique in this block is, let's add another command, it's associative arrays. And let's take a look at an example of this associative arrays. And the syntax is as follows. First we use a declare keyword followed by dash uppercase A. That will be an associative array. And we give it a name, for example, fruits. And now we'll need to populate this array. So first we use its name, an array name, which is fruits, and in square brackets we use its values, for example, apple. And these values come in key pair structure. So apple is a key, and now we'll need to provide a pair for this. And we do this with equal, and in double quotes we'll specify red as a value of this apple key. Now let's copy this and paste 2 more times. Go to this second key pair. Let's delete this word by pressing DW, and this one DW. We'll also delete this one and this one. Okay, the second key pair, key value pair is, let's say, banana, and it's yellow. And finally, grape, and it's purple. Oops, I've skipped R. So that's how we declare associative array. Now we can refer to this array and its members, for example, use an echo statement. Let me type echo, followed by dollar, and curly braces, and we'll use fruits associative array. Now I'll copy this line and paste it 2 more times. So the first reference will be echo fruits, and let's refer to banana member of this array, and we do this with using square brackets and typing in the member name. And what the output could be, it'll print out yellow, right? Now the second example will use fruits, and let's say we want to print out all the members of fruits array. For this we'll use again square brackets, not curly but square brackets, and we'll use add symbol. This will print out all keys. Such a structure will print out all keys of this array. That is apple, banana, and grape. And the last example is we won't use exclamation point like in the previous example. We'll use only square brackets and add character, again add symbol, and this will print out all values of this array. That is red, yellow, and purple. So this demonstrates associative array, which are like dictionaries in other language. First we declare an associative array with declare dash uppercase A, then assign key value pairs. And we can access individual values or all keys or all values. Now, the next technique is array slicing. Let's add a command here and name it array slicing and type an example of it. Let's say we have numbers variable which contains the following value. In parentheses, we'll use 1, comma, we don't use comma here, 2, 3, 4, 5, 7. And now we can use the following technique. We can print out with echo. Again, we refer to this array with $, curly braces. Now we need to specify the array name, which is numbers, and we'll be using all values. So we'll type @ symbol. And now to refer to some of the values, some particular values, we use the following structure. Colon, let's say we want to refer to the first value of this array and the third value of this array. Think about the results, what this echo statement will print out to our screen. And the output is, I guess, 2, 3, and 4. So it extracts a portion of the array starting at index 1 and taking 3 elements. Remember, the element is starting from 0. The next technique is process substitution. So let me type it, process substitution. And here is an example of it. We'll use div command for this example, and then redirection character and curly and parentheses followed by the command itself. For example, ls dir1, and again we'll use less than symbol, again parentheses, ls dir2. This compares the contents of 2 directories, and this structure less than parentheses command runs the command and presents its output as a file. And this allows us to use command output where a file name is expected. The next technique is brace expansion. And I'll provide 3 examples with echo command again. And then we use curly braces, and I'll copy this line, insert 2 more times. And the first example is echo, for example, from 1 to 5. You remember we've used such a structure already, and that'll output numbers from 1 to 5. Range of numbers from starting from 1 and ending with 5. The second example is, let's say we want to output letters from A to E, for example. That'll output all letters starting with A and finishing with E. And finally, let's say we want to use file, and for example 1, 2, 3, and that'll be .txt extension. This will output file 1.txt, file 2.txt, and file 3.txt. So brace expansion generates sequences or combinations, and it's useful for creating ranges of numbers or letters, or for generating multiple file name patterns. Let's go to the next technique, which is advanced input output redirection. And here is an example. For instance, first goes command, then redirection symbol, which is greater than, and we want to redirect it to file 1.txt, and then the following structure 2 greater than &1. Now you should recognize this structure. What this does, this redirects both standard output and standard error to file.txt, and this 2 greater than &1 means redirect file descriptor 2, which is stdr, to where file descriptor 1 stdout is pointed. So that was technique 1, advanced input output redirection example 1. Example 2, And by the way, let's name example 1, redirect both std out and stdr to a file. And this one is to use, and let's add a space here. So use here document for multi-line input. How does it look like? The structure is as follows. For instance, we'll use cat command, then two redirection symbols less than, then followed by end of file keyword. Oops, not this one, but EOF, end of file, and again redirect symbol greater than, example file.txt, and we'll add several multi-line input. For instance, this is line 1, this is line 2, and then we need to close this structure with end of file keyword again. So that's how we use a here document for multi-line in. It allows you to input multiple lines of text directly in the script, ending with this end of file keyword or any word you choose after this symbol, 2 less than characters. The next technique we could use in our scripts in advanced techniques is subshells and command grouping. So we can perform different commands in a subshell. What's the structure of this subshell? So let's add a command here. For instance, we want to, let's name it, changes in subshells don't affect the parent. And here is an example. In parentheses, we use the command, for example, cd, then we are changing to tmp directory, and that's a logical operator, and then we run ls command. And the next command is outside of this subshell, so to say. And we want to run, for example, pwd command. And what it does, here in subshell, we are running these commands. But the results of these commands don't affect the main script commands. So we run these commands only in subshell. And if we run the pwd command outside of this subshell, that'll print out the original directory. So let's comment it, still in the original directory. So again, this runs commands in a subshell, and please note the parentheses here, and changes made in the subshell, like changing directory or some other changes, don't affect the parent shell. And by the way, I've forgotten to mention another example for this advanced input-output redirection, so let's add it here. That will be example 3. And we can use process substitution for multi-line input. And let's take a look at the example of this process substitution for multi-line input. And we'll use while loop, while, read line, semicolon do, and echo line, and we'll use line variable, close this echo string, and we'll use done keyword here to close this while loop. And now we can use redirect symbol like this, and now we can use a command here, for example, ls-l. What this does, this uses process substitution to provide the output of ls-l as input to the while loop without creating a subshell, which is a LPIC would do. Okay, now back to subshells and command grouping. So we've seen this first example with using subshells. Let's add a number here, example number 1, not here, but after the hash. And example number 2 will be for command grouping executes in the current shell. And let's add a space here. And now I'll provide an example of such command grouping. We'll need curly braces for it, add space here, and again we'll use cd-/tmp and logical character less and the space here. And we'll need to finish this command grouping with semicolon. And now we'll type pwd, and this time pwd will print out the temporary directory. So now in /tmp directory. So this example shows how to group commands to run in the current shell. And the changes, like change in directory in our example, will persist after the group. So we use parentheses for subshell, and we use curly braces for command grouping. Okay. The next technique is traps and signals. So let's add a command, traps and signals. We've already used traps in our previous videos, but for the sake of this document of advanced bash scripting techniques, we'll document it here. And the structure, as you remember, we can declare a function, for example, clean up, followed by parentheses. We'll open this function, add some commands here, for example, echo, cleaning up, 3 dots, and you can add cleanup code here. Let's comment it out. Cleanup code here, and then we'll close this function. And now we'll use trap keyword, and again, clean up, exit. So you remember the structure. And we'll also add one more line here, trap, echo, then interrupt, received. Lots of spelling mistakes here, received, and interrupt will add one more R. That'll be our echo message, and we'll close this single quote here, followed by int keyword. What this does, this sets up a cleanup function to run when the script exits, that is trap exit, and a message to display if the script receives an interrupt signal, which is trap int. So traps allow you to handle signals and perform actions when they are received. The next technique is recursive functions. So let's add a function. Let's name it traverse. Again, parentheses, opening, square curly brace, and the function body will be as follows. We'll use for structure, file in, let's refer to the $1 variable. That will be the first parameter, divided by everything. We will start from root, semicolon, do. And now if, and we'll be checking if it is a directory in square brackets. We'll add a space here, -d, and we'll refer to file variable. Again, add a space here, semicolon, then again we'll use this traverse function for the file variable. Else echo file. End of if statement, and done. And we'll close this function body. This function recursively traverses a directory structure, starting from the root directory, specified here, and it's processing all the files. This asterisk is for all files. And if it encounters a directory, we're checking it with this -d statement. It calls itself with that directory as an argument. This is very useful for operations on directory trees. Now, the next example of advanced bash scripting techniques is parsing command line option. Let's add another command here, parsing command line options. Let's take a look at the following script. That'll be a while loop, get ops and in double quotes, followed by colon, let's say A, colon B, colon, and followed by opt variable, do. And now we'll start case structure, followed by opt variable. In case A, echo. You remember we've had such a structure in previous example. Now we'll add such an example here. Echo, and let's say option A, let's say dash A was triggered, and parameter for this option will be $opt arg variable, and we'll redirect it to standard error. Let me make the appearance a bit smaller. This will finish this case with double semicolon and start case B. And by the way, let me copy this line and insert it here. So option B was triggered, parameter opt arg. Again, we'll finish this case with double semicolon. And finally, all other options, echo, invalid, option, and we don't need all these words, dash, opt arg, and again we'll finish it with double semicolon. ESEC to close the case, and done. So this uses getOpt to parse command line option. It looks for options A and B, both of which expect an argument. The colon at the start of the option, here it is, let me scroll up. This colon at the start of the option string, suppresses error messages from getOpt. So that's a bit of advanced bash scripting techniques, as the name of this lesson, but for your information, you need to know such a technique. So that was, so to say, theoretical part, and mentioned lots of examples in this file, and I'll save this file for now, and let's rename it again. We'll rename it to 39 Advanced Techniques, Examples. And the next file will be an example script using several or some of these advanced techniques. So we'll take a look at the script example with the techniques we've mentioned in the previous file. Let's create a new file with new command, and we'll rename it to 39 Advanced Techniques, but that'll be not 39, that'll be script 40. Advanced Techniques, let's say script example 1.sh. Let's open this file with vim 40 and start from scratch. First, let's use this structure, and you try to recall how is it named. So we'll use declare keyword, declare -a, and let's name it files. Now we'll use a traverse function with open and curly brace and function body as follows. For file in, again, $1 parameter variable, parameter variable, and for all files starting from root, $do, and we'll use if statement, if. Now we'll be checking the files for is it directory with -d parameter, and we'll be doing it for each file, space, semicolon, then, and we'll call this function again, traverse, for the file variable, else, ext, which contains the following value in double quotes, $, curly braces, file, let's say, ## asterisk dot, and then files in square brackets, ext variable, and then equals, again, $, double parenthesis, files, as ext and +1. And we'll need double parentheses here. We don't need double parentheses here. We need double parentheses here. And a fi done. And we'll finish this function with closing curly brace and continue the script. Now we'll use trap keyword, clean up, exit, and of course we'll need to add this cleanup function, so let's write it. Clean up, parentheses, opening curly brace, echo statement, cleaning up, and the command for cleanup is rm-f, and we'll be removing, for example, tmp directory, and the file, let's say file count.txt. Okay, and we are using trap keyword then, cleanup function, and exit status. Now we'll start our script, so we'll inform the user with it, about it, echo starting file count, and we'll refer to reverse function with the following: $curly brace $$pwd. The display of my Vim again got corrupted. Let's change it to dark schema pwd. Now we'll start the following: opening curly brace, echo file extend counts colon, and we'll add for statement for ext variable in the following: $, curly braces, exclamation point, files, all values, semicolon do. Echo, again, double quotes, ext variable, then $, curly braces, files, and in square brackets, I'll use the ext variable. Done. Now let's close this structure and add output redirection to tmp file count.txt, and add an echo statement here. File counts have been written to tmp file underscore count.txt. Now let's use the following structure: cat redirection, end of file keyword, script completed, dot, here is summary, total number of extensions found, and we'll use the following variable: $, in curly braces, file, and we'll add hash to count all files, and we'll refer to all items in this array. Now, another command, most common extension, and we'll use such a long line: $, in parentheses, we'll use sort -rm command in tmp file underscore count.txt, and pipe it to add-n 1, the first line. And now we'll use end of file keyword. So what this script does, it uses an associated array files to count file extension. Then it defines a recursive file function traverse. Let me go back to this function. Here it is, traverse, and it walks through directory structure. Then it passes parameter expansion. Let me find it. Here it is. To use a default value if no argument is provided. Then it employs a trap for cleanup, and it uses command grouping and output redirection to write results to a file. Let me find it. So here is a trap cleanup with cleanup function, and here is a command grouping. It also demonstrates here documents for multi-line output. So this structure is a here document structure, and it uses command substitution to find the most common extension. Now let's save this script and try to run it. That's script 40. Let's hit enter. We get an error, of course, as expected, because you cannot do without errors on line 33 and line 50. Again, unexpected end of file while looking for matching. Somewhere I didn't close the statement with double quotes. So let's reopen this file and take a look at it. Let me change the appearance, reverse, everything looks fine. Okay, cleanup function misses closing curly brace. This is fixed. Now this trap cleanup exit is outside of this function. So there was another error. Yes, I see it. It's here echo file counts have been written to, and we didn't close this echo statement. Let's save it with right Q, clear the screen, and try to change appearance again. Rerun the script. So start and file count. Script started successfully. Then file counts have been written to this file. It's a good sign. Then script completed and has a summary. Total number of extensions file 27. Most common extension is .sh. That's true. Oof, that was a long lesson. So to wrap up, we've covered a lot of ground in this lesson. These advanced techniques can make your bash scripts more powerful and flexible and efficient. Remember, the key to mastering these concepts is practice. So try incorporating them into your scripts, experiment with different combinations, and don't be afraid to push the boundaries of what you think bash can do. In our next lesson, we'll look at how to optimize your bash scripts for performance and how to handle very large data sets efficiently. Welcome back, everyone. Today we are diving into lesson 13, Bash Script Optimization and Performance. This is where we learn how to make our scripts not just work, but work efficiently. And we'll walk through various techniques to optimize our bash scripts. We'll start with bash optimization that anyone can apply, and then move on to more advanced techniques for handling large data sets. Here is what we'll cover. Why optimization matters in bash scripting. Basic optimization techniques and advanced optimization strategies. Techniques for handling large data sets efficiently and how to profile your scripts to identify bottlenecks. Throughout the lesson, we'll look at code examples that demonstrate these optimization techniques. We'll also create a script that puts several of these techniques into practice. So let's get started. Now, why optimization matters? Imagine you're cooking a meal. Again, you could run back and forth to the fridge for each ingredient, or you could gather everything you need at the start. The second approach is clearly more efficient. The same principle applies to our scripts. By optimizing, we can make them run faster, use less memory, and be more responsive. This is especially important when dealing with large files or running scripts on less powerful machines. And as usual, let me switch to scripts folder directory, list it, and sort output by time created. And the last file we've created was file number 40. So let's clear the screen and create a new file, rename it to the file number 41. We'll name it Optimization Techniques, and we'll open it with Vim, file number 41. And the first optimization, I'll need to insert it. The first optimization technique is to use built-in commands, and we'll comment it out. The slower technique will be, for example, to use echo, hello, world, stream. Let's copy it. And faster technique will be to use, instead of echo command, printf built-in command. So bash built-in commands are generally faster than external commands because they don't require spawning a new process. The second technique is to avoid unnecessary commands. And let's use some example. Again, slower will be, for instance, to use cat file.txt and then pipe it to grep command and look for some pattern. And let's add faster technique. That will be to use grep without cat command. So we could type grep and look for some pattern in file.txt. Instead of using this pipe construction, we could use grep without cat. Okay, the third technique is as follows. We can use shell arithmetic instead of expression command function. Again, let's start with slower, and that will be, for instance, result containing the following command. In parentheses, we'll use expression, for instance, variable a plus variable b. And now let's add faster option, faster variant, not fatter, but faster, sorry. That'll be vice versa, thinner, not fatter. And we could type it like this, result equals dollar and double parentheses a plus b. Let me hit enter several times to scroll up. The next technique, that'll be technique number 4, will be to use double brackets or conditionals. And double brackets are more powerful and generally faster than single brackets. Again, let's add slower example. That will be single square brackets, and we'll need if conditional. Then add a space here. Let's say variable a, and it's equal to variable b. Again, we'll add space here, and then semicolon, and then keyword. Now let's add faster technique, and let me copy this previous and paste it here. And we'll use all the same, but we use double square brackets, opening and closing. So these were the basic. Let me find the start of this file, and we'll add one more command. It was basic optimization techniques. Now let's copy this line, go to the end of this file by pressing Shift G, go up several lines, and now let's list some advanced optimization techniques. So I'll replace basic with advanced optimization techniques. And the first advanced optimization technique is to use command grouping. We've already met such a technique in previous example when we've used command grouping. Let's add a slower example first, and we use parentheses for command grouping, for instance, cd command. Then we'll cd to tmp directory tmp. We'll add and logical operator, and the next command could be echo in tmp, for example, and we'll add and again ls. And now let's add faster version of this. So the first version was, let me copy it, it was using a subshell. And faster version is to use a command grouping. So we'll change this parenthesis to curly braces. The first one, and closing curly braces, and that's it. And by the way, we'll need a space in the beginning after opening curly brace, and a space at the end before closing curly brace here. So try to use command grouping instead of using subshells. The next technique, it will be the second technique, is to use process substitution. Again, first slower. For instance, with div command, we've seen such an example already. And we'll use sort output, L1, for example, and another sort command with file2. And now the faster version of it will be as follows. Again, faster. So the analog for this command could be as follows: sort file1 and output it to, let's say, sorted1. Copy it, paste 2 more times, again to insert mode, sort file2 to sorted2. And now we could use div command with sorted1 and sorted2. The third technique is to use arrays instead of multiple variables. Now, arrays can be more efficient than separate variables, especially when dealing with large data sets. And let's start with less efficient example. Let's remove this extra A letter here. And less efficient example is as follows. Let's say we've got value 1, which is, I'll copy this line and insert it 2 more times. And value 1 will be, again, apple, value 2 is banana, and value 3 is grape. And more efficient will be the following example. So let's replace less with more. And the example looks like as follows. We could use array named fruits containing, in parentheses, apple. We'll need to remove this parenthesis and double quotes, sorry, and add it here. Then banana and grape. So that will be more efficient to use such kind of array instead of 3 separate variables. Another advanced technique, that will be technique number 4, to use read command with here string for parsing. When parsing multi-line output, using this read command with here strings can be faster than using a pipe. Again, let's start with slower example. Let's say we'll use echo command and we'll need to output line 1 and we'll add new line here, then line 2, new line again, and line 3, new line again. Actually, we don't need new line after line 3. We'll close this echo string and pipe it to while read line, do echo line and line variable. We'll add done keyword, and now we'll take a look at faster example, what can be done to optimize this code. So we could use while read line do echo line and line variable, and then done keyword. And near the done keyword, we could use the following construction with 3 less than characters, symbols, and start multi-line string. So line 1, and then followed by line 2 on the next line, and line 3 on the next line, and close double quotes. What's next? Let's add a new block here and name it optimization for large data sets. So when dealing with very large files or data sets, traditional bash techniques might not be sufficient, and we'll take a look at some of the strategies for handling big data. And the first technique is to use awk for complex text processing. Awk is a very robust tool, and we could spend or dedicate a whole course to this tool. But here we just mention it for you to know that it exists. So for complex text processing tasks, awk can be much faster than pure bash. And let's first start with slower example. Again, for instance, we could use while loop, read, line, do, field 1, and we'll need field 1 to be indented. It contains the following: dollar and parentheses, and inside of parentheses, echo, and then we'll add line variable, pipe it to the following command: cut -d, and in single quotes we want to cut comma, and then followed by -F1. Let's copy this line, insert it below, and modify the second line, field 2, and we'll need to replace F1 with F2. Then we'll echo the result of it in double quotes. We'll use field 1 variable and field 2 variable. We'll need dollar before field 2, and finish it with done keyword. And again, we'll use redirection to this loop from large file, for example, .txt or CSV. And now let's take a look at faster variant of this code. We could use awk for this large file text processing with -F parameter, and again we'll be looking for comma, and then in single quotes we'll use the following expression: print $2 space double quotes space double quotes space $1, and we'll put this expression into curly braces, and we'll put it into single quotes as well, followed by large underscore file .csv. So this line will be first off more compact, and it'll be more efficient to process large text file. We won't be talking about awk here in detail, but that's just for your general knowledge that there is such a tool named awk, and it is very robust and good for working with large files. Now, the second technique for optimization for large data sets is to use sort-u command, and we'll need a space here, instead of sort-unique command. And of course we don't need this UI, just like this. So when you need to sort and remove duplicates, this sort-u is faster than pipe and sort to unique. And by the way, I've made a typo here, or mistake. That's not -unique. We'll need a pipe here. And let's take a look at slower example first. We'll use sort large file.txt, for example, piped to unique command, and faster analog will be to use sort-u large file.txt. And by the way, we've made a mistake somewhere in the previous code, because our code changed color, and it means that somewhere we've made a typo. And of course we don't need this single quotes here and this space here. Everything else seems to be fine. Okay, let's continue. And the next technique is to use grab-F for fixed strings. So let's take a note of this. We'll command use grab in single quotes grab-F for fixed strings. I made a typo here, strings, and again, slower, let's say grep with exact string, large underscore file dot txt. And faster, let's add a space here, and faster will be grep dash uppercase F parameter, and again, exact string in large underscore file dot txt. And that'll be example number 3. And example number 4, or technique number 4, in large files processing is to use parallel for multi-core processing. Again, slower. Actually, we won't be using slower here and faster. Just one example. Let's say we started with cat large file.txt and pipe it to parallel dash pipe, and now we'll use awk again, the following construction in curly braces and single quotes, print $2. So for very large data sets, you can use the parallel command to utilize multiple CPU cores. The next block is to profile your scripts. So we'll add another block, profiling your scripts. And the first technique for it is to use time command. So to optimize effectively, you need to know where your script is spending most of its time. And the first technique is to use this time command. The time command gives you a simple breakdown of how long your script takes to run. And an example of using it, for example, you could use time and run your script, like my script.sh. Let's save this file and use time command with the previous script, which was script 40. It was advanced techniques script example 1.sh. And as you can see, it provides time in milliseconds or seconds, gives you the breakdown information. Okay, let's reopen optimization techniques file and continue it. And the second technique for profiling your scripts is to use, and we've already used it, set-x command. This will add, if you add this set-x command at the beginning of your script, it will print each command as it's executed, along with its arguments. This can help you identify which parts of your script are taking the longest. So, as you remember, we first add shebang to our script, and then we add this set-x command. And then we add the script below this command. So, that'll finish up our, so to say, theoretical part of this lesson. And now let's put it all together and create a script that demonstrates some of the optimization techniques. So I'll create a new file that will be file 42, optimization techniques, script example 1.sh, and we'll add a shebang here, which is bin bash, and start our script. So first let's use printf instead of echo. That will be instead of echo. And for this we'll type the following command: printf and a message starting script 3 dots, and add a new line here to have a better readability. Then we'll continue our script and we'll use shell arithmetic. We'll declare start variable and add $, double parentheses, and after the opening double parentheses we'll add $, parentheses again, and inside we'll add date command with the following output: %s, %n, divided by 1 million. Okay, let's move on and Next, we'll use command substitution and command grouping. We'll start with opening curly brace, and we'll use awk, for example. For this example, dash uppercase F in single quotes, comma, then in single quotes and curly braces, sum plus or equal $2. Now we'll use AND keyword, not AND keyword, and again in curly braces, print total, comma, sum. And we'll need data.csv file for this. Now let's use grep dash uppercase F command, and we'll be looking for some important data. Let's add an underscore here, and we'll be looking at in some large underscore file.txt, and then we'll pipe it to word count dash L command, close double quotes. And the third example will be, by the way, let's add a command here for the second example, and the first, by the way, too. So awk, use awk for complex text processing, and grep, use grep dash uppercase F for fixed string searching. And the last example will be use sort dash U instead of sort pipe unique. And instead of, let me correct it, we'll add a here. So the command will be sort dash U, and let's say we're using names.txt file and redirect it to file named unique underscore names.txt. Now let's hit enter and close this block and redirect it to results.txt. And seems like we've got an extra close and double quotes here. Let's remove it. And as you can see, after we correct an error or a typo, Vim automatically changes the following lines, next lines. So we'll continue, and we'll add two more blocks, small blocks here with, for example, use shell arithmetic again, and let's add AND variable. Again, we'll start with $, double parenthesis, $ again, parenthesis again, and inside of this parenthesis, we'll add date again, plus %s, uppercase N, divided by 1 million. And finally, we'll use printf and command substitution. Okay, so the command is printf, and we'll add the following message. Script completed in %d millisecond, and we'll add a new line, close double quotes, and refer to AND variable and start. So I guess that's it. We'll save the script, clear the screen. Now let's try to run it. That was 41. Let me list it. This TR 42. Yes, we need to change mode plus X 42 clear the screen and try to run it to catch first errors. Permission denied. That's an interesting error. Okay. Yes. Change mode plus X. Run again. Let's list it with LTR. And as you can see, we'll need to add some more permissions. Read write X to the owner and read to the group. So let me go back to change mode. User plus read write and group read. And let's LTR once more. It didn't add to the group read permission. But I guess that's okay for us to run the script. And finally we get the first errors, line 4, print F, command not found, then cannot open data.csv file as expected because I haven't created such a file yet, then cannot find large file.txt as expected, cannot read names.txt, and script completed in 20 milliseconds. So the script is acting as expected because these files don't exist yet. So let's reopen this script again and search for line 4, print F. As you can see, it's a typo, a tiny typo. So I'll search for the previous command to open the script, search for line 4, here it is, and let's add T letter here, printf, save the file, and rerun it. Now, printf works just fine, starting script, awk dumps fatal error because data.csv doesn't exist, and grep and sort don't like that large file.txt doesn't exist and names.txt file doesn't exist. Now I've got a task for you. Let's clear the screen. And task number 1, create a script which generates data.csv file. And task number 2, create a script which generates large underscore file.txt. And task number 3, create a script which generates names.txt file. Names. So these are the scripts which you could try to create for your practice to generate these files. And if you've got any troubles doing so or some questions to do so, I'll now offer you a solution for these tasks. So if you want to see a solution, if you don't want to see a solution, press pause here and get back to the solution when you need so. Now let's create the first script which generates data.csv file. Let me ls our directory to find the number of the script. That will be number 43. So let's use new command, which is nls. The appearance got weird. Let's change it to dark. And we'll move script 1 to 33. Actually, let's use 42 and change it to 43, and that'll be optimization techniques script, and let's rename it to data CSV. Actually, let's name it data CSV and remove this part and use number 42. So that'll be 42.datacsv.sh script. We'll open it with vim 42.datacsv, and the script itself could look as follows: for I in curly braces from 1 to 100. By the way, let's change the appearance again. Then do echo and in double quotes I variable, comma, dollar, and we'll need double parenthesis and a space inside of double parenthesis, random, then percent, 1000. Another space here, and let's redirect the output of this command to data.csv file followed by done keyword. Okay, let's save it and run this script. That was 42 datacsv.sh. Now if we list the contents of our directory, we'll find data CSV file. And if we open it with vim, we'll find that it contains several numbers. Let's save it. Now if we rerun the previous script, this one 42 optimization techniques script, there will be only 2 errors now, because data CSV already is accessible. Now let's create a new script, 42, and we'll name it large_file.txt. Oops, not txt, just large_file.sh. That's a script. We'll open it with Vim, delete this line. Actually, let's use it, so I'll press U to undo the change. So for I in from 1 to, let's say, 1000, do, actually let's leave do on this line and remove all this information, and we'll start with if statement. In square brackets we'll add a space, dollar, double parenthesis, again a space here, random function, %10, and then we'll compare it equal to 0, and we'll add a space here before the closing square bracket, then keyword echo important data. Again, my virtual machine appearance connection behaving weird, so I'll change appearance to dark to have all information visible. As you can see, we've got a typo here, important data, and we'll add closing double quotes and redirect it to large_file.txt. Let's copy this line, else, and we'll insert this line below, echo other data, and by the way, let's print it with, not with uppercase, other data, underscore, so we need such a string, and important data as well, with underscore data. And we'll finish it with fi keyword and done keyword. Let's save it and run this file, that is file 42, largefile.sh. Okay, somewhere I've missed closing double quotes, so let's reopen it, and here it is. Before other data, we'll need an opening double quotes, rerun it. Now if we list the contents, we'll find large file, but not their file, large file. Okay, let's reopen it again and add G here and G here, large file. Save it again, rerun it, list. Now we've got this large file.txt. And finally, to create a script which generates names.txt file, we'll again copy file number 42.datacsv to file number 42 names.sh file, and open it with Vim, 42.names.sh, and modify it a bit for I in, let's say, from 1 to 50. Again, I'll need to change appearance, do, echo, and we'll use names variable instead of I. So let's replace I with names. We don't need this comma, and we don't need this extra dollar. Instead, we'll add curly brace here, opening curly brace, random %10, and let's add square bracket, opening square bracket here, and closing square bracket here, and closing curly brace here. And we'll append this data to names.txt file, names.txt. Also, we'll need to add a variable names containing the following: lots of names, for instance, Alice, Bob, Charlie, David, Eve, Frank, Grace, and Jack. Let's save this file, clear the screen, try to run it, that is 42 names.sh, and list the contents again. Here it is, names.sh. If we get this file, the contents of this file will get lots of randomly generated names. So let's clear the screen and rerun the file 42 Here it is, optimization technique script, example 1. Now we haven't got any errors. I'll clear the screen, and the problem is that our script doesn't produce any results. So let's try to rerun the smaller scripts to generate all the necessary files. Again, we'll run scripts with bash command, that is 42, and we'll need data csv.sh file, 42.large file, and 42.names.sh file. Okay, let's double check if the files exist. Data.csv exists, results.txt exists, but large file is produced with a typo. Let me open file 42.large file and double check it. Seems like everything is okay here, but the file doesn't exist. Let me remove this layer_file.txt, list again, and let's list it with LTR. Or better, let's list the file itself. I'll clear the screen and run ls and start large file. No, it doesn't exist because if I press tab, it doesn't offer me this name. So let's run this 42.large file shell again, list again. Now this file exists. I don't know why it wasn't generated at first time, but now all three files exist: data, csv, large file, txt, and results.txt. Let's clear the screen and run this 42 optimization technique script example once more. Now it says that names.txt doesn't exist. So the problem is that we should run these three small scripts to generate three files which are needed for this large script, which is 42 optimization technique script example 1. And the second task for you for this lesson is to add these three smaller scripts to the main script. So incorporate these three smaller scripts as blocks of this larger script, which is 42.optimization techniques script example 1. Press pause here, and in several seconds I'll show you the solution for this task. Okay, I've created a copy of this script and I've named it, ls and ls-tr. Here it is. That's optimization technique script added. So if we open this script with vim 42 optimization technique script added, we can read the modified script which incorporates the generation of these files. Let me change the appearance to dark. So first we generate data.csv file with a smaller script. You've seen how to create it, where we generate the data for this file. Then we generate large_file.txt with the following script, with the following code. We generate the screen's other data and important data. And then we generate names.txt file with names variable containing the names. The indentation is not perfect here because I used copy-paste to edit this script really fast. Later on I'll edit it with an appropriate indentation to have it on GitHub in an appropriate form. So we've generated names.txt file, and only then we run the optimization script. Now the optimization script is the same as we've seen before, so I'll close this file, clear the screen, and now let's try to run it. That was file 42 optimization script techniques added.sh. And now it performs just as expected. it outputs the information that certain script, then outputs the information of the completion in milliseconds, total number, and everything else as expected and planned to be performed in our original script. So it was quite a long lesson, and I hope it was informative with lots of troubleshooting and workarounds. And now let's wrap up. So optimization is much as an art as it is a science. The techniques we've discussed here can significantly improve your script's performance, but also remember to always measure before and after optimization to ensure you're actually improving performance. Don't optimize prematurely. Make your script work correctly first, then optimize if necessary. And also remember about readability. Readability is often more important than minor performance gains. Don't sacrifice maintainability for small speed improvements. And again, troubleshooting is important. Read errors, refer to the lines with these errors, and identify why your script isn't producing the expected output. Starting with scripting, and we'll begin with improving command line productivity. The goal for this video is to learn how to run commands more efficiently by using advanced features of the Bash shell, shell scripts and various utilities provided by Linux. The objectives for this video is to automate sequences of commands by writing a simple shell script, efficiently run commands over list of items in a script or from the command line using the loops and conditionals, and to find text matching a pattern in log files and using command output with grep command and regular expressions. So many simple common system administration tasks are accomplished using command line tools. Tasks with greater complexity often require chaining together multiple commands that pass results between them. And using the Bash shell environment and scripting features, Linux commands are combined into shell scripts to easily solve repetitive and difficult real-world problems. Now, in its simplest form, a Bash shell script is an executable file that contains a list of commands and possibly with programming logic to control decision-making in the overall task. And when well written, a shell script is a powerful command line tool on its own and can be leveraged by other scripts. Shell scripting proficiency is essential to successful system administration in any operational environment. Working knowledge of shell scripting is crucial in enterprise environments, where script use can improve the efficiency and accuracy of routine task completion. Well, you can create a Bash shell script by opening a new empty file in a text editor, and while you can use any text editor, advanced editors such as Vim or Emacs, which understand Bash shell syntax and can provide color-coded highlighting. This highlighting helps identify common errors such as improper syntax, unpaired quotes, unclosed parentheses, braces and brackets, and much more. Now, the first line of a script begins with the notation of two symbols, commonly referred as the shebang, or the names of two characters, sharp and bang. This specific 2-byte notation indicates an interpretive script. Syntax that follows the notation is the fully qualified file name for the correct command interpreter needed to process the script's line. And for script files using bash scripting syntax, the first line of a shell script begins as follows: shebang/bin/bash. As you remember, a completed shell script must be executable to run an ordinary command, and we can use change-mode command to add execute permission, possibly in conjunction with change-own command to change the file ownership of the script. So grant execute permission only for intended users of the script. If you place the script in one of the directories listed in the shell's path environmental variable, then you can invoke the shell script using the file name alone, as with any other command. The shell uses the first command it finds with that file name. So please avoid using existing command names for your shell script file name. Alternatively, you can invoke a shell script by entering a path name to the script on the command line. And here the which command, followed by the file name of the executable script, displays the path name to the command that will be executed. For example, I've got a small script in my home directory, bin directory, with the name hello. And if I run which hello, I'll get the path to that command. Now let's take a look at the path variable by typing hello $path. Now some words about quoting special characters. A number of characters and words have special meaning to the bash shell. However, occasionally you will want to use these characters for their literal values rather than for their special meanings. To do this, use one of the three tools to remove or escape the special meaning. We've got backslash, single quotes, and double quotes. The backslash escape character removes the special meaning of the single character immediately following it. For example, to display the literal string not a command with sharp character in the beginning, and if we want to display the string with echo command, the sharp sign must be interpreted by bash as having special meaning, and we can place the backslash character in front of the sharp sign. So let's type echo sharp not a command, and as you can see, this doesn't work. And if we place backslash and type echo backslash sharp not a command, we'll get the output of this string. When you need to escape more than one character in a text string, either use the escape character multiple times or employ single quotes. Single quotes preserve the literal meaning of all characters they enclose. So let's type again to test without single quotes. We'll type echo sharp not a command sharp. We'll get no output here. Now we can try another example, echo backslash sharp not a command, and sharp without backslash. We'll get this output. Then the example with two backslashes before sharp characters, and an example with single quotes. We can also use double quotes or double quotation marks to suppress globbing and shell expansion, but still allow command and variable substitution. Variable substitution is conceptually identical to command substitution, but may use optional brace syntax. Let's use different examples with single quotation to interpret all text literally, double quotation marks, question mark, which is a meta character that also needs protection from expansion, and review these examples. Take a look at the example of the first line where we display the host name of the local system with the help of variable. So variable equals the command hostname -s, and then we output this variable with the echo command. The second example is echo with double quotations, where we've got an output of the string combined with the variable var interpretation. The third example is using backslash before dollar character, and in this case dollar character is interpreted as a string. In the next example, we output the string combined with the variable where it is interpreted as a variable. In this case, we are using double quotation, and if we use single quotation, we get the string interpreted, the whole line interpreted as a string. Then again, the example of using backslash before special character, in this case it's double quotation, and interpreter skips the double quotation right after the backslash. And the last example is how to interpret single quotations. In this case, the whole string, the whole phrase is interpreted as a string. Now, some words about echo command and provide an output from a shell script. The echo command displays arbitrary text by passing the text as an argument to the command. And by default, the text displays on standard output or std-out, but it can also be directed to standard error or stdr using output redirection. In the following simple bash script, the echo command displays the message hello world to std-out. And in the second example, the echo command, which is widely used in shell scripts to display informational or error messages, can be a helpful indicator of the progress of a script and can be directed either to standard output, standard error, or be redirected to a log file for archiving. And when displaying error messages, it is good practice to direct them to std-er, std-r to make it easier to differentiate error messages from normal status messages. The echo command can also be very helpful when trying to debug a problematic shell script. The addition of echo statements to the portion of the script that is not behaving as expected can help clarify the commands being executed, as well as the values of variables being invoked. And again, for references, see bash magic echo commands man pages. Now let's write a simple bash script containing a sequence of commands and run it from the command line. First off, let's create and run a simple bash script. We'll use the Vim text editor to create a new text under your home directory and name it firstscript.sh. So we'll type vim firstscript.sh. Now we'll add the following text and save the file. First line with shebang and command line interpreter, in our case it's bash. The script lines with echo command. The first one generates a string and redirects it to the output.txt file. And two more echo commands serving as separation and for ease of reading of this output file. Now let's use the sh command to run the script. We'll type sh firstscript.sh. We can review the output file generated by the script by typing cat output.txt. Now let's add more commands to firstscript.sh script, run it and review the output. We'll use the Vim text editor again to edit the firstscript.sh by typing vim firstscript.sh and append the following lines to this script file. We'll add some more echo commands, ls bulk command, and df-h command. And all the content generated with this script will be redirected to the output.txt file. Now let's make this first script.sh file executable using the chmod command. We'll type chmod 8 plus x first script.sh. Now let's run the script by typing ./firstscript.sh and review the output file generated by this script. We'll type cat output.txt. And optionally, to remove this script and the output file, we'll type rm and the name of the files. Running commands more efficiently using loops. After completing this video, you'll be able to iterate over lists using for loops, evaluate exit codes from commands and scripts, perform tests using operators, and create conditional structures using if statements. So, system administrators often encounter repetitive tasks in their day-to-day activities. Repetitive tasks can take the form of executing an action multiple times on a target, such as checking a process every minute for 10 minutes to see if it has completed. Task repetition can also take the form of executing an action once across multiple targets, such as backing up each database on a system. The for loop is one of the multiple shell looping constructs offered by Bash and can be used for task iterations. Let's take a look at the syntax of for loop. For example, for variable in list, semicolon, do command variable, followed by done. The loop processes the strings provided in list in order one by one and exits after processing the last string in the list. Each string in the list is temporarily stored as the value of variable. So while for loop executes the block of commands contained in its construct. The naming of the variable is arbitrary. Typically, the variable value is referenced by commands in the command block. The list of strings provided to a for loop can be supplied in several ways. It can be a list of strings entered directly by the user, or be generated from different types of shell expansion, such as variable brace or file name expansion, or command substitution. Let's take a look at some examples that demonstrate the different ways strings can be provided to for loops. The first example, for host in host 1, host 2, host 3, do echo host variable done. The next example, for host in host 1, 2, 3 in curly braces, do echo host variable done. And the third example, the same result but different syntax, for host in host 1, 2.3 in curly braces, semicolon, do echo host variable, semicolon, done. Another example, for file in file asterisk, meaning all the files starting with a file word in their names, do ls file variable done. Now let's say we want to find the files with the ending from A till C. So we'll type for file in curly braces A two dots C, do ls file variable done. Now if we want to find all the packages installed on some particular date, we could run the following code. For packaging, the variable containing a set of commands like rpm and grep. Then we are using echo command to make it more readable, followed by a set of commands in variable, namely date, rpm, and followed by done. And we'll get the list of RPMs installed on some particular dates. And the last example, for even in sequence 2 to 10, do echo even variable done, meaning that we want to find even numbers from the sequence starting with 2 till 10, and the step will be 2. Now, after a script has processed all its contents, it exits to the process that called it. However, there may be times when it is desirable to exit a script before it finishes, such as when an error condition is encountered. This can be accomplished with the use of the exit command within a script. When a script encounters the exit command, it exits immediately and does not process the remainder of the script. The exit command can be executed when an optional integer argument between 0 and 255, which represents an exit code, and an exit code is a code that is returned after a process has completed. An exit code value of 0 represents no error. All other non-zero values indicate an error exit code. You can use different non-zero values to differentiate between different types of errors encountered. This exit code is passed back to the parent process, which stores it in the question character variable and can be accessed with $question character. Like in this example, if we've got this very simple script where we have hello world echo command, and the next command is exit 0. And we can find if we had some errors when running this code by typing echo $question mark. And if the exit command is called without an argument, then the script exits and passes the exit status of the last command executed to the parent process. So, to ensure that scripts are not easily disrupted by unexpected conditions, it is good practice to not make assumptions regarding input, such as command line arguments, user input, command substitutions, variable expansions, and file name expansions. Integrity checking can be performed by using Bash's test command. Like all commands, the test command produces an exit code upon completion, which is stored as the value of $question. To see the conclusion of a test, display the value of $question character immediately following the execution of the test command. Again, an exit status of 0 indicates the test succeeded, and non-zero values indicate the test failed. Tests are performed using a variety of operators. Operators can be used to determine if a number is greater than or equal to or less than or equal to, or even equal to another number. They can be used to test if a string of text is the same or not the same as another string of text. Operators can also be used to evaluate if a variable has a value or not. Let's take a look at some examples demonstrating the use of test command with the numeric comparison operators in Bash. As you can see, these two examples demonstrate the use of this command. Test 1 greater than 0 echo $question. And as you can see, it is true or a success. And if we type test 0 greater than 1, we'll get the result of 1, which is not true or unsuccess. Tests can be performed using the bash test command syntax in square brackets. They can also be performed using double square brackets, which has been available since bash version 2.02 and provides features such as glob pattern matching and regex pattern matching. Let's take a look at the following examples where we have a demonstration of test command syntax and numeric comparison operators of bash. So here is a bunch of examples with using numeric comparison operators and the results we get with them. Like 1 is equal to 1, 1 is not equal to 1, 8 greater than 2, 2 greater or even than 2, and 2 is less than 2. Now let's take a look at some string comparison operators. We can compare that ABC equals to ABC, or ABC is not equal to DEF, which is true. And the examples of some unary operators. Please note that the space characters inside the test brackets are mandatory because they separate the words and elements within the test expression. The shell's command parsing routine divides all command lines into words and operators by recognizing spaces and other meta characters using built-in parsing rules. And now some words about conditional structures. Simple shell scripts represent a collection of commands that are executed from beginning to end. Conditional structures allow users to incorporate decision-making into shell scripts so that certain portions of the script are executed only when certain conditions are met. And the simplest of the conditional structures in Bash is the if-then construct, which has the following syntax: if condition, semicolon, then statement, and encloses with fi command. This is that with this construct, if a given condition is met, one or more actions are taken. If the given condition is not met, then no action is taken. The numeric string and file tests previously demonstrated are frequently utilized by testing the condition in if-then statement. The fi or fi statement at the end closes the if-then construct. Let's take a look at the following code demonstrating the use of an if-then construct to start the PS account service if it is not active. We'll type systemctl is active PS account and redirect the result of this command to dev null, standard error or std error. Now let's type the following lines. If the result of previous command is not a 0 or a success, then sudo systemctl start PS account, followed by a fi command or fi. The if-then construct can be further expanded so that different sets of actions can be taken depending on whether a condition is met. This is accomplished with the if-then else construct. So we've got the structure like if condition, then statement, else statement, fi. Let's take a look at the following code demonstrating the use of if-then else statement to start the PS account service if it is not active and to stop it if it is active. We've got the same code as before, but here we are reading else statement and we want to stop it if it is started, if it is active. So else sudo systemctl stop PS account. And finally, using the if-then, elif, then, else construct. Lastly, the if-then else construct can be further expanded to test more than one condition, executing a different set of actions when a condition is met. Let's take a look at the following example of the construct with if-then, elif. So we've got if condition, then statement, elif condition, then statement, and else statement, followed by fi. And in this conditional structure, Bash tests the conditions in the order presented. When it finds a condition that is true, Bash executes the actions associated with the condition and then skips the remainder of the conditional structure. If none of the conditions are true, Bash executes the actions enumerated in the else clause. Let's take a look at the following code demonstrating the use of if-then, elif-then-else statement to run the MySQL client if the MariaDB service is active. Run the pSQL client if the PostgreSQL service is active, or run the SQLite 3 client if both the MariaDB and PostgreSQL service are not active. In this exercise, we'll use loops to efficiently print the host name from multiple servers. And after completing this exercise, we'll be able to create a for loop to iterate through a list of items from the command line and in a shell script. First, let's use the SSH and hostname commands to print the hostname of server 1 and server 2 to standard output. So we'll type SSH username, in my case it's Vagrant, add server 1 followed by hostname command, and the same for server 2. Now let's create a for loop to perform the same task more efficiently. We'll type for host in server 1, server 2, do SSH Vagrant add host variable and the command hostname, followed by done. Now let's create a shell script to execute the same for loop. Let's create the home Vagrant bin directory to contain the shell script. I'll type mkdir /bin. Now let's verify that the newly created directory is in our path environment variable. I'll type echo $path. Now let's create a shell script at home Vagrant bin with the name print hostname.sh to perform the for loop, and we'll use the cat command to verify the content of print hostname.sh. So first I'll type vim /bin print hostname.sh, add the necessary lines to the script. It's shebang bin bash, then the command, what the lines are doing, and then the script itself. For host in server 1, server 2, do SSH Vagrant at host and hostname. Done, and the command exit 0. After that, ensure that the newly created script is executable. I'll type change mode +x /bin print hostname.sh. And now we can run the script by typing print hostname.sh and verify that the exit code of our script is 0 by typing echo $? In this video, we'll take a look at how to use regular expressions and how to match text in command output with regular expressions. So after completing this video, you should be able to create regular expressions that match desired state. Apply regular expressions to text files using the grep command, and search files and data from piped commands using grep. So regular expressions provide a pattern matching mechanism that facilitates finding specific content. The vim, grep, and less commands can all use regular expressions. Programming languages such as Perl, Python, and C can use regular expressions when using pattern matching criteria. Regular expressions are a language of their own, which means they have their own syntax and rules. This video looks at the syntax used when creating regular expressions, as well as showing some regular expression examples. Now, the simplest regular expression is an exact match. An exact match is when the characters in the regular expression match the type and order in the data that is being searched. Suppose a user is looking through the following file looking for all occurrences of the pattern cat. Cat is an exact match of a C followed by an A followed by a T, with no other characters in between. Using cat is the regular expression to search the previous file returns the following matches. As you can see, regex found 5 matches, all the words containing this exact match. Now, we can match the start and end of a line. The previous example used an exact match regular expression on a file. Note that the regular expression would match the search string no matter where on the line it occurred, the beginning, end, or middle of the word or line. We can use a line anchor to control the location of where the regular expression looks for a match. So to search at the beginning of a line, use the caret character. To search at the end of a line, use the $sign. And using the same file as above, the caret character cat regular expression would match 2 words, starting with cat. The $cat regular expression would not find any matching words, because we don't have any word ending with cat. To locate lines in the file ending with dog, use that exact expression and an end of line anchor to create the regular expression $, and applying $, to the file would find 2 matches, dog and chili dog. Now, to locate the only word on a line, use both the beginning and end of line anchors. For example, to locate the word cat when it is the only word on a line, use caret character cat $character. We can add wildcards and multipliers to regular expressions. We can use a period or dot to match any single character with the exception of the new line character. A regular expression of C.T searches for a string that contains a C followed by any single character followed by a T. This example will match including cat, concatenate, vindication, C5T, and $T. And using an unrestricted wildcard, you cannot predict the character that would match the wildcard. To match specific characters, replace the unrestricted wildcard with acceptable characters, changing the regular expression to C in square brackets AOU followed by T, and it will match patterns that start with a C followed by either an A, O, or U followed by a T. Multipliers are a mechanism used often with wildcards. Multipliers apply to the previous character in the regular expression. One of the more common multipliers used is the asterisk or star character. When used in a regular expression, this multiplier means match 0 or more of the previous expression. You can use asterisk with expressions, not just characters. For example, C in square brackets AOU followed by asterisk T. Now, a regular expression of C dot asterisk T will match cat code calvert and even CT, 0 characters between the C and the T. Any data starting with a C, then 0 or more characters ending with a T. Another type of a multiplier would indicate the number of previous characters desired in the pattern. An example of using an explicit multiplier would be C dot backslash in curly brackets 2 backslash followed by T. This regular expression will match any word beginning with a C followed by exactly any 2 characters and ending with a T. And this regular expression would match two words in the example below, namely coat and cart. Please note that it is recommended practice to use single quotes to encapsulate the regular expression because they often contain shell meta characters such as dollar, asterisk, and curly brackets. This ensures that the characters are interpreted by the command and not by the shell. Now, let's take a look at some regular expressions options we can use. The period matches any single character. Question mark matches the preceding item is optional and will be matched at most once. Asterisk, the preceding item will be matched 0 or more times. Plus, the preceding item will be matched 1 or more times. A number in curly braces means that the preceding item is matched exactly this number of times, for example, 2 times. Number followed by comma means that the preceding item is matched this number of times or more time. Comma followed by number means that the preceding item is matched at most this number of times. So at most 2, for example. If we write 1, 2 means that the preceding item is matched at least 1 times, but not more than 2 times. We can match alphanumeric characters, all digits and all letters. We can also match all alphabetical characters, lower and uppercase. We can match blank characters, space and tab, control characters like delete, control, and so on. Digits, we can match graphical characters, lowercase letters, printable characters, punctuation characters, space characters, uppercase letters, hexadecimal digits. We can also match the empty string provided it is not at the edge of a word, match the empty string at the beginning of a word, at the end of word, white space, and non-white space. And this guided exercise will search for text in the system logs and the output of the commands in order to find information more efficiently. So first I'll use the sudo-i command to switch to the root user. Now I'll use the grep command to find the GID and UID for the postfix and post-drop groups and users. To reduce the output of the grep command, we can display all logs from a specific start time. So first we'll use the date command to determine the current date, and then use the grep command with the date, start time, and group ID options. So the command could look like this: grep, in single quotes, the date, followed by asterisk GID, and then the file var log secure. Now we can modify our regular expression to locate the first 2 messages in the var log mail log file. Please notice that in this search we are not using the caret character because we are not searching for the first character in a line. So the command could look like this: grep postfix var log mail log and piped to head-n2. Now let's find the name of the Q directory for the postfix server, and we'll search the etc postfix main.cf configuration file for all information about queries. And we'll use the -i option to ignore case distinctions. So we'll type grep -i q in single quotes and the file etc postfix main.cf. Now let's confirm that postfix is writing messages to var log messages file. We'll use the less command, then the / character to search this file. And Press N to move to the next entry that matches the search. And we'll use the Q key to quit the last command. Now we'll use the PSAUX command to confirm that the postfix server is currently running. And we can reduce the output of PS command by combining it with the grep command. So we'll type PSAUX pipe grep postfix. And the last example will confirm that the QMGR, cleanup, and pickup queues are correctly configured. We'll use the grep command with the -E option to match multiple entries in the same file. The configuration file is etc postfix master.cf. So we'll type grep-e qmanager qmgr -e pickup -e cleanup and the file etc postfix master.cf. And this will finish our guided exercise on using grep. The grep command, provided as part of the distribution, uses regular expressions to isolate matching data. The grep command provides a regular expression and a file on which the regular expression should be matched. Take a look at this example. I have a vocabulary file and let's grep compute, the word starting with compute with grep. So I'll type grep in quotes, in single quotes, caret compute and the file. Please note that it is recommended practice to use single quotes to encapsulate the regular expression because they often contain shell meta characters such as $, and curly brackets. This ensures that the characters are interpreted by grep and not by the shell. We can also use grep command in conjunction with other commands using a pipe operator. For example, PSAUX pipe grep chrony. Now let's take a look at some useful options for adjusting how grep uses the provided regular expression with data. -I will use the regular expression provided but not enforce case sensitivity. -V only displays lines that do not contain matches to the regular expression. -R will apply the search recursively. -E will use multiple options. Here we can supply multiple regular expressions. And of course there are many other options to grep. You can use the man page to research them. Now let's take a look at some grep examples. Regular expressions are case sensitive by default, and you can use the -I option with grep to run a case insensitive search. Let's open httpd.conf file with cat, and now let's use grep-i server root in this file in etc httpd conf httpd.conf, and it'll find server root regardless the case. Now, in cases where you know what you are not looking for, the -v option is very useful. The -v option only displays lines that do not match the regular expression. In this example, all lines, regardless of case, that do not contain the regular expression server are returned. Let's open this file with cat again, cat etc hosts, and let's look for server with grep-v-i server etc hosts. Now, to look at a file without being distracted by command lines, we can use the -v option again. In this example, the regular expression matches all lines that begin with a sharp or semicolon. These are typical characters that indicate the line will be interpreted as a command. Those lines are then omitted from the output. So let's open this file with cat again to see the file first. We'll type cat etc other types, And now let's grab this file with the following search. So we omit sharp and semicolon. We can use grep command with the -e option, which allows to search for more than one regular expression at a time. The following example, using a combination of less and grep, locates all occurrences of pam_unix, user, root, and accepted public key in the var log secure log file. So we'll type this long search query. We'll first cat the file with cat command, then pipe it to grep-e, looking for pam_unix. Then we'll add -e again, looking for user, root, and -e again, looking for accepted public key. And then pipe it to less command. Now to search for text in a file opened using vim or less, we can use the / character and type the pattern to find. So press enter to start the search, press N to find the next match. Try it with less var log messages and try to look for device. And again, to read more, you can find man pages on regex and grep commands. In this lab, you'll create a bash script that can filter and get relevant information from different hosts. And after completing this lab, you should be able to create a bash script and redirect its output to a file, use loops to simplify your code, and filter the relevant content using grep and regular expressions. So here are the steps you need to complete this lab. First, you need to create the bash script named bash-lab in your home directory, and then edit your newly created script to comply with the following requested information. And again, I remind you that your system needs to be configured to use SSH keys for authentication, and the password shouldn't be required. So the information you need to gather is as follows. You need to find host name and do it with the hostname-f command to get all the output. Then get all the output with echo command, the output with ls_cpu command, divide it again with echo command. Then you want to find the output from etc/se linux config file, ignoring lines starting with sharp. Again, divide this block with echo command and get all failed passwords entries from var log secure file. And again, divide it with echo command. Then you need to save the required information to the new files for server 1 and server 2. Here you can use sudo without requiring a password on server 1 and server 2 hosts. And remember to use a loop to simplify your script. You can also use multiple grep commands concatenated with the use of the pipe character. And again, if you have some troubles with solving this lab or you have some questions, further on I'll show step-by-step completion of this lab. So press pause here, complete the lab, and if you need some answers, watch this video further. So first off, we'll create a home directory, a directory in our home directory with mkdir-p home, your username, bin directory. Then we'll use vim to create and edit a script which is called bash-lab. So we'll type vim /bin bash-lab. Insert the text like this one, it's shebang bin bash, and save the file. And make sure the script file is executable. So for this we'll type change mode a+x bin bash-lab. Now let's edit the newly created script file to comply with the following requested information. we have to find host name, ls CPU, the information from SEL Linux config file, and the information from log secure file. So we'll open the script file again with vim by typing vim -bin bash-lab and add the following lines. User equals vagrant in my case, out equals home vagrant output. Then for SRV in server 1, server 2, do the following commands. SSH with user to server 1 and 2 and run the following command hostname-f and redirect this output to out SRV. Also we'll add the lscpu command followed by pipe grep --scpu CPU and redirect this again to this file out SRV. And the same we'll do for SE Linux config file and log secure file. We'll grep for $, so we are looking for $character to exclude it from our output. Also we want to exclude sharp character and redirect the output to this file. And lastly, we'll grab failed password in single quotes from log secure file and redirect it, append it to the file out SRV. And we'll close the script with done. Now run the script and review the output content on your server. You can do this with cat command by typing cat home your username output-server1 and the same step for server 2. So in this several videos we've learned how to create and execute simple bash scripts. We've learned how to use loops to iterate through a list of items from the command line and in a shell script, and how to search for text in log files and configuration files using regular expressions and grep. We continue with script building, and we already know how to create a new script and how to make it executable with the change mode command and +x parameter. Now, the echo command is used in script very often, and the echo command uses either double or single quotes to use text strings in scripts. If you use them within your string, you need to use one type of quote within the text and the other type to determine the string. Let's run the following script and see the results of this script. As you can see in this script, we are using both single quotation and double quotation. And we can use double quotes within the single quotes to determine the string within the text. Now, all of the quotation marks appear properly in this output, and we can add echo statement anywhere in our shell script where we want or need to display additional information. Let's say we want to display the date and who's logged on. So we'll type in our script echo the time and date are, then followed by date command, and then echo let's see who is logged into the system, followed by who command. So here we mix echo commands with the output of bash commands. And when we run the script, it produces the following output. It will show the text from echo command and the output from the commands date and who. Now, if we want to echo a text string on the same line as the command output, we can use the -n parameter for the echo statement, and the output will be as follows. We'll get the text followed by the output of the date command and the text from echo command followed by the output of who command. So as you get it, the echo command is a very crucial piece of shell scripts that interact with users. Now let's switch on to using variables in our scripts. You can display a complete set of active environment variables available by using the set command. So try typing set and you'll get the list. Now when you know some variables from the set command, you can use them in your script by typing variable's name preceded by a $sign. Take a look at this script where we are using the variables UID, home, and user. This user and UID and home environment variables are used to display the information about the logged-in user, and the output of this script should look like this. We'll get user info for user ID, UID, and home for this user. And as you can notice here, the environment variables in the echo commands are replaced by their current values when the script is run. Also notice that we were able to place the user variable within the double quotation marks in the first string, and that the shell script was still able to figure out that we want to use the variable. But be aware that whenever the script sees the $sign within quotes, it assumes you are referring to a variable. So be aware of using $sign inside of the quotes. And if you want to use the $character or $sign, you must precede it with a / character so that the interpreter doesn't see it as a variable. We can also use user variable besides to the environment variable. You can set your own variable within the script. It will allow you to temporarily store data and use it throughout the script, making the shell script more like a real program, real application. User variables can be any text string of up to 20 letters, digits, or underscore characters. User variables are case sensitive, so make sure you remember the case when declaring the variables. Values are assigned to user variables using an equal sign. No spaces can appear between the variable, the equal sign, and the value. Here are some examples of variables. var1 equals 10, var2 equals minus 57, var3 equals testing, var4 is equivalent to a string. The shell script stores all variables values as text strings. It's up to the individual commands in the shell to determine the data type used for the variable value. Variables defined within the shell, their values throughout the life of the shell script, but they are deleted when the shell script completes. And just like system variables, user variables can be referenced using the $sign. So we could type the following in the script referring to the variables we've just declared in the previous step. Each time the variable is referenced, it produces the value currently assigned to it. It's important to remember that when referencing a variable value, you use the $sign. But when referencing the variable to assign a value to it, you do not use the $sign. And here is an example. When you use the value of the value1 variable in the assignment statement, you must still use the $sign. If you forget the $sign and make the value2 assignment line look like this, value2 equals value1, you'll get the following output. The resulting value is value1 instead of 10. Without the $sign, the shell interprets the variable name as a normal text string, which is most likely not what you wanted. Now we can use command substitution in our scripts, and it's one of the most useful features of shell scripts. It's the ability to extract information from the output of a command and assign it to a variable. Once assigned the output to a variable, you can use that value anywhere in your script. It is very useful when you're processing data in your scripts. And there are two ways to assign the output of a command to a variable. You can use the backtick character and the dollar brackets format. And people use this second format more often. It is more convenient to use. For example, you could type testing equals $date command in brackets, and the shell runs the command within the command substitution characters and assigns the output to the variable testing. Please notice that there are no any spaces between the assignment equal sign and the command substitution character. Here the variable testing receives the output from the date command and it is used in the echo statement to display it. And running the shell script produces the following output. The date and time are and your current date and time. And of course, once you get this command output in your variable, you can do anything with this variable. Here is a popular example of how command substitution is used to capture the current date and use it to create a unique file name in a script. You can use the today variable to be assigned to the output of a formatted date command. This is a common technique used to extract date information for log names. The +%year %m %d format instructs the date command to display the date as a 2-digit year, month, and date. The script assigns the value to a variable which is then used as part of a file name. The file itself contains the redirected output of a directory listing, and after running the script you should see a new file in your directory with the current date appended, and it's very useful. The log file appears in the directory using the value of the today variable as part of the file name. The contents of the log file are the directory listing from the USR bin directory. If the script is run the next day, the log file name will be the date of the next day, thus creating a new file for the new day. Another useful feature for building your scripts is redirecting input and output. There are times when you'd like to save the output from a command instead of just having it displayed in your shell on the monitor. As you remember, we can redirect it with the greater than symbol. So we can redirect the command's output with greater than symbol to the, let's say, some text file. And anything that would appear on the monitor from the command instead is stored in the output file specified. For example, we can redirect the output from the date command or the output from the who command and then display it with a cat command. Now the contents of the test file contain the output from the who command, and sometimes instead of overwriting the file we can append the data to this file. As you remember, we could type the date command and double greater than symbol, and it'll append the output from the date command to this file. And of course we can use also input redirection. It's the opposite of output redirection. Instead of taking the output of a command and redirecting it to a file, we can input redirection the content of a file to a command. And it is used with symbol less than. So we could type a command less than and followed by the input file. For example, we could type wc input from test 6. Here the WC command provides a count of text in the data, and by default it produces three values: the number of lines in the text, the number of words in the text, and the number of bytes in the text. And by redirecting a text file to the WC command, you can get a quick count of the lines, words, and bytes in the file. So maybe the pronunciation of this command would be better word count, not WC. Besides the redirection, input redirection from the file, you could use the inline input redirection. This method allows you to specify the data from input redirection on the command line instead of from a file. And the symbol for inline input redirection is double less than symbol. Besides this symbol, you must specify a text marker that separates the beginning and the end of the data used for input. You can use any string value for the text marker, but it must be the same at the beginning of the data and the end of the data. So here is an example for the input redirection, inline input redirection. When using this inline input redirection on the command line, the shell will prompt for data using the secondary prompt, defined in the PS2 environment variable. And here is how this looks when you use it. Let's say we use word count command, double less than symbol, the marker, EOF abbreviation, then the input itself. Let's say we have three strings, like test string 1, test string 2, and 3. And then the end of the text marker. We show the end of the data. And of course, the secondary prompt continues to prompt for more data until you enter this string value for the text marker. And when you do, the word count command will get the input and process it. As you might remember, the most basic type of structured command is the if-then statement. Let's take a look at several examples using this statement. In this first example, this script uses the pwd command on the if line, and if the command completes successfully, the echo statement should display the text string. In this script, the shell ran the pwd command listed on the if line. Because the exit status was 0, it also executed the echo statement listed in the then section. In the next example, we deliberately used a non-existent command in the if statement line. Because this is not correct command, it produces an exit status that's not non-zero. Thus, the bash shell skips the echo statement in the then section. Also notice that the error message generated from running the command in the if statement will appear in the script's output. We'll discuss later how to avoid this error message output if we don't want it to appear. Of course, you are not limited to just one command in the then section. You can list commands just as you do in the rest of the shell script. The bash shell treats the commands as a block, executing all of them when the command in the if statement line returns a 0 exit status, or skipping all of them when the command returns a non-zero exit status. Now, the if statement here uses the grep command to search the etc password file to see if a specific username is currently used on the system. If there is a user with that logon name, the script displays some text and then lists the bash script in the user's home directory. However, if you set the test user variable to a user that does not exist on the system, nothing within the then code block executes. And of course, it would be nice if we would display a little message saying that the username wasn't found on the system. And in this case, we can use another feature of the if-then statement. And it's the if-then-else statement. In the if-then statement, you have only one option for whether a command is successful, and if the command returns a non-zero exit status code, the bash shell just moves on and runs the next command in the script. In this situation, it would be good to be able to execute an alternative set of commands. That's exactly what the if-then-else statement is for. This structure provides another group of commands in the statement. If command, then commands, else commands, ended with fee. When the command in the if statement line returns with a zero exit status code, the commands listed in the then section are executed, just as in normal if-then statement. But when the command in the if statement line returns a non-zero exit status code, the bash shell executes the commands in the else section. And you can see in this example that just like the then section, the else section can contain multiple commands, and the fee statement finishes the end of the else statement. We can nest ifs, because sometimes you must check for several situations in your script code. For these situations, you can nest the if-then statements. And to check if a logon name is not in the etc password name and yet a directory for that user still exists, we can use a nested if-then statement. In this case, the nested if-then statement is within the primary if-then-else statements, else code. And in this case, the script correctly will find that although the login name has been removed from the etc password file, the user's directory is still on the system. But the problem with using this manner of nested if-then statements in a script is that the code can get hard to read and the logic flow becomes difficult to follow. And instead of having to write separate if-then statements, you can use an alternative version of the else section called elif. The elif continues an else section with another if-then statement. The elif statement line provides another command to evaluate, similar to the original if statement line. If the exit status code from the elif command is 0, bash executes the commands in the second then statement section. Using this method of nesting provides cleaner code with an easier to follow logic flow. But the problem with this script is that if the account is gone as well as the directory, you get no notifications of these facts. You can fix this problem and even take the script a step further by having it checked for both a non-existent user with a directory and a non-existent user without a directory. You accomplish this by adding an else statement within the nested elif. And before the home no such user directory was removed and the test script executed, the elif statement, a zero exit status was returned. Thus, the statements within the elif's then code block were executed. After the home no such user directory was removed, a non-zero exit status was returned for the elif statement. This caused the statements in the elif block within the elif block to be executed. And of course you can continue to string elif statements together, gathering one huge if-then-elif structure. Each block of commands is executed depending on which command returns the zero exit status code. Remember that the bash shell executes the if statements in order, and only the first one that returns a zero exit status results in the then section being executed. Even though the code looks cleaner with elif statements, it still can be confusing to follow the script's logic. Later we'll see how to use the case command instead of having to nest lots of if-then statements. The test command provides a way to test different conditions in an if-then statement. If the condition listed in the test command evaluates to true, the test command exits with a zero exit status code. This makes the if-then statement behave in much the same way that if-then statement work in other programming languages. If the condition is false, the test command exits with a non-zero exit status code, which causes the if-then statement to exit. The format for test command is pretty simple. Test condition. The condition is a series of parameters and values that the test command evaluates. When used in an if-then statement, the test command looks like this: if test, condition, then commands fee. If you leave out the condition portion of the test command statement, it exits with a non-zero exit status code, or false, and triggers any else block statements. Take a look at this example. If test, then echo, else echo fee. When you add in a condition, it is tested by the test command. For example, using the test command, you can determine whether a variable has content. A simple condition expression is needed to determine whether a variable has content. Here, the variable myVariable contains content full, so when the test command checks the condition, the exit status returns a 0. This triggers the statement in the then code block. And as you would suspect, the opposite occurs when the variable does not contain content. The bash shell provides an alternative way of testing a condition without declaring the test command, and it can be used in if-then statement. If condition is in square brackets, then commands fee. The square brackets define the test condition. Be careful, you must have a space after the first bracket and a space before the last bracket, or you'll get an error message. The test command and test conditions can evaluate three cases of conditions: numeric comparisons, string comparisons, and file comparisons. The next part of the video describes how to use each of these test classes in your if-then statements. So first, let's see how to use numeric comparison. The most common test evaluation method is to perform a comparison of two numeric values. And here we've got first value equal to the second value, greater than or equal to, greater than, less than or equal to, less than, and is not equal to. The numeric test conditions can be used to evaluate both numbers and variables. Take a look at this example. The first test condition, if variable value 1 is greater than 5, will test if the value of the variable value 1 is greater than 5. The second test condition, if variable value 1 is equal to variable value 2, it will test if the value of variable 1 is equal to the value of the variable value 2, and both numeric test conditions evaluate as expected. Another type of comparisons is using string comparison. Test conditions also allow you to perform comparisons on string values. And here we can evaluate two string values. For example, we can check if string 1 is the same as string 2. We can check if string 1 is not the same, is less than or greater than the string 2. Or we can check if string 1 has a length greater than 0, or we can check if string 1 has a length of 0. So the equal and not equal conditions are fairly self-explanatory with strings. It's pretty easy to know whether two strings values are the same or not. Also, using the not equal string comparison allows you to determine whether or not two strings have the same value. And also keep in mind that the test comparison takes all punctuation and capitalization into account when comparing strings for equality. Now, trying to determine if one string is less than or greater than another is where things start getting tricky. Two problems often appear when we are trying to use the greater than or less than features to test conditions. The greater than and less than symbols must be escaped, or the shell uses them as redirection symbols, with a string value as file names. And another trick is that the greater than and less than order is not the same as that used with the sort command. The first item can result in a huge problem that often goes undetected when programming your scripts. There is an example of what sometimes happens to beginners. Take a look at this example. By just using the greater than symbol itself in the script, no errors are generated, but the results are wrong. The script interpreted the greater than symbol as an output redirection. Thus, it created a file called Zorp Football. Because the redirection completed successfully, the test condition returns a zero exit status code, which the if statement evaluates as though strings completed successfully. To fix this program, you need to properly escape the greater than symbol using the backslash, like in this example. Now that answer is more along the lines of what you would expect from the string comparison. The second issue is a little more subtle, and you may not even run across it unless you are working with uppercase and lowercase letters. The sort command handles uppercase letters opposite to the way the test conditions consider them. Take a look at this example. Capitalized letters are treated as less than lowercase letters in test comparisons. However, the sort command does the opposite. When you put the same strings in a file and use the sort command, the lowercase letters appear first. This is due to different ordering techniques. Tag comparisons use standard Unicode ordering, using each character's Unicode number or numeric value to determine the sort order. The sort command uses the sorting order defined for the system local language settings. For the English language, the local settings specify that lowercase letters appear before uppercase letters in sorted order. Now let's move on and take a look at string size. The -n and -z comparisons are handy when you are trying to evaluate whether a variable contains data. This example creates two string variables, the string1 variable containing a string and the string2 variable is created as an empty string. The following comparisons are made. If -n variable string1, this code determines whether the string1 variable is non-zero in the length, which it is, so its then section is processed. So it contains a non-zero length. Next, we have if-z string2 variable, and this code determines whether the string2 variable is 0 in length, which it is. So its then section is processed. And next we have -z string3 variable in if statement, and this code determines whether the string3 variable is a 0 in length. This variable was never defined in the shell script, so it indicates that the string length is still 0, even though it wasn't defined. Please be careful with empty and uninitialized variables, because they can have very bad effect on your shell script tests. One more category of test comparisons includes quite possibly the most powerful and most used comparisons in shell scripting. This category allows you to test the status of files and directories on the Linux file system. We can use the following comparisons. -d followed by file checks if file exists and is a directory. -e checks if file exists. -f checks if file exists and is a file. -r file exists and is readable. -s file exists and is not empty. -w file exists and is writable. -x file exists and is executable. -O will check if file exists and is owned by the current user. -G will check if file exists and the default group is the same as the current user. And also we've got file -nt, we can compare file 1 -nt, file 2. It will check if file 1 is newer than file 2. And finally, file 1 -ot, file 2. It will check if file 1 is older than file 2. These conditions give you the ability to check file system files within shell scripts. They are often used in scripts that access files. Because they are used so often, let's look at each of these comparison. So the first example, the -d test condition checks to see if the jump directory variable directory exists. If it does, it proceeds to use the cd command to change to the current directory and performs a directory listing. If it does not, the script emits a warning message and exits the script. The next example is checking whether an object exists. The -e comparison allows you to check if either a file or directory object exists before you attempt to use it in your script. In this script, the first check uses the -e comparison to determine whether the user has a home directory. If so, the next -e comparison checks and determines whether the Centine1 file exists in the home directory. If the file doesn't exist, the shell script notes that the file is missing and that here is nothing to update. And if this file exists, when the conditions are tested, both the home and the Centine1 file are found and the current date and time is appended to the file. The next example is checking for a file. The -e comparison works for both files and directories. To ensure that the object specified is a file and not a directory, you must use the -f comparison. So in this example, first the script uses the -e comparison to test whether home variable exists. If it does, it uses the -f to test whether it's a file. If it's not a file, a message is displayed stating that it is a directory. If you modify the variable object name, replacing the directory home with a file, for example home/Centine1, it will cause a different outcome. Now when the script is run, the -f test on home Centine1 exists with a 0 status, triggering the then statement, which in turn inputs the message that Centine1 is a file. The next example is checking for read access. Before trying to read data from a file, it's usually a good idea to test whether you can read from file first. You do this with the -r comparison. And in this example, the etc shadow file contains the encrypted passwords for system users. So it's not readable by normal users on the system. The -r comparison determined that read access to the file wasn't allowed, so the test command failed and the bash shell executed the else section of the if-then statement. Next on is checking for empty files. In this example, we use -s comparison to check whether a file is empty, especially if you don't want to remove a non-empty file. Be careful because when the -s comparison succeeds, it indicates that a file has data in it. So here, first the -f comparison tests whether the file exists. If it does exist, the -s comparison is triggered to determine whether the file is empty. An empty file will be deleted. You can see from the ls-sh command that the file which you've used in this example, Centine1, is not empty, and therefore the script does not delete it. In the next example, we'll check whether you can write to a file. The -w comparison determines whether you have permission to write to a file. The can I write to it.sh script is simply an update of the previous script. But now instead of checking if you can read the item name file, this script checks to see whether you have permissions to write to the file. And here the item_name variable is set to home/Centine1, and this file allows user write access. Thus, when the script is run, the -w test expression returns a non-zero exit status, and the then code block is executed, which writes a timestamp into the Centine1 file. When the Centine1 file user's write access is removed via change mode, the -w test expression returns a non-zero status, and a timestamp is not written to the file. The change mode command could be used again to grant the write permission back for the user. This would make the write test expression return a zero exit status and allow a write attempt to the file. The next example is for checking whether you can run a file. The -x comparison is a handy way to determine whether you have execute permission for a specific file. Although this may not be needed for most commands, if you run lots of scripts from your shell scripts, it could be useful. And in this example, shell script uses the -x comparison to test whether you have permission to execute the can I write to it.sh script. If so, it runs the script. After successfully running the script the first time, the permissions were changed. And this time the -x comparison failed because the execute permission had been removed from this script. So you could experiment with change mode command and this -x comparison. Another useful comparison is for checking ownership, and this example is using the -o comparison, which allows you to easily test whether you are the owner of a file. And here the script uses the -o comparison to test whether the user running the script is the owner of the etc password file. The script is run under a user account other than root, so the test fails. The next example is for checking default group membership. The -G comparison checks the group of a file, and it succeeds if it matches the default group for the user. This can be somewhat confusing because the -G comparison checks only the script user's default group and not all the groups to which the user belongs. So here is an example. Next up we have checking file date comparison. It's the last set of comparisons deal with comparing the creation times of two files. This comes in handy when writing scripts to install software. Sometimes you don't want to install a file that is older than a file already installed on the system. The -nt comparison determines whether a file is newer than another file. If a file is newer, it has a more recent file creation time. The -ot comparison determines whether a file is older than another file. If the file is older, it has an older file creation time. And this example demonstrates that if one of the files does not exist, the -nt comparison returns incorrect information. It's imperative to ensure that the file exists before trying to use them in the -nt or -ot comparison. The if-then statement allows you to use Boolean logic to combine tests. You can use these two Boolean operators, condition1, two ampersands, condition2, each condition in square brackets. And the second operator is two pipes, so condition1 in square brackets, two pipes, condition2. The first Boolean operation uses the AND Boolean operator to combine two conditions. Both conditions must be met for the then section to execute. Please note that Boolean logic is a method that reduces potential returned values to either true or false. The second Boolean operation uses the OR Boolean operator to combine two conditions. If either condition evaluates to a true condition, the then section is executed. The following example shows the AND Boolean operator in use. Using the AND Boolean operator, both of the comparisons must be met. The first comparison checks to see if the home directory exists for the user. The second comparison checks to see if there is a file called new file in the user's home directory, and if the user has right permissions for the file, and if either of these comparisons fails, the if statement fails and the shell executes the else section. If both of the comparisons succeed, the if statement succeeds, and the shell executes the then section. Now, there are three additions to the bash shell providing advanced features that you can use in if-then statements. The first one is that single parenthesis for running the command in a subshell. The second addition is that double parenthesis for the mathematical expression. And the third one is that double square brackets for advanced string handling functions. Let's take a look at each of these features in more detail. So the first one is using single parentheses. Single parentheses allow you to use subshells in your if statement comparisons. So this is the format of the single parentheses test command. Before the bash shell executes the command, it creates a subshell in which to run the command. If the command completes its task successfully, the exit status is set to 0, and the commands listed under the then section are executed. If the exit status of the command is anything else, the then commands aren't executed. Here is a script to test using subshells. When the script runs the echo $bash_subshell command the first time prior to the if statement, it completes the operation within the current shell. The command displays a 0 indicating there is no subshell in use. Within the if statement, the script performs the command in a subshell, and the echo $bash_subshell command shows a 1, indicating a subshell was used. This subshell operation completes successfully, triggering the then command. As a warning here that while you can use process lists within the if test statement, unexpected results may occur. If all the process lists commands fail except the last command, the subshell will set the exit status to 0, and the commands listed under the then section will run. Now, if we modify the script slightly, we'll get an example of an unexpected command run in a subshell. Because the subshell command contained an incorrect file name in its operation, the exit status was not set to 0. Thus, the else command was triggered instead of the then command. And we move on to using double parentheses. The double parentheses command allows you to incorporate advanced mathematical formulas in your comparisons. The test command allows for only simple arithmetic operations in the comparison. The double parentheses command provides more mathematical symbols which programmers who have used other programming languages may be familiar with using. There is the format of the double parentheses command. Here the expression term can be any mathematical assignment or comparison expression. Besides the standard mathematical operators that the test command uses, the additional operators are available for use in the double parentheses command. Take a look at this table with the double parentheses command symbols. As you can see, there is post-incremental symbol, post-decrement, pre-increment, pre-decrement, logical negation, bitwise negation, exponential, left bitwise shift, right bitwise shift, bitwise boolean AND, bitwise boolean OR, and logical AND and logical OR. You can use double parentheses command in an if statement, as well as in a normal command in the script for assigning values. Take a look at this example and notice that you don't need to escape the greater than symbol in the expression within the double parentheses. This is yet another advanced feature besides the double parentheses command. And lastly, using double brackets. The double bracket command provided advanced feature for string comparisons. Here is the double bracket command format. The double bracketed expression uses the standard string comparison used in the test evaluations. However, it provides an additional feature that the test evaluations don't pattern matching. Please note that double brackets work fine in the bash shell. Be aware, however, that not all shells support double brackets. In pattern matching, you can define a regular expression that's matched against the string value. Take a look at this example and notice in the script that double equal signs are used. These double equal signs designate the string to the right, 5 dot asterisk in parentheses, as a pattern, and pattern matching rules are applied. The double bracket command matches the $bash_version environment variable to use whether it starts with a 5 string. If so, the comparison succeeds and the shell executes the then section command. Oftentimes you'll find yourself trying to evaluate a variable's value, looking for a specific value within a set of possible values. In this scenario, you'll end up having to write a lengthy if-then-else statement like this. The elif statement continues the if-then checking, looking for a specific value for the single comparison variable. Instead of having to write all the elif statements to continue checking the same variable value, you can use the case command. The case command checks multiple values for a single variable in a list-oriented format. The syntax is as follows: case variable in pattern 1, pattern 2, followed by commands. Then we have pattern 3, commands 2, default commands, and we close case by typing ESAC. The case command compares the variable specified against the different patterns. If the variable matches the pattern, the shell executes the command specified in the pattern. You can list more than one pattern in a line using the bar operator to separate the patterns. The asterisk symbol is the catch-all for values that don't match any of the listed patterns. Here is an example of covering the if-then-else program to using the case command. In this example, the case command provides a much cleaner way of specifying the various options for each possible variable value. Now, let's describe a script that puts the structure commands we've covered in this set of videos to a practical use, determining what package managers are available in the current system. It also takes a guess on which Linux distribution the current system is based, using the installed package managers as a guide. For its analysis, the script first checks for standard Red Hat-based package managers like RPM, DNF, and Flatpak. It uses the which command for each package manager and uses single parentheses in the if condition statement. If the package manager is found, a special Boolean variable for that particular manager is set to true or 1. And if not found, it is set to false or 0, as shown snipped here. There is special handling for DNF and UM, in case you are running the script on an older Red Hat-based distro that does not yet have the DNF utility. Notice that an elif statement is employed to check for UM if DNF is not found. Please note that output redirection is used after the which command within the single parentheses. Building off what was covered in these previous videos, regular or standard output and any error messages from the which command are redirected via the ampersand greater than symbols. They go to dev null, which is also humorously called the black hole, because things put into it never come out. This action cleans up the script's output significantly, but does not adversely affect its integrity. We'll talk about error redirection a bit more later on. So after the script finishes its package manager analysis of the system, it calculates a score, Red Hat score, which this score is used later to make a guess concerning this system's distribution base. And when the Red Hat Package Manager audit is completed, a Debian analysis starts. It is very similar to the Red Hat assessment, except it covers Debian package managers like DPKG, APT, Snap, and determines a Debian score, shown snipped here. The two scores, Red Hat score and Debian score, are compared and a distribution determination is declared. So take a look at the entire script, pause here to learn it more carefully, and as you read through, think of different ways to accomplish these tasks using modified if-then statements or even case structures, getting your creativity as part of learning. Previously, you saw how to manipulate the flow of a shell script program by checking the output of commands and the values of variables. Next up, we'll continue to look at structured commands that control the flow of your shell scripts. You'll see how to perform repeating processes, commands that can loop through a set of commands until an individual condition has been met. Now let's take a look at the demonstration of the for, while, and until bash shell looping commands. We'll start with the for command. Iterating through a series of commands is common programming practice, so often you need to repeat a set of commands until a specific condition has been met, such as processing all the files in a directory, all the users on a system, or all the lines in a text file. The bash shell provides the for command to allow you to create a loop that iterates through a series of values. Each iteration performs a defined set of commands using one of the values in the series. Take a look at this basic format of the bash shell for command. As you can see, for var in list do commands, followed by done. So you supply the series of values used in the iterations in the list parameter. You can specify the values in the list in several ways. In each iteration, the variable var contains the current value in the list. The first iteration uses the first item in the list. The second iteration, the second item, and so on, until all the items in the list have been used. The commands entered between the do and done statements can be one or more standard bash shell commands. Within the commands, the var variable contains the current list item value for the iteration. Please note that if you prefer, you can include the do statement on the same line as the for statement, but you must separate it from the list items using a semicolon, like for var in list semicolon do. We mentioned that there are several ways to specify the values in the list. Let's take a look at the various ways. So we can read values in a list. The most basic use of the for command is to iterate through a list of values defined within the for command itself, like in this example. Each time the for command iterates through the list of values provided, it assigns the test variable the next value in the list. The test variable can be used just like any other script variable within the for command statements. After the last iteration, the test variable remains valid throughout the remainder of the shell script. It returns the last iteration value unless you change its value. Take a look at this example. Here the test variable retained its value and allows us to change the value and to use it outside of the for command loop, as any other variable would. We can also read complex values in a list. things aren't always as easy as they seem with the for loop. There are times when you run into data that causes problems. Here is a classic example of what can cause problems for shell script programmers. Here the shell saw the single quotation marks within the list values and attempted to use them to define a single data value. And it really messed things up in the process. We have two ways to solve this problem. You can use the escape character, the backslash, to escape the single quotation mark. And you can use double quotation marks to define the values that use single quotation marks. Neither solution is all that fantastic, but each one helps solve the problem. In this first problem value, you added the backslash character to escape the single quotation mark in the don't value. In the second problem value, you enclosed the this will value in double quotation marks. Both methods worked fine to distinguish the value. Another problem you may run into is multi-word values. Remember that the for loop assumes that each value is separated with a space, and if you have data values that contain spaces, you run into another problem. Take a look at this example. Here the for command separates each value from the others in the list with a space. If there are spaces in the individual data values, you must accommodate them using double quotation marks. Now the for command can properly distinguish between the different values. Also notice that when you use double quotation marks around a value, the shell does not include the quotation marks as part of the value. Now we can also read a list from a variable. Often what happens in a shell script is that you accumulate a list of values stored in a variable and then need to iterate through the list. You can do this using the for command as well. Like in this example, the list variable contains the standard text list of values to use the iterations. Notice that the code also uses another assignment statement to add or concatenate an item to the existing list contained in the list variable. This is a common method for adding text to the end of an existing text string stored in a variable. Now we can also read values from a command. It's another way to generate values for inclusion in the list is to use the output of a command. You use command substitution to execute any command that produces output and then use the output of the command in the for command. Like in this example. This example uses the cat command in the command substitution to display the contents of the file states.txt. Notice that the states.txt file includes each state on a separate line, not separated by spaces. The for command still iterates through the output of the cat command one line at a time, assuming that each state is on a separate line. However, this does not solve the problem of having spaces in data. If you list a state with a space in it, the for command still takes each word as a separate value. There is a reason for this, which we look at later on. Please note that this example code assigned the file name to the variable using just the file name without a path. This requires that the file be in the same directory as the script. If this isn't the case, you need to use a full path name, either absolute or relative, to reference the file location. We continue with looping with the for statement, and now some words about changing the field separator. The cause of the problem is the special environment variable IFS, the internal field separator. The IFS environment variable defines a list of characters the bash shell uses as field separator. So by default, the bash shell considers the following characters as field separator: a space, a tab, and a new line. If the bash shell sees any of these characters in the data, it assumes that you are starting a new data field in the list. When working with the data that can contain spaces, such as file names, this can be annoying, as you saw in the previous script example. To solve this problem, you can temporarily change the IFS environment variable values in your shell script to restrict the characters the bash shell recognizes as field separators. For example, if you want to change the IFS value to recognize only the new line character, you need to do this: IFS equals $ single quote \n single quote. Adding this statement to your script tells the bash shell to ignore spaces and tabs in data values. Applying these techniques to the previous script yields the following. Take a look at this example. Now the shell script can use values in the list that contain spaces. As a warning here that when working on long scripts, you may change the IFS value in one place and then forget about it and assume the default value elsewhere in the script. A safe practice to get into is to save the original IFS value before changing it and then restore it when you are finished. This technique can be coded like this: ifs.out equals $ifs followed by ifs equals $ single quote \n single quote, and we can use the new IFS value in code by typing ifs equals $ifs.out. This ensures that the IFS value is returned to the default value for future operations within the script. Now, other excellent applications of the IFS environment variable are possible. Suppose you want to iterate through values in a file that are separated by a colon, such as in the etc password file. You just need to set the IFS value to a colon by typing ifs equals colon. If you want to specify more than one IFS character, just string them together on the assignment line, like typing ifs equals $ single quote \n single quote colon semicolon double quotation. This assignment uses the new line, colon, semicolon, and double quotation mark characters as field separators. There is no limit to how you can parse your data using the IFS characters. Next up, we'll talk about reading a directory using wildcards. Finally, you can use the for command to automatically iterate through a directory of files. To do this, you must use a wildcard character in the field or path name. This forces the shell to use file globbing. File globbing is a process of producing file names or path names that match a specified wildcard character. This feature is great for processing files in a directory when you don't know all the file names. Take a look at this example. Here the for command iterates through the results of the home reach test, followed by wildcard listing. The code tests each entry using the test command, using the square bracket method, to see if it is a directory using the -d parameter or a file using the -f parameter. Notice in this example that we did something different in the if statement tests. We typed if in square brackets -d and in double quotation $file. In Linux, it's perfectly legal to have directory and file names that contain spaces. To accommodate that, you should enclose the file variable in double quotation marks. If you don't, you'll get an error if you run into a directory or file name that contains spaces. The bash shell interprets the additional words as arguments within the test command, causing an error. You can also combine both the directory search method and the list method in the same for statement by listing a series of directory wildcards in the for command, as in this example. Here the for statement first uses file globin to iterate through the list of files that result from the wildcard character. Then it iterates through the next file in the list. You can combine any number of wildcard entries in the list to iterate through. As a warning here, notice that you can enter anything in the list data, even if the file or directory does not exist. The for statement attempts to process whatever you place in the list. This can be a problem when you are working with files and directories. You have no way of knowing if you are trying to iterate through a non-existent directory or non-existent files. It's always a good idea to test each file or directory before trying to process it. Now, sometimes you can encounter the C style for command used in bash scripts, and you can use the C style for command by yourself. In the C language, a for loop normally defines a variable which it then iterates automatically during each iteration. Typically, programmers use this variable as a counter and either increment or decrement the counter by 1 in each iteration. The bash for command can also provide this functionality. Let's take a look at how you use a C-style for command in a bash shell script. The C language for command has a method for specifying a variable, a condition that must remain true for the iterations to continue, and a method for altering the variable for each iteration. When the specified condition becomes false, the for loop stops. The condition equation is defined using standard mathematical symbols. For example, consider the following C language code. This code produces a simple iteration loop where the variable I is used as a counter. The first section assigns a default value to the variable. The middle section defines the condition under which the loop will iterate. When the defined condition becomes false, the for loop stops iterations. The last section defines the iteration process. After each iteration, the expression defined in the last section is executed. In this example, the I variable is incremented by 1 after each iteration. The bash shell also supports a version of the for loop that looks similar to the C-style for loop, although it does have some differences, including a couple of things that will confuse shell script programmers. Here is the basic format of the C-style bash for loop. The format of the C-style for loop can be confusing for bash shell script programmers because it uses C-style variable references instead of the shell-style variable references. Here is what a C-style for command looks like. Notice that there are a couple of things that don't follow the standard bash shell for method, and they are the assignment of the variable value can contain spaces. The variable in the condition isn't preceded with a $sign, and the equation for the iteration process does not use the expr command format. The shell developers created this format to more closely resemble the C-style for command. Although this is great for C programmers, it can throw even expert shell programmers into confusion Be careful when using the C-style for loop in your scripts. Here is an example of using the C-style for command in a bash shell program. Here the for loop iterates through the commands using the variable defined in the for loop, the letter I in this example. In each iteration, the I variable contains the value assigned in the for loop. After each iteration, the loop iteration process is applied to the variable, which in this example increments the variable by 1. And finally, some words about using multiple variables. The C-style for command also allows you to use multiple variables for the iteration. The loop handles each variable separately, allowing you to define a different iteration process for each variable. Although you can have multiple variables, you can define only one condition in the for loop. Take a look at this example. Here the A and B variables are each initialized with different values and different iteration processes defined. While the loop increases the A variable, it decreases the B variable for each iteration. Next up, we'll be talking about exploring the while command. I'll see you there. The while command is somewhat of a cross between the if-then statement and the for loop. The while command allows you to define a command to test and then loop through a set of commands for as long as the defined test command returns a zero exit status. It tests the test command at the start of each iteration. When the test command returns a non-zero exit status, the while command stops executing the set of commands. Take a look at the basic while format. Here is the format of the while command. So you type while, test command, do, other commands, done. The test command defined in the while command is the exact same format as in if-then statement. As in the if-then statement, you can use any normal bash shell command, or you can use the test command to test the conditions, such as variable values. The key to the while command is that the exit status of the test command specified must change based on the commands run during the loop. If the exit status never changes, the while loop will get stuck in an infinite loop. The most common use of the test command is to use brackets to check the value of a shell variable that's used in the loop commands. Take a look at this example. Here the while command defines the test condition to check for each iteration. While, in square brackets, var1 variable dash greater than 0. As long as the test condition is true, the while command continues to loop through the commands defined. Within the commands, the variable used in the test condition must be modified. You'll have an infinite loop. In this example, we use shell arithmetic to decrease the variable value by 1. var1 equals $square brackets var1 variable minus 1. The while loop stops when the test condition is no longer true. We can use multiple test conditions. The while command allows you to define these multiple test conditions, commands, on the while statement line. Only the exit status of the last test command is used to determine when the loop stops. This can cause some interesting results if you are not careful. Here is an example. Please pay close attention to what happened in this example. Two test commands were defined in the while statement. While echo variable1 variable, in square brackets var1 greater or equal to 0. The first test simply displays the current value of the var1 variable. The second test uses brackets to determine the value of the var1 variable. Inside the loop, an echo statement displays a simple message, indicating that the loop was processed. Notice when you run the example how the output ends. This is inside the loop, -1. The while loop executes the echo statement when the var1 variable was equal to 0 and then decreased the var1 variable value. The test commands were then executed for the next iteration. The echo test command was executed displaying the value of the var1 variable, which is now less than 0. It's not until the shell executes the test command that the while loop terminates. This demonstrates that in a multi-command while statement, all the test commands are executed in each iteration, including the last iteration when the last test command fails. Be careful of this. Another thing to be careful of is how you specify the multiple test commands. Note that each test command is on a separate line. Now some words about using the until command. The until command works in exactly the opposite way for the while command. The until command requires that you specify a test command that normally produces a non-zero exit status. As long as the exit status of the test command is non-zero, the bash shell executes the commands listed in the loop. When the test command returns a zero exit status, the loop stops. As you would expect, the format of the until command is until test commands do, other commands done. Similar to the while command, you can have more than one test command in the until command statement. Only the exit status of the last command determines if the bash shell executes the other commands defined. Take a look at the following example of using the until command. This example tests the var1 variable to determine when the until loop should stop. As soon as the value of the variable is equal to 0, the until command stops the loop. The same caution should be used here. About for the while command applies when you use multiple test commands with the until command. Take a look at this example, and here the shell executes the test command specified and stops only when the last command is true. Now we can nest loops. The loop statement can use any other type of command within the loop, including other loop commands. This is called a nested loop. Care should be taken when using nested loops, because you're performing an iteration within an iteration, which multiplies the number of times commands are being run. If you don't pay close attention to this, it can cause problems in your scripts. Here is an example of nested for loop inside another for loop. Here the nested loop, also called the inner loop, iterates through its values for each iteration of the outer loop. Notice that there is no difference between the do and done commands for the two loops. The bash shell knows when the first done command is executed that it refers to the inner loop and not to the outer loop. The same applies when you mix loop commands, such as placing a for loop inside a while loop, like in this example. Again, here the shell distinguished between the do and done commands for the inner for loop from the same commands in the outer while loop. You can even combine until and while loops, like in this example. Here the outer until loop starts with a value of 3 and continues until the value equals 0, and inner while loop starts with a value of 1 and continues as long as the value is less than 5. Each loop must change the value used in the test condition, or the loop will get stuck infinitely. Next up, we'll continue to talk about loops in scripts So I'll see you in the next video. Often you must iterate through items stored inside a file. This requires combining two of the techniques covered, namely using nested loops and changing the IFS environment variable. By changing the IFS environment variable, you can force the for command to handle each line in the file as a separate item for processing, even if the data contains spaces. After you've extracted an individual line in the file, you may have to loop again to extract data contained within it. The classic example of this is processing data in the etc password file. This requires that you iterate through the etc password file line by line and then change the IFS variable value to a colon so that you can separate the individual components in each line. Take a look at the following example, which is an example of doing just what I've said. This script uses two different IFS values to parse the data. The first IFS value parses the individual lines in the etc password file. The inner for loop next changes the IFS value to the colon, which allows you to parse the individual values within the etc password lines. And when you run the script, you get output something like this. Here, the inner loop parses each individual value in the etc password entry. This is also a great way to process comma-separated data, a common way to import spreadsheet data. Now, we can control the loop. You might think that after you start a loop, you're stuck until the loop finishes all its iterations. This is not true. A couple of commands help us control what happens inside a loop: the break command and the continue command. Each command has a different use in controlling the operation of a loop. The following part of the video describes how you can use these commands to control the operation of your loops. So, the break command. The break command is a simple way to escape a loop in progress. You can use the break command to exit any type of loop, including while and until loops. You can use the break command in several situations. For example, breaking out of a single loop. When the shell executes a break command, it attempts to break out of the loop that it's currently processing, like in this example. Here, the for loop should normally have iterated through all the values specified in the list. However, when the if-then condition was satisfied, the shell executed the break command, which stopped the for loop. This technique also works for while and until loops, like in this example. The while loop here terminated when the if-then condition was met, executing the break command. Another technique is breaking out of an inner loop. When you are working with multiple loops, the break command automatically terminates the innermost loop you are in. Take a look at this example. Here, the for statement in the inner loop specifies to iterate until the b variable is equal to 100. However, the if-then statement in the inner loop specifies that when the b variable value is equal to 5, the break command is executed. Notice that even though the inner loop is terminated with the break command, the outer loop continues working as specified. The next technique is breaking out of an outer loop. There may be times when you are in an inner loop but need to stop the outer loop. The break command includes a single command line parameter value, which is break followed by n, where n indicates the level of the loop to break out of. By default, n is 1, indicating to break out of the current loop. If you set n to a value of 2, the break command stops the next level of the outer loop, like in this example. Now, when the shell executes the break command, the outer loop stops. Next, we have a continue command. The continue command is a way to permanently stop processing commands inside of a loop, but not terminate the loop completely. This allows you to set conditions within a loop where the shell won't execute commands. Here is an example of using the continue command in a for loop. In this example, when the conditions of the if-then statement are met, the value is greater than 5 and less than 10, the shell executes the continue command, which skips the rest of commands in the loop but keeps the loop going. When the if-then condition is no longer met, things return to normal. Now, you can use the continue command in while and until loops, but be extremely careful with what you are doing. Remember that when the shell executes the continue command, it skips the remaining commands. If you are incrementing your test condition variable in one of those conditions, bad things happen. Take a look at this example. Here, you'll want to make sure you redirected the output of this script to the more command so that you can stop things. Everything seems to be going just fine until the if-then condition is met and the shell executes the continue command. When the shell executes the continue command, it skips the remaining commands in the while loop. Unfortunately, that's where the var1 variable, counter variable, that is tested in the while test command is incremented. That means that the variable isn't incremented, as you can see from the continually displaying output when you run this example. And as with the break command, the continue command allows you to specify what level of loop to continue with a command line parameter. You type continue n, where n defines the loop level to continue. Here is an example of continuing an outer for loop. The if-then statement uses the continue command to stop processing the commands inside the loop, but continue the outer loop. Notice in the script output that the iteration for the value 3 does not process any inner loop statements, because the continue command stopped the processing, but it continues with the outer loop processing. Now some words about processing the output of a loop. Finally, you can either pipe or redirect the output of a loop within the shell script. You do this by adding the processing command to the end of the done command. Now, instead of displaying the results on the monitor, the shell redirects the results of the for command to the file output.txt. Take a look at the following example of redirecting the output of a for command to a file. Here the shell creates the file test23.txt and redirects the output of the for command only to the file. The shell displays the echo statement after the for command as usual. The same technique also works for piping the output of a loop to another command, like in this example. Here the state values aren't listed in any particular order in the for command list. The output of the for command is piped to the sort command, which changes the order of the for command output. Running the script indeed shows that the output was properly sorted within this script. Next up, we'll be working through a few practical examples. I'll see you there. Now that you have seen how to use different ways to create loops in shell scripts, let's look at some practical examples of how to use them. Looping is a common way to iterate through data on the system, whether it's files in folders or data contained in a file. Here are a couple of examples that demonstrate using simple loops to work with data. The first example is for finding executable files. When you run a program from the command line, the Linux system searches a series of folders looking for that file. Those folders are defined in the path environment variable. If you want to find out what executable files are available on the system for you to use, just scan all the folders in the path environment variable. That may take some time to do manually, but it's very fast working out a small shell script to do that. The first step is to create a for loop to iterate through the folders stored in the path environment variable. When you do that, don't forget to set the IFS separator character by typing IFS equals : and then followed by the code for folder in path variable do. Now that you have the individual folders in the folder variable, you can use another for loop to iterate through all the files inside that particular folder by typing the following: for file in folder variable / do. The last step is to check whether the individual files have the executable permission set, which you can do using the if-then test feature. If in square brackets -x file variable, then echo file variable, and there you have it. Putting all the pieces together in a script looks like this. Now, when you run the code, you get a listing of the executable files that you can use from the command line. And of course, you can run the script and piping it to the more command. The output will show all the executable files found in all the folders defined in the path environment variable, which is quite a few. Another example is to create multiple user accounts. The goal of the shell scripts is to make life easier for the system administrator. If you happen to work in an environment with lots of users, one of the most boring tasks can be creating new user accounts. Fortunately, you can use the while loop to make your job a little easier. Instead of having to manually enter user add commands for every new user account you need to create, you can place the new user accounts in a text file and create a simple shell script to do that for you. The format of the text file we'll use looks like this: login name, next line, comma, next line name. Here, the first entry is the login name you want to use for the new user account. The second entry is the full name of the user. The two values are separated by a comma, making this a comma-separated values or CSV file format. This is a very common file format used in spreadsheets, so you can easily create the user account list in a spreadsheet program and save it in a CSV format for your shell script to read and process. To read the data, the file data, we're going to use a little shell scripting trick. We'll set the IFS separator character to a comma as the test part of the while statement. Then to read the individual lines, we'll use the read command. And it'll look like this: while IFS equals comma in single quotes, read-r user ID name. Here the read command does the work of moving on to the next line of the text in the CSV text file. So we don't need another loop to do that. The while command exits when the read command returns a false value, which happens when it runs out of lines to read in the file. To feed the data from the file into the while command, you just use a redirection symbol at the end of the while command. So putting everything together results in this script. Take a look at this example. Here the input variable points to the data file and is used as the redirect data for the while command. The users.csv file, for example, username, comma, name and last name. To run the program, you must be the root user account, because the user-add command requires root privileges. Then by taking a quick look at the etc password file, you can see that the accounts have been created. you can do this with tail command. For example, tail /etc/passwd. And I guess it can save you lots of time in adding user accounts. So looping is an integral part of programming. The Bash shell provides 3 looping commands that you can use in your scripts. The for command allows you to iterate through a list of values supplied within the command line, contained in a variable or obtained by using file globbing to extract file and directory names from a wildcard character. The while command provides a method to loop based on the condition of a command, using either ordinary commands or the test command, which allows you to test conditions of variables. As long as the command produces a zero exit status, the while loop continues to iterate through the specified set of commands. And finally, the until command also provides a method to iterate through a command, but it bases its iterations on a command producing a non-zero exit status. This feature allows you to set a condition that must be met before the iteration stops. You can combine loops in shell scripts, producing multiple layers of loops. The Bash shell provides the continue and break commands, which allow you to alter the flow of the normal loop process based on different values within the loop. The Bash shell also allows you to use standard command redirection and piping to alter the output of a loop. You can use redirection to redirect the output of a loop to a file, or piping to redirect the output of a loop to another command. This provides a wealth of features with which you can control your shell script execution. Next up, we'll be exploring how to interact with your shell script user, because often shell scripts aren't completely self-contained. They require some sort of external data that must be supplied at the time you run them. We'll be discussing different methods with which you can provide real-time data to your shell scripts by processing. I'll see you there. In a few next videos, we'll be talking about passing parameters, tracking parameters, being shifty, working with options, standardizing options, and getting user input. Now, so far you've seen how to write scripts that interact with data, variables, and files on the Linux system. But sometimes you need to write a script that has to interact with a person running the script. The Bash shell provides a few different methods for retrieving data from people, including command line parameters, which is data values added after the command. Command line options, which is single letter values that modify the behavior of the command, and the capability to read input directly from the keyboard. We'll discuss how to incorporate these various methods into your Bash shell scripts to obtain data from the person running your script. And we'll begin with passing parameters. The most basic method of passing data to your shell script is to use command line parameters. Command line parameters allow you to add data values to the command line when you execute the script, like in this example. Here we've got the script name and the parameters 10, 30. This example passes two command line parameters 10 and 30 to the script add-m. The script handles the command line parameters using special variables. Further in this video, we'll be describing how to use command line parameters in your Bash shell scripts. And we begin with reading parameters. The Bash shell assigns special variables called positional parameters to all of the command line parameters entered. This includes the name of the script the shell is executing. The positional parameter variables are standard numbers with $0 being the script's name, $1 being the first parameter, $2 being the second parameter, and so on, up to $9 for the ninth parameter. Here is a simple example of using one command line parameter in a shell script. Here you can use the $1 variable just like any other variable in the shell script. This shell script automatically assigns the value from the command line parameter to the variable, so you don't need to do anything special. Now, if you want to enter more command line parameters for your script, each parameter must be separated by a space on the command line, and the shell assigns each parameter to the appropriate variable, like in this example. In this example, the command line parameters used were both numerical values, but you can also use text strings as parameters. As in the next example, take a look at this example. Here we use strings, text strings as parameters. Here the shell passes the string value entered into the command line to the script. However, you'll have a problem if you try to do this with a text string that contains spaces. Remember that the parameters are separated by spaces, so the shell will interpret the space as just separating the two values. To include a space at the parameter value, you must use quotation marks, either single or double quotation marks. Please note that the quotation marks used when you pass text strings as parameters are not part of the data. They just separate the beginning and the end of the data. If your script needs more than 9 command line parameters, you can continue, but the variable names change slightly. After the 9th variable, you must use braces around the variable number, such as $10 in braces. Here is an example of doing that. Take a look at this script. In this script, this technique allows you to add as many command line parameters as your script or you could possibly need. Next, reading the script name. You can use the $0 parameter to determine the script name as shell started from the command line. This can come in handy if you are writing a utility that has multiple functions or that produces log messages. Take a look at this example. However, there is a potential problem when using a different command to run the shell script. The command becomes entangled with the script name in the $0 parameter. An additional issue occurs when the actual string passed is the full script path and not just the script's name. In this case, the $0 variable gets set to the full script path and name. If you want to write a script that only uses the script's name, you'll have to do a little work in order to strip off whatever path is used to run the script or any entangled commands. Fortunately, there is a handy little command available that does just that. The base name command returns just the script's name without the path. Take a look at this example. Now that's much better, and you can use the technique to write a script that produces log messages identifying when it ran. And the next example is a script that identifies itself, and it is useful for tracking down script problems, auditing the system, and producing log messages. Now we can test parameters. Be careful when using command line parameters in your shell scripts. If the script is run without the needed parameters, wrong things can happen. When the script assumes there is data in a parameter variable and no data is present, most likely you'll get an error message from your script. This is a poor way to write scripts. Always check your parameters to make sure the data is there before using it. Take a look at this example. In this example, the -n test evaluation was used to check for data in the $1 command line parameter. Next up, you'll learn another way to check command line parameters. I'll see you in the next video. A few special bash shell variables track command line parameters. This video will describe what they are and how to use them. First, there are counting parameters. As you saw in the last video, you should verify command line parameters before using them in your script. For scripts that use multiple command line parameters, this checking can get tedious. Instead of testing each parameter, you can count how many parameters were entered on the command line. The bash shell provides a special variable for this purpose. The $hash variable counts the number of command line parameters included when the script was run. You can use this special variable anywhere in the script, just like a normal variable. Take a look at this example. Now you have the ability to test the number of parameters present before trying to use them. Take a look at another example. Here the if-then statement uses the -ne evaluation to perform a numeric test of the command line parameters supplied. If the correct number of parameters isn't present, an error message displays showing the correct usage of the script. This variable also provides a cool way of grabbing the last parameter on the command line without having to know how many parameters were used. However, you need to use a little trick to get there. If you think this through, you might think that because the $hash variable contains the value of the number of parameters, using the variable dollar in curly braces $hash would represent the last command line parameter variable. Try that and see what happens. Obviously, something will go wrong. It turns out that you can't use the $sign within the braces. Instead, you must replace the $sign with an exclamation mark. Strange, but it works. Take a look at this next example, where we are using this exclamation mark in braces. It's important to note that when there weren't any parameters on the command line, the $hash value was 0, but the $braces exclamation mark hash mark variable returns the script name used on the command line. Now, in some situations, you want to grab all the parameters provided on the command line. Instead of having to mess with using the $hash variable to determine how many parameters are on the command line and having to loop through them all, you can use a couple of other special variables. The $asterisk and $at variable provide easy access to all your parameters. Both of these variables include all the command line parameters within a single variable. The $asterisk variable takes all the parameters supplied on the command line as a single word. The word contains each of the values as they appear on the command line. Basically, instead of treating the parameters as multiple objects, the $asterisk variable treats them all as one parameter. The $at variable, on the other hand, takes all parameters supplied on the command line as separate words in the same string. It allows you to iterate through the values, separating out each parameter supplied. This is most often accomplished using a for loop. It can easily get confusing trying to figure out how these two variables operate. Let's look at the difference between the two. Take a look at this example. Notice that on the surface, both variables produce the same output, showing all the command line parameters provided at once. The next example demonstrates where the differences are. Here, by using the for command to iterate through the special variables, you can see how They each treat the command line parameters differently. The $* variable treated all the parameters as a single parameter, whereas the $@ variable treated each parameter separately. This is a great way to iterate through command line parameters. Now, another tool you have in your bash shell. The bash shell provides the shift command to help you manipulate command line parameters. The shift command literally shifts the command line parameters in their relative positions. When you use the shift command, it moves each parameter variable one position to the left by default. Thus, the value for variable $3 is moved to $2. The value of variable $2 is moved to $1, and the value for variable $1 is discarded. Note that the value of variable $0, the program name, remains unchanged. This is another great way to iterate through command line parameters. You can just operate on the first parameter, shift the parameters over, and then operate on the first parameter again. Here is a short demonstration of how this works. Here the script performs a while loop, testing a length of the first parameter's value. When the first parameter's length is 0, the loop ends. After testing the first parameter, the shift command is used to shift all parameters one position. Be careful when working with the shift command. When a parameter is shifted out, its value is lost and can't be recovered. Alternatively, you can perform a multiple location shift by providing a parameter to the shift command. Just provide the number of places you want to shift. Take a look at this example. Here, by using values in the shift command, you can easily skip over parameters you don't need in certain situations. Next up, we'll be talking about working with options in your scripts. I'll see you there. In Bash, there are commands that provide both parameters and options. Options are single letters preceded by a dash that alter the behavior of a command. Further on, we'll see three methods for working with options in your shell scripts. Options appear on the command line immediately after the script name, just the same as command line parameters. In fact, if you want, you can process command line options the same way you process command line parameters. In the previous shift_param.sh script, you saw how to use the shift command to work your way down the command line parameters provided with the script program. You can use the same technique to process command line options. As you extract each individual parameter, use the case statement to determine when a parameter is formatted as an option. Take a look at this example. Here the case statement checks each parameter for valid options. When one is found, the appropriate commands are run in the case statement. This method works no matter in what order the options are presented on the command line. The case statement processes each option as it finds it in the command line parameters. If any other parameters are included on the command line, you can include commands in the catch-all part of the case statement to process them. Now we can separate options from parameters. Oftentimes you'll run into situations where you'll want to use both options and parameters for a shell script. The standard way to do this in Linux is to separate the two with a special character code that tells the script when the options are finished and when the normal parameters start. For Linux, this special character is a double dash. The shell uses the double dash to indicate the end of the option list. After seeing the double dash, your script can safely process the remaining command line parameters as parameters and not options. To check for the double dash, simply add another entry in the case statement. Take a look at this example. This script uses the break command to break out of the while loop when it encounters the double dash. Because we are breaking out prematurely, we need to ensure that we stick in another shift command to get the double dash out of the parameter variable. For the first test, try running this script using a normal set of options and parameters. The results will show that the script assumed that all the command line parameters were options when it processed them. Next, try the same thing, only this time using the double dash to separate the options from the parameters on the command line. And now when the script reaches the double dash, it stops processing options and assumes that any remaining parameters are command line parameters. Options can be processed with values. Some options require an additional parameter value. In this situation, the command line looks as follows: -a test1, for example, -b, -c, -d, test2. Your script must be able to detect when your command line options requires an additional parameter and be able to process it appropriately. Take a look at this example of how to do that. In this example, the case statement defines 3 options that it processes. The -b option also requires an additional parameter value. Because the parameter being processed is $1, you know that the additional parameter value is located in $2, because all the parameters are shifted after they are processed. Just extract the parameter value from the $2 variable. Of course, because we used 2 parameter spots for this option, you also need to run the shift command to shift one additional position. Just as with the basic feature, this process works no matter what order you place the options in. Now you have the basic ability to process command line options in your shell scripts, but there are limitations. For example, this doesn't work if you try to combine multiple options in one parameter. It is a common practice in Linux to combine options, and if your script is going to be user-friendly, you'll want to offer this feature for your users as well. Fortunately, there is another method for processing options that can help you. We can use the getopt command. The getopt command is a great tool to have handy when processing command line options and parameters. It reorganizes the command line parameters to make parsing them in your script easier. Let's take a look at the command format. The getopt command can take a list of command line options and parameters in any form and automatically turn them into the proper format. It uses the following command format: opstring parameters. The opstring is the key word to the process. It defines the valid option letters that can be used in the command line. It also defines which option letters require a parameter value. First, list each command line option letter you're going to use in your script in the opt stream. Then place a colon after each option letter that requires a parameter value. The getopt command parses the supplied parameters based on the opt string you define. As a warning here, a more advanced version of the getopt command called getopts. Notice it is plural. The getopts command is covered later in this video or further video. Because of their nearly identical spelling, it's easier to get these commands confused, so be careful. Here is an example of how getopt works. Here the opt string defines 4 valid option letters, A, B, C, and D. A colon is placed after the letter B in order to require option B to have a parameter value. When the getopt command runs, it examines the provided parameter list and parses it based on the supplied opt string. Notice that it automatically separated the -cd options into two options and inserted the double dash to separate the additional parameters on the line. If you specify a parameter option not in the opt string, by default the getopt command produces an error message. If you prefer to just ignore the error messages, use getopt with the -q option. Please note that the getopt command options must be listed before the opt string. Now you should be ready to use this command in your scripts to process command line options. So you can use the getopt command in your scripts to format any command line options or parameters entered for your script. It's a little tricky, however, to use. The trick is to replace the existing command line options and parameters with a formatted version produced by the getopt command. The way to do that is to use the set command. The set command works with the different variables in the shell. One of the set command options is the double dash. The double dash instructs set to replace the command line parameter variables with the values on the set command's command line. The trick then is to feed the original script's command line parameters to the getopt command and then feed the output of the getopt command to the set command to replace the original command line parameters with the nicely formatted ones from getopt. And it looks something like this. Now the values of the original command line parameter variables are replaced with the output of the getopt command, which formats the command line parameters for us. Using this technique, we can now write scripts that handle our command line parameters for us. Take a look at this example. Here you'll notice that this is basically the same script as in the extract option values.sh. The only thing that changed is the addition of the getopt command to help format our command line parameters. Now when you run the script with complex options, things work much better. And of course all the original features work just fine as well. Also please note that getopt command isn't good at dealing with parameter values with spaces and quotation marks. It interprets the space as a parameter separator instead of following the double quotation marks and combining the two values into one parameter. Now, when you create your shell script, obviously you're in control of what happens. It's completely up to you as to which letter options you select to use and how you select to use them. However, a few letter options have achieved a somewhat standard meaning in the Linux world. If you leverage these options in a shell script, your scripts will be more user-friendly. Take a look at these common Linux command line options. Here you will find that -a shows all objects, -c produces a count, -d specifies a directory, -e expands an object, -f specifies a file to read data from, and so on. This is the list of command line options which are commonly used in Linux, and when writing your scripts you can get use of this list, of this table. Next up we'll be talking about getting user input. I'll see you there. Although providing command line options and parameters is a great way to get data from your script users, sometimes your script needs to be more interactive. You may need to ask a question while the script is running and wait for a response from the person running your script. The bash shell provides the read command just for this purpose. The read command accepts input either from standard input, such as from the keyboard, or from another file descriptor. After receiving the input, the read command places the data into a variable. Take a look at this example with the read command as its simplest. Now that's pretty simple. Notice that the echo command that produced the prompt uses the -n option. This suppresses the new line character at the end of the string, allowing the script user to enter data immediately after the string, instead of on the next line. This gives your script a more form-like appearance. In fact, the read command includes the -p option, which allows you to specify a prompt directly in the read command line, like in this example. You'll notice in the first example that when a name was entered, the read command assigned both the first name and last name to the same variable. The read command assigns all data entered at the prompt to a single variable, or you can specify multiple variables. Each data value entered is assigned to the next variable in the list. If the list of variables runs out before the data does, the remaining data is assigned to the last variable, like in this example. You can also specify no variables on the read command line. If you do that, the read command places any data it receives in the special environment variable reply. The reply environment variable contains all the data entered in the input, and it can be used in the shell script like any other variable. Now, be careful when using the read command. Your script may get stuck waiting for the script user to enter data. If the script must go on regardless of whether any data was entered, you can use the -t option to specify a timer. The -t option specifies the number of seconds for the read command to wait for input. When the timer expires, the read command returns a non-zero exit status. Take a look at this example. Because the read command exists with a non-zero exit status if the timer expires, it's easy to use the standard structured statements such as an if-then statement or a while loop to track what happened. In this example, when the timer expires, the if statement fails and the shell executes the commands in the else section. Instead of timing the input, you can also set the read command to count the input characters. When a present number of characters has been entered, the script automatically continues. The user doesn't have to press the enter key, so it continues assigning the entered data to the variable, like in this example. Here, this example uses the -n option with a value of 1, instructing the read command to accept only a single character before continuing. As soon as you press the single character to answer, the read command accepts the input and passes it to the variable. You don't need to press the enter key. Now, sometimes you need to input from the script user, but you don't want that input to display on the monitor. The classic example is when entering passwords, but there are plenty of other types of data that you need to hide. The -s option prevents the data entered in the read command from being displayed on the monitor. Actually, the data is displayed, but the read command sets the text color to the same as the background color. Here is an example of using the -s option in a script. Here the data typed at the input prompt does not appear on the monitor because it is assigned, but it is assigned to the variable for use in the script. And another use of read is reading from a file. Finally, you can also use this read command to read data stored in a file on the Linux system. Each call to the read command reads a single line of text from the file. When no more lines are left in the file, the read command exits with a non-zero exit status. The tricky part here is getting the data from the file to the read command. The most common method is to pipe the result of the cat command of the file directly to a while command that contains the read command. Here is an example. Here the while command loop continues processing lines of the file with the read command until the read command exits with a non-zero exit status. In this video, we'll take a look at a practical script that handles user input from what we've covered in previous video and employs the pin or pin6 command to test connectivity to other local systems. The pin command is a quick way to determine if a system is up and operating on the network. It is a useful command and is often employed as a first check. If you have only one system to check, just use the command directly. But if you have 2 or 3 or possibly even hundreds of systems to check, a shell script can help. This example has 2 methods to select the systems to check, through command line options or via file. Here is the script in action on an Ubuntu system using the command line options. So to run it, you type /checksystem.sh-t IPv4 and the IP addresses you want to check. If the IP address parameters are accidentally not included, the script produces a message for the user and exits. Another example of running the script is using a file name filled with IP addresses, which is provided by the user when no command line options are entered. And in this case, the script will check every IP address. So take a look at the script. Notice that getOpts is used to grab the provided command line option, value and parameters. But if none are entered, the script instead asks the user for the file's name, which contains the system's IP addresses and types. The file is processed using the read command. Now, you may notice some repeated code within this script. It would be nice to use functions in order to eliminate the repeated code, but we'll have to wait until the future videos when we'll be talking about creating functions, and we'll be covering this topic. Another script improvement to consider is checking for correct formatting of the user-provided file, ensuring the file line under the IP address has either IPv4 or IPv6. Also, this script doesn't have a help option, -h, which is another nice addition you can make. What are some additional user input improvements you thought about when reading through this script? So remember, you can improve the script and change it whatever way you like it. So in these previous few videos, we've had 3 methods for retrieving data from the script user. Command line parameters allow users to enter data directly on the command line when they run the script. The script uses positional parameters to retrieve the command line parameters and assign them to variables. Next, the shift command allows you to manipulate the command line parameters to rotate them within the positional parameters. This command allows you to easily iterate through the parameters without knowing how many parameters are available. You can use 3 special variables when working with command line parameters. The shell sets the $hash variable to the number of parameters entered on the command line. The $asterisk variable contains all the parameters as a single string, and the $at variable contains all the parameters as separate words. These variables come in handy when you're trying to process long parameter lists. Besides parameters, your script users can use command line options to pass information to your script. Command line options are single letters processed by a dash. Different options can be assigned to alter the behavior of your script. The bash shell provides 3 ways to handle command line options. You can iterate through the options using the positional parameter variables, processing each option as it appears on the command line. You can use the getOpt command to convert command line options and parameters into a standard format that you can process in your script. Or you can use the getOpts command, which provides more advanced processing of the command line parameters. An interactive method to obtain data from your script users is the read command. The read command allows your script to query users for information and wait. The read command places any data entered by the script user into one or more variables, which you can use within the script. Also, several options are available for the read command that allows you to customize the data input into your script, such as using hidden data entry, applying timed data entry, and requesting a specific number of input characters. Next up, we'll be looking further into how bash shell scripts output data. So far, you've seen how to display data on the monitor and redirect it to a file. Next, we'll explore a few other options that you have available, not only to direct data to specific locations, but also to direct specific types of data to specific locations. This will help you make your shell script look professional. I'll see you there. A few next videos will be talking about presenting data. We'll be discussing understanding input and output, redirecting output in scripts, redirecting input in scripts. We'll create our own redirection, list open file descriptors, suppress command output. We'll be using temporary files and login messages. So let's start with understanding input and output. So far we've seen 2 methods for displaying the output from your scripts. The first one is displaying output on the monitor screen, and the second one is redirecting output to a file. Both methods produced an all-or-nothing approach to data output. There are times, however, when it would be nice to display some data on the monitor and other data in a file. For these instances, it comes in handy to know how Linux handles input and output so that you can get your script output to the right place. The following videos describe how to use standard Linux input and output system to your advantage to help direct script output to specific locations. Now, the Linux system handles every object as a file. This includes the input and output process. Linux identifies each file object using a file descriptor. The file descriptor is a non-negative integer that uniquely identifies open files in a session. Each process is allowed to have up to 9 open file descriptors at a time. The bash shell reserves the first 3 file descriptors, namely 0, 1, and 2. It reserves it for special purposes. The 0 file descriptor is abbreviated as std_in or standard input. The 1 descriptor is abbreviated as std_out or standard output, and the 2 descriptor is abbreviated as std_err or standard error. These three special file descriptors handle the input and output from your script. The shell uses them to direct the default input and output in the shell to the appropriate location, which by default is usually your monitor. So let's take a closer look at each of these standard file descriptors in greater detail. The first one is standard input, or stdin, file descriptor, which references the standard input to the shell. For a terminal interface, the standard input is the keyboard. The shell receives input from the keyboard on the stdin file descriptor and processes each character as you type it. When you use the input redirect symbol or less than, Linux replaces the standard input file descriptor with the file referenced by the redirection. It reads the file and retrieves data just as if it were typed on the keyboard. Many bash commands accept input from stdin, especially if no files are specified on the command line. Here is an example of using the cat command with data entered from stdin. So you type cat and then you populate the data by entering different symbols. When you enter the cat command on the command line by itself, it accepts input from stdin. As you enter each line, the cat command echoes the line to the display. However, you can also use the stdin redirect symbol to force the cat command to accept input from another file or other than stdin. We've had such example previously in this course, but now we are reviewing them in more detail for you to better use this information in your future scripts. So let's return to cat command, and now the cat command uses the lines that are contained in the test file, for example. If you want to use stdin from the needed file. So you use this file as the input. You can use this technique to input data to any shell command that accepts data from stdin. Next, stdout. The standard output file descriptor references the standard output for the shell. On a terminal interface, the standard output is a terminal monitor. All output from the shell, including programs and scripts you run in the shell, is redirected or directed to the standard output, which is the monitor. Most bash commands direct their input to the stdout file descriptor by default. The example could be ls-l greater than test2. So with the output redirection symbol or greater than, all the output that normally would go to the monitor is instead redirected to the designated redirection file by the shell. You can also append data to a file. You do this with using the two greater than symbols. For example, who greater than test2. The output generated with this who command is appended to the data already in the test2 file. However, if you use the standard output redirection for your scripts, you can run into a problem, like in this example. You type ls-al bad file standard output symbol test3, and you can get the error that cannot access bad file, no such file or directory. When a command produces an error message, the shell does not redirect the error message to the output redirection file. The shell created the output redirection file, but the error message appeared on the monitor screen, not in the file. Notice that there isn't an error when trying to display the contents of the test3 file. The test3 file was created just fine, but it's empty. The shell handles error messages separately from the normal output. If you are creating a shell script that runs in background mode, often you must rely on the output messages being sent to a log file. Using this technique, if any error messages occur, they don't appear in the log file. You need to do something different. So we come to std_err or standard error. The shell handles error messages using the special std_err file descriptor. The std_err file descriptor references the standard error output for the shell. This is the location where the shell sends error messages generated by the shell or programs and scripts running in the shell. By default, the std_err file descriptor points to the same place as the std_out file descriptor, even though they are assigned different file descriptor values. This means that by default, all error messages go to the monitor display. However, as you saw in this example, when you redirect std_out, this does not automatically redirect std_err. When working with scripts, you'll often want to change this behavior, especially if you are interested in logging error messages to a log file. So we can redirect errors. You've already seen how to redirect the std_out data by using the redirection symbol. Redirecting the std_err data isn't much different. You just need to define the std_err file descriptor when you use the redirection symbol. You can do this in a couple of ways. First, redirecting errors only. As you saw, the std_err file descriptor is set to the value 2. You can select the redirect only error messages by placing this file descriptor value immediately before the redirection symbol. The value must appear immediately before the redirection symbol or it doesn't work. For example, you could type ls-al bad file 2 redirection symbol test4. And now if you cat this test4 file, you'll get the contents of the error which appeared in the previous command. Namely, ls cannot access bad file, no such file or directory. Now when you run the command, the error message doesn't appear on the monitor. Instead, the output file contains any error messages that are generated by the command. Using this method, the shell redirects the error messages only, not the normal data. Here is another example of mixing std_out and std_err messages in the same output. You could type ls-al test bad test test2 followed by 2 redirection symbol test5. And now you'll get the data separated redirection, namely the part of data goes to monitor and the part of data goes to the file. The ls command tries to find information on 3 files, test, bad test and test2. The normal standard output from the ls command went to the default std_out file descriptor, which is the monitor. Because the command redirects file descriptor to output or std_err to an output file, the shell sends any error messages generated directly to the specified redirection file. We can redirect errors and data. If you want to redirect both errors and the normal output, you need to use 2 redirection symbols. You need to precede each with the appropriate file descriptor for the data you want to redirect, and then have them point to the appropriate output file for holding the data. For example, you could type ls-al test test2 test3 bad test followed by 2 and redirection symbol test6 followed by 1 and redirection symbol test7. Now the shell redirects the normal output of the ls command that would have gone to std_out to the test7 file using the 1 greater than symbol. Any error messages that would have gone to stdr were redirected to the test6 file using the 2 greater than symbol. You can use this technique to separate normal script output from any error messages that occur in the script. This allows you to easily identify errors without having to wade through thousands of lines of normal output data. Alternatively, if you want, you can redirect both stdr and stdout output to the same output file. The bash shell provides a special redirection symbol just for this purpose, namely the ampersand greater than symbol. So you could type ls-al test, test2, test3, bad test, followed by ampersand greater than test7. When you use this ampersand greater than symbol, all the output generated by the command is sent to the same location, both data and errors. Notice that one of the error messages is out of the order from what you'd expect. The error message for the bad test file, the last file to be listed, appears second in the output file. The bash shell automatically gives error messages a higher priority than the standard output. This allows you to view the error messages together rather than having them scattered throughout the output file. So it's very handy for your reviewing the error messages. You can use the stdout and stdr file descriptors in your script to produce output in multiple locations, simply by redirecting the appropriate file descriptors. There are two methods for redirecting output in the script: temporarily redirect each line and permanently redirecting all commands in the script. Further, we'll describe how each of these methods works. So, temporary redirections. If you want to purposely generate error messages in your script, you can redirect an individual output line to stdr. You just need to use the output redirection symbol to redirect the output of the stdr file descriptor. When you redirect to a file descriptor, you must precede the file descriptor number with an ampersand. For example, echo in double quotes, this is an error message greater than ampersand 2. This line displays the text wherever the stdr file descriptor for the script is pointing, instead of the normal stdout. The following is an example of a script that uses this feature. If you run the script as normal, you don't notice any difference. Remember that by default Linux directs the stdr output to stdout. However, if you redirect stdr when running the script, any text directed to stdr in the script is redirected. So to work it properly, you should run the script followed by 2 redirect sign and the name of the file, for example, test9. Now the text will be displayed using stdout and it will appear on the monitor, whereas the echo statement text will be sent to stdr and redirected to the output file. This method is great for generating error messages in your scripts. If someone uses your script, they can easily redirect the error messages using the stdr file descriptor. Now, permanent redirections. If you have lots of data that you are redirecting in your script, it can get tedious having to redirect every echo statement. Instead, you can tell the shell to redirect the specific file descriptor for the duration of the script by using the exec command. Take a look at this example. Here the exec command starts a new shell and redirects the stdout file descriptor to a file. all output in the script that goes to stdout is instead redirected to the file. You can also redirect the stdout in the middle of a script, like in this example. Here the script uses the exec command to redirect any output going to std_err to the file test_error. Next, the script uses the echo statement to display a few lines to stdout. After that, the exec command is used again to redirect stdout to the testout file. Notice that even when stdout is redirected, you can still specify the output from an echo statement to go to std_err, which in this case is still redirected to the test_error file. This feature can come in handy when you want to redirect the output of just parts of a script to an alternative location, such as an error log. There is just one problem you run into when using this. After you redirect stdout or std_err, you can't easily redirect them back to their original location. If you need to switch back and forth with your redirection, you need to learn a trick, which we'll be talking about next, when we'll talk about redirecting input in scripts. So you can use the same technique used to redirect stdout and std_err in your scripts to redirect std_in from the keyboard. The exec command allows you to redirect std_in from a file on the Linux system. For example, you could type exec 0 less than test file. This command informs the shell that it should retrieve input from the file test file instead of in std_in. This redirection applies anytime the script requests input. Here is an example of this in action. So take a look at this script. Here we are using the read command to read data entered from the keyboard by a user. By redirecting std_in file from a file, when the read command attempts to read from std_in, it retrieves data from the file instead of the keyboard. This is an excellent technique to read data in files for processing in your scripts. A common task for Linux system administrators is to read data from log files for processing. This is the easiest way to accomplish that task. Now, some words about creating your own redirection. When you redirect input and output in your script, you are not limited to the 3 default file descriptors. We've mentioned that you could have up to 9 open file descriptors in the shell. The other 6 file descriptors are numbered from 3 through 8 and are available for you to use either input or output redirection. You can assign any of these file descriptors to a file and then use them in your scripts as well. So creating output file descriptors. You assign a file descriptor for output by using the exec command. As with the standard file descriptors, after you assign an alternative file descriptor to a file location, that redirection stays permanent until you reassign it. Here is an example of using an alternative file descriptor in a script. Take a look at it. In this script, we use the exec command to redirect file descriptor 3 to an alternative file location. When the script executes the echo statements, they display on stdout as you would expect. However, the echo statements that you redirect to file descriptor 3 go to the alternative file. This allows you to keep normal output for the monitor and redirect special information to files, such as log files. You can also use the exec command to append data to an existing file instead of creating a new file. For example, you could type exec 3, 2 redirection symbols, test13 out. Now the output is appended to the test13 out file instead of creating a new file. Now we can redirect file descriptors. Here is the trick to help you bring back a redirected file descriptor. you can assign an alternative file descriptor to a standard file descriptor, and vice versa. This means that you can redirect the original location of stdout to an alternative file descriptor and then redirect that file descriptor back to stdout. This might sound somewhat complicated, but in practice it's fairly straightforward. This example will clear things up for you. Take a look at it. In this example, it's a little crazy, so let's walk through it piece by piece. First, the script redirects file descriptor 3 to the current location of file descriptor 1, which is stdout. This means that any output sent to file descriptor 3 goes to the monitor. The second exec command redirects stdout to a file. The shell now redirects any output sent to stdout directly to the output file. However, file descriptor 3 still points to the original location of stdout, which is the monitor. If you send output data to file descriptor 3 at this point, it still goes to the monitor, even though stdout is redirected. After sending some output to stdout, which points to a file, the script then redirects stdout to the current location of file descriptor 3, which is still set to the monitor. This means that now stdout points to its original location, the monitor. This method can get confusing, but it's a common way to temporarily redirect output in script files and then set the output back to the normal settings. You can redirect input file descriptors exactly the same way as output file descriptors. Save the std_in file descriptor location to another file descriptor before redirecting it to a file. When you are finished reading the file, you can restore std_in to its original location. Take a look at this example. Here, file descriptor 6 is used to hold the location for std_in. The script then redirects std_in to a file. All the input for the read command comes from the redirected std_in, which is now the input file. When all the lines have been read, the script returns std_in to its original location by redirecting it to file descriptor 6. The script tests to make sure that std_in is back to normal by using another read command, which this time waits for input from the keyboard. Now we can create a read-write file descriptor. It may seem strange, but you can also open a single file descriptor for both input and output. You can then use the same file descriptor to both read data from a file and write data to the same file. You need to be especially careful with this method. However, as you read and write data to and from a file, the shell maintains an internal pointer indicating where it is in the file. Any reading or writing occurs where the file pointer last left off. This can produce some interesting results if you are not careful. Take a look at this example. In this example, we use the exec command to assign file descriptor 3 for both input and output sent to and from the file test file. Next, it uses the read command to read the first line in the file, using the assigned file descriptor, and then it displays the read line of data in stdout. After that, it uses the echo statement to write a line of data to the file opened with the same file descriptor. When we run the script, at first things look just fine. The output shows that the script read the first line in the test file. However, if you display the contents of the test file after running the script, you see that the data written to the file overrode the existing data. When the script writes data to the file, it starts where the file pointer is located. The read command reads the first line of data, so it left the file pointer pointing to the first character in the second line of data. When the data statement outputs data to the file, it places the data at the current location of the file pointer, overwriting whatever data was there. So be very careful when using this method. Now we can also close file descriptors. If you create new input or output file descriptors, the shell automatically closes them when the script exits. There are situations, however, when you need to manually close a file descriptor before the end of the script. To close a file descriptor, redirect it to the special symbol, which is ampersand dash. This is how it looks in the script. exec3 greater than ampersand dash. This statement closes file descriptor 3, prevented it from being used anymore in the script. Here is an example of what happens when you try to use a closed file descriptor. Take a look at this script. And after running the script, you'll get an error, bad file descriptor. Because after you close the file descriptor, you can't write any data to it in your script, or the shell produces an error message. There is yet another thing to be careful of when closing file descriptors. If you open the same file, the same output file later on in your script, the shell replaces the existing file with a new one. This means that if you output any data, it overwrites the existing file. Consider the following example of the problem. Here, after sending a data string to the test17 file and closing the file descriptor, the script uses the cat command to display the contents of the file. So far, so good. Next, the script reopens the output file and sends another data string to it. Then you display the contents of the output file, and all you see is the second data string. The shell overwrote the original output file. Now, let's take a closer look at listing open file descriptors. With only 9 file descriptors available to you, you'd think that it wouldn't be hard to keep things straight. Sometimes, however, it's easy to get lost when trying to keep track of which file descriptor is redirected where. To help you keep things in order, the bash shell provides the lsof command, lsof. The lsof command lists all the open file descriptors on the entire Linux system. This includes file opened by all the processes running in the background, as well as any user accounts logged into the system. Plenty of command line parameters and options are available to help filter out the lsof output. The most commonly used are -p, which allows you to specify a process ID or PID, and -d, which allows you to specify the file descriptor numbers to display separated by commas. To easily determine the current PID of the process, you can use the special environment variable, which is $2, which the shell sets to the current PID. The -a option is used to perform a Boolean AND of the results of the other two options to produce the following. So you could type, for example, /usr/bin/lsof-a-p $2 $d 0,1,2. And this will show the default file descriptors 1, 0, and 2 for the current process, the bash shell. The default output of the lsof contains several columns of information, namely colon command, it's the first 9 characters of the name of the command in the process. colon pid, the process ID of the process, colon user, the login name of the user who owns the process. Then we'll get FD, which is file descriptor number and access type, which is the type of the file, device, size, node, and name. The file type associated with stdin, stdout, and stdr is character mode, because the stdin, stdout, and stdr file descriptors all point to the terminal. The name of the output file is the device name of the terminal. All three standard files are available for both reading and writing, although it does seem odd to be able to write to stdin and read from stdout. Now let's look at the result of the lsof command from inside a script that's opened a couple of alternative file descriptors. So take a look at this script, which will create three alternative file descriptors. 2 for output, namely 3 and 6, and 1 for input, namely 7. When the script runs the lsof command, you can see the new file descriptors in the output. So the file name shows the complete path name for the files used in the file descriptors. It shows each of the files as type reg, which indicates that they are regular file on the file system. Sometimes you may not want to display any output from your script. This often occurs if you are running a script as a background process. If any error messages occur from the script while it's running in the background, the shell emails them to the owner of the process. This can get tedious, especially if you run scripts that generate minor, not important errors. To solve that problem, you can redirect stdr to a special file called the null file. The null file is pretty much what it says it is, a file that contains nothing. Any data that the shell outputs to the null file is not saved, thus the data is lost. The standard location for the null file is on Linux system is /dev/null. Any data you redirect to that location is thrown away and doesn't appear. So if you'll type ls-al redirect /dev/null and try to cat this file /dev/null, you'll get nothing. This is a common way to suppress any error messages without actually saving them. So you could type the following: ls-al bad file test16 to redirect /dev/null. You can also use the dev null file to input redirection as an input file. Because the dev null file contains nothing, it is often used by programmers to quickly remove data from an existing file without having to remove the file and recreate it. So if you create, let's say, test file with 3 lines containing this is the first line, second line, third line, and then you'll type the following command: cat /dev/null redirect test file. The file test file will still exist on the system, but now it will be empty. This is a common method used to clear out log files that must remain in place for applications to operate. So take a note on this technique and you can use it further in your scripts. Now, some words about using temporary files. The Linux system contains a special directory location reserved for temporary files. Linux uses the /tmp directory for files that don't need to be kept indefinitely. Most Linux distributions configure the system to automatically remove any files in the /tmp directory at boot up. Any user account on the system has privileges to read and write files in the /tmp directory. This feature provides an easy way for you to create temporary files that you don't necessarily have to worry about cleaning up. There is even a specific command to use for creating a temporary file, the mktemp command. This command allows you to easily create a unique temporary file in the /tmp folder. The shell creates the file but doesn't use your default umask value. Instead, it only assigns read and write permissions to the file's owner and makes you the owner of the file. After you create the file, you have full access to read and write to and from it from your script, but no one else can access it, other than the root user, of course. Now, creating a local temporary file is easy. By default, mktemp creates a file in the local directory. To create a temporary file in a local directory with the mktemp command, you just need to specify a file template. The template consists of any text file name, plus 6 axes appended to the end of the file name. For example, you could type mktemp testing.6axes. The mktemp command replaces the 6 axes with a 6-character code to ensure that the file name is unique in the directory. You can create multiple temporary files and be assured that each one is unique. So if you repeat creating the files with the previous command, you'll get a unique file each time you are doing this. And as you can see, the output of the mkdir command is the name of the file that it creates. When you use the mktemp command in a script, you'll want to save that file name in a variable so that you can refer to it later in the script. Take a look at this example. Here the script uses the mktemp command to create a temporary file and assign the file name to the temp file variable. It then uses the temporary file as the output redirection file for the descriptor 3. After displaying the temporary file name on the stdout, it writes a few lines to the temporary file, and then it closes the file descriptor. Finally, it displays the contents of the temporary file and then uses the rm command to remove it. Now, we can use the -t option, which forces mktemp to create the file in the temporary directory of the system. When you use this feature, the mktemp command returns the full path name used to create the temporary file, not just the file name. So try typing mktemp-t test.6axes. And here, because the mktemp command returns the full path name, you can then reference the temporary file from any directory on the Linux system, no matter where it places the temporary directory. So take a look at this example. Here, when mktemp creates the temporary file, it returns the full path name to the environment variable. You can then use that value in any command to reference the temporary file. We can also create a temporary directory. The -d option tells the mktemp command to create a temporary directory instead of a file. You can then use that directory for whatever purposes you need, such as creating additional temporary files. Take a look at this example. The script creates a directory in the current directory and uses the cd command to change to that directory before creating 2 temporary files. The 2 temporary files are then assigned to file descriptors and used to store output from the script. So as you can see, this technique can get in handy when working with temporary files. Now some words about login messages. Sometimes it's beneficial to send output both to the monitor and to a file for login. Instead of having to redirect output twice, you can use the special t command. The t command is like a T connector for pipes. It sends data from std in to two destinations at the same time. One destination as std out, the other destination is a file name specified on the T command line. Because T redirects data from std in, you can use it with the pipe command to redirect output from any command. For example, date pipe t test file. And if you cat test file, you'll get the output from the date command. The output appears in std out and is written to the file specified. Be careful, by default the T command overrides the output file on each use. For example, if you type who pipe t test file and cat test file, you'll get the output from the who command, not from the date command. If you want to append data to the file, you must use the -a option. So you could type date pipe t-a test file and then type who pipe t-a test file, and you'll get the output from both commands, who and date. Using this technique, you can both save data in files and display the data on the monitor for your users. Take a look at this example. Now you can save a permanent copy of your output at the same time as you're displaying it to your users. Next up, we'll be working through a practical example. I'll see you there. File redirection is very common, both when reading files into scripts and when outputting data from a script into a file. This example script does both for those things. It reads a CSV formatted data file and outputs SQL insert statement to insert the data into a database. The shell script uses a command line parameter to define the name of the CSV file from which to read the data. The CSV format is used to export data from spreadsheets, so you can place the database data into a spreadsheet, save the spreadsheet in a CSV format, read the file, and create insert statements to insert the data into a MySQL database. So here is what the script looks like. That's a pretty short script thanks to the file redirection that goes on. There are three redirection operations happening in the script. The while loop uses the read statement to read text from the data file. Notice in the done statement the redirection symbol. The $1 represents the first command line parameter when you run the test23 program. That specifies the data file from which to read the data. The read statement parses the text using the IFS character, which we specify as a comma. The other two redirection operations in the script both appear in the same statement. So here we type cat to redirection out file variable, and we are reading from the standard input. This one statement has one output, append redirection, the double greater than symbol, and one input, append redirection, the double less than symbol. The output redirection appends the cat command output to the file specified by the out file variable. The input to the cat command is redirected from the standard input to use the data stored inside the script. The EOF symbol marks the start and end delimiter of the data that's appended to the file. Next, the text creates a standard SQL insert statement. Notice that the data values are replaced with the variables from the data read from the read statement. So basically the while loop reads the data one line at a time, plugs those data values into the insert statement template and then outputs the result to the output file. For this example, we can use the input data file, for example, members.csv, containing the needed data in a comma-separated format. For example, Joe, Doe, 123, Main Street, New York, and so on. When you run the script, nothing appears in the output of the monitor. But when you look at the members.sql output file, you should see the output data, containing the commands that you can easily import into a MySQL database table. So it will contain insert into members in brackets lname, fname, address, and so on, then values in brackets and in single quotes Joe, Doe, and so on. Now let's wrap up previous several videos. So understanding how the bash shell handles input and output can come in handy when creating your scripts. You can manipulate both how the script receives data and how it displays data to customize your script for any environment. You can redirect the output of a script from the standard input, which is stdin, to any file on the system. You can also redirect the output of the script from the standard output, which is stdout, to any file on the system. Besides the stdout, you can redirect any error messages your script generates by redirecting the stderr output. This is accomplished by redirecting the file descriptor associated with the stderr output, which is file descriptor 2. You can redirect stderr output to the same file as the stdout output, or to a completely separate file. This enables you to separate normal script messages from any error messages generated by the script. The bash shell allows you to create your own file descriptors for use in your scripts. You can create file descriptors 3 through 8 and assign them to any output file you desire. After you create a file descriptor, you can redirect the output of any command to it using the standard redirection symbols. The bash shell also allows you to redirect input to a file descriptor, providing an easy way to read data contained in a file into your script. You can use the lsoff command to display the active file descriptors in your shell. Also, Linux systems provide a special file called /dev/null to allow you to redirect output that you don't want. The Linux system discards anything redirected to the dev null file. You can also use this file to produce an empty file by redirecting the contents of the dev null file to the file. The mktemp command is a handy feature of the bash shell that allows you to easily create temporary files and directories. Simply specify a template for the mktemp command and it creates a unique file each time you call it, based on the file template format. You can also create temporary files and directories in the /tmp directory on the Linux system, which is a special location that isn't preserved between system boots. The t command is a convenient way to send output both to the standard output and to a log file. This enables you to display messages from your script on the monitor and store them in a log file at the same time. Next up, you'll see how to control and run your scripts. Linux provides several different methods for running scripts other than directly from the command line interface prompt. You'll see how to schedule your scripts to run at a specific time, as well as learn how to pause them while they are running. I'll see you there. As you start building advanced scripts, you'll probably wonder how to run and control them on your Linux system. As far in this course, the only way we've run scripts is directly from the command line interface in real-time mode. This isn't the way to execute scripts in Linux. Quite a few options are available for running your shell scripts. There are also options for controlling your scripts. Various control methods include sending signals to your script, modifying a script's priority, and switching the run mode while the script is running. Further on, we'll examine the various ways you can control your shell scripts. And we'll start with handling signals. As you know, Linux uses signals to communicate with processes running on system. As you remember, there are different Linux signals which Linux uses to stop, start, and kill processes. You can control the operation of your shell script by programming the script to perform certain commands when it receives specific signals. There are more than 30 Linux signals that can be generated by the system and applications. Take a look at this list of the most common Linux system signals that you'll run across in your shell script writing. Signal number 1 is cyc-hup, which hangs up the process. Number 2, cyc-int interrupts the process. Number 3, cyc-quit stops the process. 5, cyc-kill unconditionally terminates the process. 15, cyc-term terminates the process if possible. 18, cyc-cont continues a stop process. 19, cyc-stop unconditionally stops but doesn't terminate the process. And cyc-20, cyc-tstp stops or pauses the process but doesn't terminate. Now, by default, the bash shell ignores any cyc-quit or signal number 3 and cyc-term or signal number 15 signals it receives. So an interactive shell cannot be accidentally terminated. However, the bash shell does not ignore any received cyc-hup or signal number 1 and cyc-int or signal number 2. If the bash shell receives a cyc-hup signal, such as when you leave an interactive shell, it exits. Before it exits, however, it pauses the cyc-hup signal to any processes started by the shell, including any running shell scripts. With a cyc-int signal, the shell is just interrupted. The Linux kernel stops giving the shell processing time on the CPU. When this happens, the shell passes the cyc-int signal to any processes started by the shell to notify them of the situation. As you probably have noticed, the shell passes these signals on to your shell script program for processing. However, a shell script's default behavior does not govern these signals, which may have an adverse effect on the script's operation. To avoid this situation, you can program your script to recognize signals and perform commands to prepare the script for the consequences of the signal. Now, the bash shell allows you to generate two basic Linux signals using key combinations on the keyboard. This feature comes in handy if you need to stop or pause a runaway script. And as you might know, you can interrupt a process by pressing the Ctrl+C. This Ctrl+C key combination generates a cyc-int signal and sends it to any processes currently running in the shell. You can test this by running a command that normally takes a long time to finish and pressing the Ctrl+C key combination. For instance, you can run sleep 60 and then press Ctrl+C. This sleep command pauses the shell's operation for the specified number of seconds and returns the shell prompt. The Control+C key combination sends a cyc-int signal which simply stops the current process running in the shell. By pressing the Control+C key combination before the time passed, in our case it's 60 seconds, you permanently terminated sleep command. We can also pause a process. Instead of terminating a process, you can pause it in the middle of whatever it's doing. Sometimes this can be a dangerous thing. For example, if a script has a file lock open on a crucial system file. But often it allows you to peek inside what a script is doing without actually terminating the process. The Control+Z key combination generates a cyc-ts-tp signal, stopping any processes running in the shell. Stopping a process is different than terminating the process. Stopping the process leaves the program in memory and able to continue running from where it left off. When you use the Control+Z combination, the shell informs you that the process has been stopped. The number in the square brackets is the job number assigned by the shell. The shell refers to each process running in the shell as a job and assigns each job a unique number within the current shell. It assigns the first started process job number 1, the second job number 2, and so on. We've talked about this in controlling processes and jobs section. If you have a stopped job assigned to your shell session, Bash warns you the first time you try to exit the shell. So you could try running sleep command with 70 seconds, then stop it by pressing Control+Z, and then type exit, and you'll get the warning there are stopped jobs. Now, as you remember, you can view the stopped jobs using the ps command by typing ps-l. Here in the s column, which is process state, the ps command shows the stopped job state as t. This indicates the command is either being traced or is stopped. If you really want to exit the shell with a stopped job or jobs still active, just type the exit command again, and the shell exits terminating the stopped jobs. Alternatively, now that you know the PID or the stopped job, you can use the kill command to send a cyc kill, it's signal number 9, to terminate it. Each time the shell produces a prompt, it also displays the status of any jobs that have changed states in the shell. After you kill a job, the shell displays a message showing that the job was killed while running, and then provides the prompt. Please note that on some Linux systems, when you kill the job, you initially don't get any response. However, the next time you do something that produces a shell prompt, such as pressing the Enter key, you'll see a message indicating that the job was killed. Next up, we'll be talking about trapping signals. I'll see you there. Instead of allowing your scripts to leave signal ungoverned, you can trap them when they appear and perform other commands. The trap command allows you to specify which Linux signals your shell script can watch for and intercept from the shell. If the script receives a signal listed in the trap command, it prevents it from being processed by the shell and instead handles it locally. The format of the trap command is trap followed by command signals. On the trap command line, you just list the commands you want the shell to execute along with a space-separated list of signals you want to trap. You can specify the signals either by their numeric value or by their Linux signal name. Here is an example of using the trap command to capture the cyc-int signal and govern the script's behavior when the signal is sent. The trap command used in this example displays a simple text message each time it detects the seek int signal. Trapping this signal makes this script, so to say, immune to the user attempting to stop the program by using the bash shell keyboard Ctrl+C command. Each time the Ctrl+C key combination is used, the script executes the echo statement specified in the trap command instead of not managing the signal and allowing the shell to stop the script. As a warning here, if a command in your script is interpreted by a signal using trap with a specified command, will not necessarily allow the interpreted command to continue where it left off. To keep critical operations flowing in your scripts, use trap with a null specification along with a list of the signals to trap, such as trap in double quotes, two double quotes, seek int. Using trap in this way allows the script to completely ignore signal interruptions and continue its important work. Now, besides trapping signals in your shell script, you can trap them when the shell script exits. This is a convenient way to perform commands just as the shell finishes its job. To trap the shell script exiting, just add the exit signal to the trap command, like in this example. Now, when the script gets to the normal exit point, the trap is triggered and the shell executes the command you specify in the trap command line. The exit trap also works if you prematurely exit the script. And here, because the seek int signal isn't in the trap command list, when the Ctrl+C key combination is used to send that signal, the script exits. However, before the script exits, because the exit is trapped, the shell executes the trap command. We can modify and remove a trap. To handle traps differently in various sections of your shell script, you simply reissue the trap command with new options. Take a look at this example. Here, after the signal trap is modified, the script manages the signal or signals differently. However, if a signal is received before the trap is modified, the script processes it per the original trap command. If you try out the trap command in your interactive shell session, you can view that signals are being trapped by issuing the trap-p. If nothing displays, your shell session is handling signals in the default manner. Now you can also remove a set trap. Add two dashes after the trap command and a list of the signals you want to return to default behavior. Like in this example. Take a look at it. As a note here, you can use a single dash instead of double dash after the trap command to remove signals traps. Both the single and double dash work properly. And here, after the signal trap is removed, the script handles the seek int signal in its default manner, terminating the script. However, if a signal is received before the trap is removed, the script processes it per the original trap command. Sometimes running a shell script directly from the command line is inconvenient. Some scripts can take a long time to process and you may not want to tie up the command line interface as it executes. While the script is running, you can't do anything else in your terminal session. Fortunately, there is a simple solution to that problem. When you use the ps-e command, you see a whole bunch of different processes running on the Linux system. Obviously, all these processes are not running on your terminal. In fact, many are not running on any terminal. They are running in the background. In background mode, a process runs without being associated with the std-in, std-out, and std-err on a terminal session. You can exploit this feature with your shell scripts as well, allowing them to run behind the scenes and not lock up your terminal session. The following video describes how to run your scripts in background mode on your Linux system. So running in the background, running a shell script in background mode is a fairly easy thing to do. To run a shell script in background mode from the command line interface, just place an ampersand symbol after the command. So you type a script name with ampersand followed after it. Take a look at this example. You can use this example to test this background mode. So when you place the ampersand symbol after a command, it separates the command from the current shell and runs it as a separate background process on the system. The first thing that displays is the line with the number in square brackets, which is the job number assigned by the shell to the background process. The next number is a process ID or PID. As you might know, we've met it many times before. So the Linux system assigns each process its PID. Every process running on the Linux system must have a unique PID. As soon as the system displays these items, a new command line interface prompt appears. Now you are returned to the current shell and the command you executed runs safely in background mode. At this point, you can enter new commands at the prompt. When the background process finishes, it displays a message on the terminal. It will show the number and the status of the job, which is done, for example, allowing with the command used to start the job, minus the ampersand sign. Be aware that while the background process is running, it still uses your terminal monitor for stdout and stderr messages. If you run this example, you'll notice that the output from the background output.sh script will be displayed. The output intermixes with the shell prompt, which is why you'll get start in the script and it'll appear next to the $prompt. You can still issue commands while this output is occurring. And while the background output.sh script is running in the background, the command pwd, for example, can be entered. The script's output, the type command, and the command's output all intermixes with each other output display. This can be confusing. It is a good idea to redirect stdout and stderr for scripts you will be running in the background to avoid this messy display. But it's good to know that it is a normal behavior to intermix each other's output on display. Now we can run multiple background jobs. You can start any number of background jobs at the same time from the command line prompt. You can start one script, for example, test a script.sh with ampersand, another script, test bscript.sh ampersand, and so on. Each time you start a new job, the Linux system assigns it a new job, number, and PID. You can see that all the scripts are running using the ps command. Now, you must be careful when using background processes from a terminal session. You can notice in the output from the ps command that each of the background processes is tied to the terminal session. For example, pts/0 terminal. If the terminal session exits, the background process also exits. Please note that when you attempt to exit a terminal session, a warning is issued if there are stopped processes. However, with background processes, only some terminal emulators remind you that a background job is running before you attempt to exit the terminal session. So if you want your script to continue running in background mode after you logged off the console, there is something else you need to do. Namely, we can run scripts without a hang-up. Because sometimes you may want to start a shell script from a terminal session and let the script run in background mode until it finishes, even if you exit the terminal session. You can do this by using the no-hup command. The no-hup command blocks any cyc-hup signals that are sent to the process it is protecting. This prevents the process from exiting when you exit your terminal session. The format used for no-hup command is as follows: no-hup followed by command. Here is an example using a shell script launched into the background as the command. As with a normal background process, the shell assigns the command a job number, and the Linux system assigns a PID number. The difference is that when you use the no-hup command, the script ignores any cyc-hup signals sent by the terminal session if you close the session. Because the no-hup command disassociates the process from the terminal, the process loses the stdout and stdr output links. To accommodate any output generated by the command, the no-hup command automatically redirects stdout and stdr messages to a file called nohup.out. Please note that, if possible, the nohup.out file is created in your current working directory. Otherwise, it is created in your home directory. The nohup.out file contains all the output that would normally be sent to the terminal monitor. After the process finishes running, you can view the nohup.out file for the output results. The output appears in this file just as if the process ran on the command line. Now, if you run another command using nohup, the output is appended to the existing nohup.out file. Be careful when running multiple commands from the same directory, because all the output is sent to the same nohup.out file, which can get confusing. So, with the use of nohup, you can run scripts in the background, log out of your terminal session to accomplish other tasks without stopping the script process, and check on its output later. There is even more flexibility to managing your background jobs, and we'll be talking about it during our next video. I'll see you there.
Sometimes, you may want to start a shell script from a terminal session, and let the script run in background mode until it finishes, even if you exit the terminal session. You can do this by using the nohup command. The nohup command blocks any SIOP signals that are sent to the process it is protecting. This prevents the process from exiting when you exit your terminal session. The format used for the nohup command is as follows: nohup command. Here's an example using a shell script launched into the background as the command: nohup/testscript.sh %. As with a normal background process, the shell assigns the command a job number, and the Linux system assigns a PID number. The difference is that when you use the nohup command, the script ignores any SIOP signals sent by the terminal session if you close the session. Because the nohup command disassociates the process from the terminal, the process loses the stdout and stderr output links. To accommodate any output generated by the command, the nohup command automatically redirects stdout and stderr messages to a file called nohup.out. Note: if possible, the nohup.out file is created in your current working directory. Otherwise, it is created in your home directory. The nohup.out file contains all the output that would normally be sent to the terminal monitor. After the process finishes running, you can view the nohup.out file for the output results. The output appears in the nohop.out file just as if the process ran on the command line. Note: if you run another command using nohop, the output is appended to the existing nohop.out file. Be careful when running multiple commands from the same directory, because all the output is sent to the same nohop.out file, which can get confusing. With the use of nohop, you can run scripts in the background, log out of your terminal session to accomplish other tasks without stopping the script process, and check on its output later. There's even more flexibility to managing your background jobs, which is covered next. Controlling the job. Earlier in this course, you saw how to use the Ctrl+C key combination to stop a job running in the shell. After you stop a job, the Linux system lets you either kill or restart it. You can kill the process by using the kill command. Restarting a stopped process requires that you send it a sigcont signal. The function of starting, stopping, killing, and resuming jobs is called job control. With job control, you have full control over how processes run in your shell environment. This section describes the commands used to view and control jobs running in your shell. Viewing jobs. The key command for job control is the jobs command. The jobs command allows you to view the current jobs being handled by the shell. Though it doesn't contain the jobs command, the following script will help us demonstrate the command's power. The script uses the $variable to display the PID that the Linux system assigns to the script, then it goes into a loop, sleeping for 10 seconds at a time for each iteration. You can start the script from the command line interface, and then stop it using the Ctrl+Z key combination. Using the same script, another job is started as a background process, using the ampersand symbol. To make life a little easier, the output of that script is redirected to a file so that it doesn't appear on the screen. The jobs command enables you to view the jobs assigned to the shell, as shown here. The jobs command shows both the stopped and the running jobs, along with their job numbers and the commands used in the jobs. Note: you probably noticed the plus and minus signs in the jobs command output. The job with the plus sign is considered the default job. It would be the job referenced by any job control commands, if a job number wasn't specified in the command line. The job with the minus sign is the job that would become the default job when the current default job finishes processing. There will be only one job with the plus sign and one job with the minus sign at any time, no matter how many jobs are running in the shell. You can view the various jobs PIDs by adding the L parameter, lowercase l, to the jobs command. The jobs command uses a few different command line parameters, including the ones shown in table. If you need to remove stopped jobs, use the kill command to send a sigkill 9 signal to the correct PID. It's a good idea to double-check that you've got an accurate process number to avoid stopping processes that need to keep running. It's a little tedious to check and recheck for correct PIDs. So in the next section, you'll learn how to use commands to interact with the default process using no PID or job number.